A very good morning to all of you. We hope that you had a nice stay last night and enjoyed yesterday's sessions, all sessions. So we are starting the second day of the international conference. The first talk will be by Professor Armugam. And before we start that, I would like to invite Professor G.O.S. Katona from Hungary to chair this session. So let us welcome Professor Katona to chair this session. Please, sir.
Good morning, Suprabhat. It's my pleasure to introduce Professor Arumugam. Actually, it's difficult to introduce someone if everybody knows him. And I have a long list of positions, results. If I read all of them, then there will be no time for his lecture. So I will just tell a few words. So he is one of the founders of the Indian graph theory. He has a very large number of papers, about nearly 300, and 20 books, and the number of citations is counted in thousands. Let me mention one paper, the edge domination, has already almost 200 citations. And if you look at his activity in organizing conferences, having students, writing books, so he has a very wide scale of activity. So probably everybody knows what his name means. Aru in Tamil means six. So his name means six faces. And I think it should be changed into 100 faces, because he has so many faces within mathematical science and applications. And we shouldn't forget that he founded this very important X journal, and he's still the editor-in-chief of it. Okay, please, Professor Arumugam.
So I'm very happy to be a part of this conference. And I will start with a small note as a motivational factor for the younger students who are sitting here. I had delivered lectures on several conferences in this campus. And last year, when there was a pandemic situation, we had an online workshop for about a week. And I delivered 4 talks in that workshop, covering various aspects of domination. At the end of the talk, I gave an open invitation that any participant who is willing to work on any of the topics that I have given is free to contact me, provided he is a full-time research scholar and has already completed the coursework, so that he is ready to take off research. Within 24 hours, I received a mail from one of the participants, David Collarcap, a full-time scholar from University of Mysore, saying that he is interested in a particular topic that I have introduced. I would like to work with you, but only thing is I am not satisfying the condition that I have completed the coursework. because the coursework was delayed due to the pandemic situation. They said, no problem, we shall work together. And we worked together and we published the paper and we put an acknowledgement in the paper stating that this collaboration emerged from the workshop organized at Ramanujan College during such a period, wherein the first author was an invited speaker of the workshop and the second author was a participant. And we are thankful to the coordinator, Rajesh Singh, and the principal of the college for having provided such an opportunity for us to come together to work on the topic. So this is how my association with this institution came. I hope a similar thing should happen today after the talk, because I have a lot of new things to say and new problems to work at. Okay. So I'll now talk about the all of you are familiar with the Sudoku puzzle, which you solve almost as a entertainment. Okay. So we have a 9x9 grid where some entries are there, and you have to complete the puzzle by filling out all the entries with the conditions that each row, each column, and the subsquares have the entry 1 to 9. Okay. So what I thought is, let us take the 9x9 grid, make each row a complete graph, each column a complete graph K9, and each 3x3 subsquare, the 9 subsquares, also complete graphs. Then the Sudoku puzzle is simply a coloring of some of the vertices of the graph, because each row is a complete graph. We are going to have distinct entries. So the solution to a Sudoku puzzle is simply a proper vertex coloring of the graph. Okay, that K9 Cartesian K9 with 9 squares forming complete graph. So the solution to Sudoku puzzle is simply a proper vertex coloring of the graph. The graph has chromatic number 9. Okay, because K9 is present. So what we are doing is, so if you take the 81 cells and the 3x3 subsquares and get a graph in which the rows, columns, and the 3x subsquares are all complete graphs. So chromatic number is 9, and the solution of the Sudoku puzzle is simply a proper vertex coloring of G. So the Sudoku puzzle corresponds to a proper vertex coloring of an induced subgraph using at most 9 colors. The puzzle is yes, coloring of the induced subgraph, and the solution is coloring of the whole graph. So the process of solving a Sudoku puzzle is simply extending a partial coloring of an induced subgraph to a 9 coloring of the whole graph. Okay, the given puzzle is a partial coloring of an induced subgraph of the graph, and the full solution is simply a coloring of the whole graph, 9 coloring of the whole graph. So motivated by this, we say that you start with an arbitrary connected graph of order n with chromatic number k, take an induced subgraph and take a proper coloring of the induced subgraph using at most k colors. So it's a partial coloring of the graph G. The coloring is it's an extendable coloring for the induced subgraph if it can be extended to a k coloring of the whole graph. If further the extension is uniquely done, then it is called a Sudoku coloring. Because a Sudoku puzzle has a unique solution. You don't have two solutions for a given Sudoku puzzle. So if the coloring is uniquely extended to a proper k coloring of the graph, then that coloring is called a Sudoku coloring. And what's the smallest order of such an induced subgraph which admits a Sudoku coloring? That I call the Sudoku number of the graph and denoted by a symbol S and G. So Sudoku number of a graph is simply the order of a smallest order of a subgraph of G, induced subgraph of G, such that on that subgraph there is a coloring which is uniquely extendable to the coloring of the whole graph. And for the standard Sudoku graph, as on today, we have no Sudoku puzzle with less than or equal to 16 clues. The smallest Sudoku puzzle has 17 clues as on today. And a few years back, a paper came saying that there is no Sudoku puzzle with 16 clues, but the proof was computer based. And mathematicians are still believing that the proof is not completely satisfactory. Okay. So as to my definition, the standard Sudoku puzzle, the number is 17. We have a Sudoku puzzle with 17 clues. Less than 17, we do not know. So it is greater than or equal to 17. That's all I can say. For the standard Sudoku puzzle, it is greater than or equal to 17. If you can prove mathematically that there is no Sudoku puzzle with 16 clues, then this number will become exactly equal to 17. Okay. We should come back to this. So how I am going to look at this problem is, if you take an extendable coloring of a graph G, then for each uncolored vertex, there are some possible colors that can be used to color that vertex. So the set of all possible colors for that vertex is a color list for V. So problem of extending the original partial coloring is simply a list coloring problem. Okay. The problem of extending the original given coloring is simply a list coloring. Because, for example, if in the standard Sudoku puzzle, if one row has already 1, 2, 3 entry, then for all the other elements in the row, the list will not have 1, 2, 3. It's already used for a neighbor. Okay. So associate with every vertex the possible colors that can be used to color that vertex. That is, omit those colors which are already assigned to the neighbors of V. Then the extending problem is simply a list coloring problem. To give an example, see, this is my graph and this is the partial coloring. I have colored 5 vertices. This is a graph with chromatic number 3. So I have used 3 colors. Okay. Now I am going to extend this. coloring. Here, I have two possible extensions. I have two possible extensions. You see, if you start from I'll see which is the right place to start. Okay. So these two vertices have color list 2, 3, because one is forbidden. This vertex can be anything. And for this vertex, the color list is 1, 3. Okay. And for this vertex, it is again 2, 3. So I have here color list is 2, 3. I have put 2. And here the color list is 2, 3. I have chosen 2, and so on. So this is an extendable coloring, but it is not a Sudoku coloring because we have two extensions here. The extensions are different. I have a difference here. Okay. So that two different extensions. Whereas here, it is not extendable. Again, given another coloring for the same graph, this is not extendable because the vertices V1, V2, and there's something wrong here. V1, V2, and V4. The 2 must be here. Here, this small mistake doesn't matter. I have put 1 here, but I have made a mistake here. It's 1, so that all these 3 things will have color is 2, 3, and they form a triangle. Therefore, it's not extendable. Assume that that's 1 here, okay? So that these 3 vertices have color list 2, 3, and that makes it not extendable. And here is a uniquely extendable case, the Sudoku coloring actually. Because I have given the color list here for all the vertices, the color list is given. So for this it's 2, 3, and for this 1, 3. Okay. Now you cannot give color 2 to this vertex. Suppose you give color 2 here, then this list will become 3 because 2 is used. This becomes 3. Okay. So you have to give 3. You have to give 3. So this 2, 3 now is further is not extendable. You see that? If B2 is assigned color 3, then both V3, see, if this is assigned color 3, both this okay, now we are here. So if B2 is given color 3, then 3 is removed from here, 3 is removed from here. Therefore, this is forced to 1. Okay. Color list is singleton set. So this color is forced. Now you see that there is no possibility of coloring this because its color list is 1, 3, 1 is assigned here, 3 is assigned here, so extension is not possible. Okay. So if 3 is assigned here, 2 is forced here, 1 is forced here, and therefore you'll see that this is not colorable. Okay. Therefore, this is to be given 3. Once this is given 3, this is forced 2, and this is forced 1, and therefore this is forced 3, and the coloring is unique. So this is a Sudoku coloring for the graph. The extension is unique. Okay, the extension is unique. Fine. Okay. So we are going to make some statements which will help us to say that the Sudoku number can be defined, can be determined easily. Let us take LXI, the list of colors for the vertex Vi in a path. If each list has at least two members, then it's not a Sudoku coloring. There will be at least 2 distinct extensions for this coloring. Okay. So for a path, if the list at every vertex is having at least 2 colors, then it is not a Sudoku coloring. For a cycle, if the list at every vertex is having exactly 2 members and it's a proper subset of the 3 colors 1, 2, 3, then again we have 2 list colorings, so that such a coloring will not be a Sudoku coloring. So with this, I'll come back to this. So if you have a graph with chromatic number at least 3, and if you have an extendable coloring on an induced subgraph, if the number of colors used is less than or equal to the chromatic number -2, then 2 new color classes will be created. And in this case, the extension will not be unique. Therefore, if you want to have a unique extension in the partial coloring, you have to use at least k-1 colors. Okay. In the partial coloring, you have to use at least k-1 colors. If you use only less than or equal to k-2 partial colors, when you extend it to a k coloring, 2 new color classes are going to be created, and therefore they can be interchanged in the process, showing that the extension is not unique. So you see that in a Sudoku puzzle, only 1 symbol may be missing. 2 symbols cannot be missing. Okay. So how do you solve a Sudoku puzzle? So you take an extendable coloring. These are vertices to be colored. S is already colored vertices. The complement is to be colored. You choose the first vertex that can be colored in the extension process. Once you color that vertex, your C1 becomes the S union W1. Then choose the next vertex to be colored, add it, and continue this process until the whole thing is colored. Okay. So when you do this process, I change the list as follows. Whenever a vertex is colored, you make the list set as empty, because it is no more to be colored. Its color is fixed. And then remove that color from all the neighbors of W. From the list of all the neighbors, remove that color, because that color cannot be used for the neighbors of W. So this is how I'm going to update the color list in the process of extension. So whenever a vertex is colored, make that list of that vertex empty and remove that color from the list of all the neighbors of W. So this is how I will do the extension process. Okay. So now, if you are using K minus 1 colors in the extendable coloring, then a vertex W is called a color dominating vertex if W is adjacent to at least one vertex in each of the color classes here. If W is adjacent to at least one vertex in each of these color classes, then W is called a color dominating vertex. Because if W is a color dominating vertex, in the extension process, it cannot be given any of the colors 1, 2, etc., K minus 1. This is adjacent to a vertex with color 1, is adjacent to a vertex with color 2, and so on. Therefore, this W will enter the new color class VK. This W will enter the new color class VK in the extension process. So this is color dominating vertex. Okay. If you are using all the K colors in the extendable coloring, then I go for a near color dominating vertex. That is a vertex which is belonging to a color class, is adjacent to the one vertex in each of the remaining color classes. Okay. So in that case, that W will get that color J uniquely in the extension process, because this W is adjacent to at least one vertex here except Vj. Okay, except Vj. That means J is the only color that can be assigned to W. So this is how these two observations are useful in the extension process. So to check whether something is a color dominating vertex or near color dominating vertex, that has to be colored successively. Okay. Fine. Let me take this example. I have taken a cycle of length 6 and alternate edges I have put a K4. I have taken a cycle of length 6 at alternate edges I have put a K4. I denote it by the symbol C6 K4. I have given a partial coloring for this graph. This is given 4, 2, 4, 4, 3. A partial coloring is given. Can we extend it? Okay. Can we extend it to a whole coloring? First, let us see whether there is this vertex. Let us look at the vertex V2. Oh, let us look at the vertex V2. It's a color dominating vertex. It is adjacent to a vertex with color 1. It's adjacent to a vertex with color 4. Adjacent to a vertex with color 2. So I have to give color 3 to V2. Okay. So once I have given color 3 to this vertex, I can fix the color of this. It's adjacent to 3, 4, 1. So this will get 2. So this will get 3, this will get 2. So this is what I am explaining here. So this is my original coloring. V6 is a color near color dominating vertex, and that receives the color 2. So my C1 becomes in V2, V6 is entering. Okay. In V2, V6 is entering. Then V11 gets a color 1. So V11 enters the color class 1. I continue this process. And C6 gives the final coloring of the graph G. It's a unique extension of G. Therefore, this is a Sudoku coloring. So the ordering of the uncolored vertices, the ordering of the uncolored vertices is like this. First vertex is colored is V6, the next vertex is V11, and so on. This is how you solve a Sudoku puzzle. Okay? How do you solve a Sudoku puzzle? You have to put some entry, then which entry next, which entry next. Exactly the same thing I am doing. Okay, exactly the same thing. So this is a unique extension, unique extension. Therefore, this is a Sudoku coloring. This partial coloring is a Sudoku coloring, and has a unique extension given here. Okay. See, these observations are very useful. If you have a graph with, see, first of all, I will close chromatic number 2 case. It is a trivial situation. The chromatic number is 2. Your connected graph always, so bipartite graph. So if you give color to one vertex, that's it. Everything is uniquely determined. Okay? If you have a bipartite graph, a connected bipartite graph, color one vertex with color 1, then it's uniquely extendable to a 2 coloring of the whole graph. Just keep traveling or give 2 1 alternate. Okay. Therefore, the Sudoku number of a connected bipartite graph is 1. It's if and only if. The Sudoku number of a connected graph is 1, if and only if it is a bipartite graph. So hereafter, I shall assume that the chromatic number is at least 3. Okay? The chromatic number is at least 3. Okay. So if you have a graph with chromatic number at least 3, and if you have an extendable coloring, and there is a pendant uncolored vertex, then it is not a Sudoku coloring. It's obvious, because that pendant vertex will have 2 choices of colors, at least 2 choices, because chromatic number is 3. It has only 1 colored neighbor. Therefore, the pendant vertex will have more than 1 choice, and therefore it is not a Sudoku coloring. Again, if you have a graph with chromatic number 3, if there's a pair of adjacent vertices uncolored, and both of them have degree at most k minus 1, then also it's not a Sudoku coloring. These observations help us to determine the Sudoku number of a graph later. Here again, the same argument. For both the vertices, I can have 2 choices of colors. Okay? Because I have k colors and degree is less than or equal to k minus 1. So its colored neighbors will be at most k minus 2. The colored neighbors will be at most k minus 2. Therefore, at least two colors will be there in that list. So the extension is not going to be unique. So with this I have already stated. Okay. If a graph is uniquely colorable, then the Sudoku number is t minus 1. It's fairly obvious. Suppose you have uniquely colorable graph with chromatic number t. That means the graph admits only one K coloring. You take a K coloring V1, V2, Vk. Choose one vertex from each of the color classes except one of the color class. You take T color classes from T minus 1 color classes, choose one vertex and give that color. That's my partial coloring. Okay. For T minus 1 color classes, you choose one vertex and give that coloring. That's a partial coloring. Now, because the graph is uniquely colorable, this partial coloring has a unique extension to the whole graph. And therefore, the Sudoku number is at most t minus 1. It cannot be less than t minus 1. If it is less than, then again, two color classes are going to be created. Uniqueness is lost. Okay. So for a uniquely colorable graph, the Sudoku number is t minus 1. In particular, for a complete t-parted graph, the Sudoku number is t minus 1. Because the complete t-parted graph is uniquely colorable with chromatic number t. Okay. So this is one family of graphs for which I have the Sudoku number. Okay. And for a cycle, it is 1 if it's even. For odd, it is n plus 1 by 2. This part is obvious because when n is even, it's bipartite. So the Sudoku number is 1. When n is odd, it is n plus 1 by 2. Because you can take the usual coloring of an odd cycle where exactly one vertex gets the color 3. Okay, where exactly one vertex you give 1 to 1 to 1 to alternatively. For last vertex, you give color 3. Now you choose that 1 to 1 to alternatively. That will be a uniquely extendable coloring. So it will be n plus 1 by 2. The proof is fairly elementary. Okay. So for the cycle, it is this much. Okay. Now I am generalizing this construction. This construction. Namely, I have taken a graph and I have copies of K4 and putting them in a nice way. So what I'm doing is, you take m simple graphs, all of them having a particular subgraph as an induced subgraph. So G1 has a copy of H, G2 has a copy of H, Gm has a copy of H. Now you put all these together in such a way that copy of H is present as an induced subgraph. That I call amalgamation. You are amalgamating m graphs by identifying the copy of H in all of them. Okay, the copy of H in all of them. Okay. So what I have done here, for example, suppose you take m copies of K2, that is each G is a K2, and your H is K1. Your H is K1. So what is this amalgamated graph? So m copies of K2. How do we do that? How do you do this here? Okay. So you have now. It doesn't work for me. Okay, it's obvious. Doesn't matter. You have m copies of K2, and you are going to amalgamate everything with a K1. So you get a star. Whereas if you take m copies of K3, amalgamate with K1, you'll get the usual friendship graph. Okay, so the generalizes so many things because I'm able to get the chromatic, the Sudoku number of this amalgamated graph in terms of the base graphs, at least for some special cases. That is, if you take m copies of Kn and R is strictly less than n and amalgamate them along this Kr, then the Sudoku number is this much. With this, first I was trying this problem. I was only trying this friendship graph problem. Okay. Then I thought it's better to put it in a more general format. Okay. Because for the friendship graph, this R is 1 and N is 3. Okay. So I get this. So for this amalgamation of m copies of Kn over a copy of Kr, the Sudoku number is given by this formula. Okay, so for a friendship graph, the Sudoku number is m. Then you've got some simple examples. If you take a cycle with a path attached to it, tadpole graph, a cycle with a path attached to it. If the cycle is even, it's bipartite, so answer is 1. Otherwise, it is very similar to n plus 1 by 2 case. On the cycle n plus 1 by 2, on the path you put alternate vertices. So this is this. Similarly, for the complete graph with a tail, a complete graph with a path attached to it, the Sudoku number is n plus m minus 3. Okay. So this is what I have put in the earlier example. You take an even cycle, at alternate edges, you put a copy of Km. At alternate edges, you put a copy of Km. So I denote this by this graph C2n Km. Okay. Then for this graph, the Sudoku number is n times m minus 2. So in my original example was n equal to 3, C6 and a K4. Oh. Yeah, this is C6 over K4. So here I'm replacing this by any even cycle, and alternate edges you paste a complete graph. Okay, and what I have demonstrated earlier is that the Sudoku number is 7. Okay, I have colored 6 vertices. The Sudoku number is 6. Okay. The original partial coloring is for 6 vertices, and the extension is taking place. So I have generalized this in general that it is n times m minus 2. Okay. That is 3 times 2. Okay. So there are some families of graphs for which you have determined the Sudoku number. Okay. Okay. I have constructed a family of graphs with Sudoku number 2. Several families of graphs with Sudoku number 2, fan graph, and then in general, you start from a maximal outer planar graph and keep adding vertices and join it to the outside external face 2 vertices and to get us families of graph like this. For all these graph, Sudoku number is 2. Because we were trying to characterize graphs with Sudoku number 2. So the Sudoku number lies between 1 and n minus 1. It is 1 if and only if it is bipartite. It is n minus 1 if and only if it is complete graph Kn. Okay, the Sudoku number is n minus 1 if and only if it is the complete graph Kn. Because if you can't omit two uncolored vertices in the complete graph, uniqueness gets lost. Okay, so the most natural problem is which graphs have Sudoku number 2 and which of them have Sudoku number n minus 2. So I have got families of graphs with Sudoku number 2. And for the wheel, it happens to be very similar to cycle n plus 1 by 2. Okay. So the complete graph for a connected graph of order n, the Sudoku number is n minus 1 if and only if the graph is complete. Okay. This proof is very easy, both ways. Fine. Because if the Sudoku number is n minus 1, only one uncolored vertex is there. Okay. And it's uniquely extendable, and it happens if and only if the graph is complete. Okay. In general, given a graph with chromatic number at least 3, the question of whether a given partial coloring can be extended to a whole graph is an NP complete problem. Okay. So it's algorithmically it is not easy. But for disconnected graph, the problem is really complicated. I'll tell you why it is complicated. Suppose I take a disconnected graph. Say one graph. I am not used to this. Can someone help? Huh? Or finger only? Oh, I see. Okay. So this is E1. Okay. I take a disconnected graph with two components. Assume that this has chromatic number 5, and this is simply a complete bipartite graph. Okay. Now I want to find the Sudoku number of this graph. See, for bipartite graph, the Sudoku number is 1. However, when you think of the whole disconnected graph, I have 5 colors available with me. And therefore, even for the complete bipartite graph, if I give one vertex color 1, it's not uniquely extendable now because I have 5 colors with me. I can distribute them in any way. So for a disconnected graph, I have to look at a new parameter, namely Sn G colon K, where K is bigger than or equal to the chromatic number. What is the minimum number of vertices to be colored with k colors, where k can be larger than the chromatic number. And look at that number, and that will play a role here. So for example, for this graph, the Sudoku number will be Sudoku number of G1 plus Sn of this graph, comma 5. Sn of this graph, comma 5. For the complete bipartite graph with 5 colors, what's the minimum number of vertices to be colored? So the extension is unique. Let us look at, we have a V1, okay, and there's a V2. Assume that R and S are more than 5. So I have vertices here and vertices here. I assume that V1 is a smaller part. This is smaller. Okay. V1 is a smaller part. Now I have to use 5 colors and get a Sudoku coloring for this complete bipartite graph. Okay. I use 5 colors, get a Sudoku coloring for the complete bipartite graph. Suppose you give colors to all the vertices in the one part with colors 1, 2, 3, 4. Take all the vertices in one part, color them with 1, 2, 3, 4. Use all of them. Then you see that for this part, extension is unique. You have to give only color 5. Okay. Can you manage with less than this smart V1 and still get a Sudoku coloring? You have 5 colors with you. Can you get a subset S with cardinality less than this and still have a Sudoku coloring? If the cardinality is less than this, there is definitely an uncolored vertex in here as well as an uncolored vertex here, which will make the extension not unique. Because here you are going to use one color, then the uncolored vertex here will have more than one choice. Because I have 5 colors with me. Okay. So therefore, you see that this parameter seems to be more difficult to study than the classical parameter. That is, study the parameter Sn Gk, where chi of G equal to K is much larger than chi of G. The problem initially looks artificial. Why should I consider coloring with more than chi colors? Okay, it looks artificial, but for disconnected graph, that is what is happening. Without that parameter, it's not possible for me to study. So you see, I find this problem to be really difficult. Determining the Sudoku number of disconnected graphs seems to be really a difficult, challenging problem. Okay, because I have to look at the components and take the maximum chromatic number of among the components. That number of colors I have to use everywhere and see how that number determine this number for each of the components separately and then add up. Okay, so studying Sudoku number of disconnected graphs is a very interesting, challenging problem. Okay. Other fundamental problems include, do you remove this? Okay. Erase. Add. Okay. Fine. Now I am more familiar with this. Okay. So my fundamental problem to when? N minus 2 when? Fundamental basic problem. And there are graphs for which this is chi minus 1. For example, any uniquely colorable graph. What I said, any uniquely colorable graph. So is that depend only if? I am not sure. The Sudoku number is chi minus 1 if and only if what? I don't know. I also have examples of graphs for which the Sudoku number is chi. Simplest is C5. The cycle C5 has chromatic number 3 and Sudoku number 3, ceiling n plus 1 by 2. For the cycle, ceiling n plus 1 by 2 is the Sudoku number. So here's a graph where the Sudoku number is exactly equal to chi. So again, I want when it is if and only if. These graphs have to be characterized. For which graphs Sudoku number is exactly 2, n minus 2, chi g minus 1, and chi g. Okay. Fine. Then another interesting graph which you have to look at is Kn Cartesian Kn. It is actually subgraph of the standard Sudoku graph. Kn, if you take n equal to 9, this is a subgraph of the Sudoku graph is K9, Cartesian K9 with 9 more commutative graph put on them. So find the Sudoku number of this graph. So what is the Sudoku number of Kn, or in general Kn, Cartesian Km, make Nm arbitrary. So what is the Sudoku number of this graph? And people have made a conjecture that it is something like n squared by 2. Now n squared by so 9, 36. I'm not exactly sure. I'll check. It's better not to give a wrong. I'll check it and let you know. There is a conjecture that this number is very near to n squared by 4, I think. Okay. So this is the conjecture. The Sudoku number of Kn, Cartesian Kn is n squared by 4. See, why I am interested in this is, for the standard Sudoku puzzle, it is conjecture that it is 17. Okay, its conjecture is 17. So if you remove that sub 9 copies of K9, it comes to nearly 21. 81 by 4. Okay. So it looks reasonable. For the standard thing, it is 17. So if you remove some of the computer graphs, so I have more freedom of doing things. So this is an interesting conjecture that for Kn, Cartesian Kn, it is n squared by 4. Okay, fine. Here is. Okay. Okay. Another interesting thing is, which I want to work with Professor Baga. See, Professor Baga has written a book on line graphs and line digraphs. And there's one chapter in his book dealing with coloring of line graphs. Okay. There's one chapter on his book on coloring of line graphs. So I want to look at how this Sudoku number behaves with respect to edge coloring. Take an edge coloring of a graph, do the same thing. take a partial edge coloring and see when it can be extended to a unique chi-dash coloring of the graph G, and I call that as edge Sudoku number. I denote it by the symbol ESN. Or simply Sudoku number of the line graph. Okay. So what is the edge Sudoku number of graphs? It's completely unexplored, but maybe perhaps more interesting, because edge coloring, behaves completely differently from vertex coloring. The Weissing's theorem says it is either maximum degree or maximum degree plus 1. Okay. Therefore, you have to look at graphs of class 1 and class 2 separately. This graphs with index delta and index delta plus 1, and see what is the smallest number of edges to be colored, so that from that extension is unique. Okay. And a similar thing completely is open for total coloring. For total coloring, it's up to delta plus 2, where vertices and edges are colored. The total chromatic number is at most delta plus 2. It's still an unsolved problem. The total coloring conjecture still remains unsolved. So now, if I allow both vertices and edges to be colored, okay, both vertices and edges to be colored, and again go for a partial coloring and see when it is uniquely extendable, and call that order as the total Sudoku number of the graph G. Okay. These are problems for a full doctoral thesis. Okay. It's not just you can do it in one line. It's a full theory to be developed. This can become a topic for a doctoral thesis of a student, studying the edge Sudoku number and the total Sudoku number of a graph. Okay, fine. So this is the place where they have that 16 computer-based theorem. There is no Sudoku puzzle with 16. Some work has taken place on this concept, but not much. Okay. It's completely an area to be explored in full, especially for edge and total coloring. For vertex coloring, some work has been done, but I thought even for an extendable coloring, we can do that. Don't worry about uniquely extendable. Simply take an extendable coloring and say what is the smallest order of a subgraph where an extendable coloring is permissible, and you can put a new parameter. Okay. The extension is interesting practically, because when you apply graph coloring to problems like scheduling problem or things, the knowledge of chromatic number alone is not sufficient. You need actually a K coloring to give a scheduling problem solution. You actually need a K coloring. So this extendable coloring gives you a tool for the construction of a K coloring. Okay, it's a nice tool for constructing a K coloring of a given graph. Okay. Fine. Some progress has been done for n-2 case, but not much. I recently came across a few scattered results giving examples of graphs with Sudoku number n-2. But if and only if it's really a nice problem to try. Okay. Fine. I started with a happy note as to how the conference gave a new collaboration. I'll again end with another happy note. The file open. You open the next file, the 5 author paper. because Katana may perhaps say that that record is broken because he mentioned in one of the conferences. I'll come to that. Yes. So we have recently published a paper entitled Total Monophonic Number of a Graph in 2022. It's available online. There are 5 authors for this paper. And what is important is the 5 authors are such that the ith author is the research supervisor of the I+1th author. Okay. The ith author is the research supervisor of the I+1th author. So Santakumaran is my research student. Titus is a student of Santakumaran. Ganeshmurthy is a student of Titus, and Murugan is a student of Ganeshmurthy. So I have a paper with mathematicians of 5 consecutive academic generations. You have an example of similar to that? You told in one of the conferences. Am I correct? Mr. Katana, you have similar thing in you stated. Is it 5 or more than 5? Your example. Anyhow, I have asked the last student, he has just submitted the thesis last week. I asked him when you are going to take the next, when you are going to take a research scholar, because the chain is active. As on today, all the members of the chain are actively involved in research. So I am expecting that this fellow will take a research scholar here, and possibly in another 2 years, I can make 5 into 6. Let us say there is going to happen. I don't know. It's my plan. And I have so many other paths of length 5 like this, but those chains unfortunately are not active. The in-between members are not all of them are active, because I wanted to have at least one more chain where all the descendants are women students. Here all of them are men students. But I have a chain where the descendants are women students, but the chain is not very active as on today. I'm trying to activate it. Okay, I'm trying to activate it. And Professor Katana said Armuga means 6 faces. And here Kumaran is another name for the same god. Murugan is another name for the same god. Okay, so these 3 names represent the same god. And this is again elder brother of this god. Some mythology is also sitting there. So this I wanted to share with you, just to say that we are keeping things going in a nice way. That's it. So thank you very much. So questions are welcome. Yes, there's someone is, people are asking questions, let us see. Yeah.
Thank you for the exciting and very clear talk. Question. Oh. Thank you. Can you hear now? Okay.
Yeah.
Thank you for the exciting and very clear talk. Questions?
It's not. You can come here.
I'm able to.
Come here.
My question is, can we determine?
If we come here so that others can see and listen to him.
Hello. Now it is working. My question is, can we determine any relationship between Sudoku number and crossing number? Because there is a relation has been determined between crossing and chromatic number.
Okay. So how does crossing number play a role in this problem?
Yeah.
I don't know. I don't think it is going to be of any significance for me, because I'm only interested in the order of a smallest subgraph. Okay. I don't worry whether it crosses or not. Perhaps it may not have any implication, most probably.
Okay, sir. Thank you.
Any other question? Yeah.
Hello. Sir, let's consider a graph with large number of vertices, and chromatic number of this graph is let's suppose 10.
Okay.
And now it's obvious that color we can have a 15 coloring also for this particular graph. And suppose for that that we have a for using 15 colors, I can have a Sudoku. I can have a Sudoku coloring, means that
Okay.
particular using 15 colors, that there exists a Sudoku coloring. So can we say about that using a 14 color Sudoku coloring always be exist, or lesser than that always be Sudoku coloring exist?
Nice question is, can you repeat the question?
So
come here. It's not clear as to what he's trying to say.
so let's suppose a chromatic number is 15.
So chromatic number is
Sorry,
15,
chromatic number is 10.
10. Okay.
Okay, that graph is always be 15 colorable.
Okay.
Large number of vertices I have considered, that's why.
So chromatic number is
10
10.
and 15 is the colorable graph. 15 colorable graph is also.
Okay.
Okay. So, and also I have somehow I found that that is a for using a 15 colors, that is a Sudoku coloring exists.
Right.
Okay.
That's the SNGK, what I have put.
Yes.
SNGK. Okay.
Okay. So what about not that coloring is exists? That that is minimum or not? I don't know about it.
Okay.
Okay. So now question is, the graph is also 14 colorable.
Okay.
So what about Sudoku coloring? Always be exist or not?
It always exists, no problem.
Always be exist.
Always exists.
That Sudoku, that minimum number I don't know. Na,
that finding the minimum number is a problem.
Okay.
The parameter is defined for all graphs. Okay.
Okay.
For all graphs, SN, G, K, where K is any number bigger than Kg.
Okay. So what about, like, suppose I'm considered the 16 colors.
Okay.
So 16 colors, there always be exist?
No, you'll end up with a maximum, right?
Yes.
You can go up to n, no problem.
No, I'm not
I
going
can
to
go
be.
up to
I'm not going to the that. I have considered a graph with large number of vertices.
Okay.
I'm not reaching to that n.
Okay.
I'm just reaching to the number of the chromatic number. Like suppose the graph is colorable.
Right.
That is higher than obviously chromatic number. Okay, so around this one, that particular number I have considered that k, then k plus 1 for the k using the k colors I can have a Sudoku coloring.
Yeah.
So what about k plus 1 always be exist? What about k minus 1 for that Sudoku coloring exist? That is my question.
K minus 1.
Yes.
See, you start with the smallest k.
Yeah.
The chromatic number itself. Okay. If you want to, whenever a vertex is colorable, instead of giving a old color, you give a new color.
Old color and new color. But the list
So
is there.
I'll go to k plus 1 now. In the extension process, I don't give the old color, but give a new color.
Okay.
Until you reach the number that you want. Then afterwards, I'll do the extension process in the usual way.
Okay.
So that's not a very big problem.
This question is like, suppose we have a k chromatic graph, small. We want to make a bigger graph.
Yeah.
Which is having Sudoku color.
Yes.
So
because in the process of extension,
chromatic number plus something.
Yes.
K will change.
Something can we have?
K will change.
Okay.
What you want is K. Yeah.
Okay. Thank you.
Okay. Is it clear?
Okay. Any other short question?
Sir, in the disconnected case, if each component is having equal chromatic number,
Ah.
then the problem is simple, it seems. It's
That should be
maximum.
Sum of the Sudoku numbers. of
Some
each
or
component.
maximum, sir?
Huh?
Is it some or maximum of
No, I
Sudoku
have
number?
to get a coloring
Yes,
such that it is uniquely extendable. For each component, the extension is to be done.
yes. But if we take the maximum of Sudoku number of each component,
Okay,
then it will work, right, sir?
that is enough.
That will be enough because I think so. I'm
Ah,
not sure.
No, I don't think it will be the maximum.
Sir, if you
all-
take G1 and G2, Sudoku number of, say, G1 is 5 and G2 is 6. If we are fixing 6 colors for G1, then that will be uniquely extendable. With 5 colors itself, I can insist that the extension is unique.
Okay,
So with 6 colors, definitely I can do that. So it is not some, it will be maximum. I'm not sure, sir, whether I got the concept correctly.
okay.
Yeah.
Some are maximum. Okay.
Okay,
I have
we'll
to
discuss
think about-
later, sir.
We
It's
have
okay.
to think about.
Yeah, we will discuss later.
Yeah. Because you have not started
Hello.
the work on disconnected graphs.
Yeah. Hello, sir.
Yeah.
Sir, suppose G is a graph with vertex chromatic number 5. Okay. And suppose G has a proper subgraph H with chromatic number 5.
Okay.
Then in this case, is it that Sudoku number is same as chromatic number?
Sudoku number and chromatic number have nothing to do with each other.
Okay.
Even for a standard Sudoku puzzle, chromatic number is only 9, but Sudoku number is 17.
Okay.
Okay.
Okay. So in some case, it may be same, no? Means
Huh?
if you have a proper
So
subgraph.
only a few small class of graphs you have,
Okay.
they are equal.
Okay. Okay. Yeah.
Okay.
Thank you.
Even for a cycle, it is n plus 1 by 2.
Okay.
Whereas chromatic number is only 3.
Yeah. 2 or 3. Yeah.
Okay.
Yeah. Thank you, sir.
Any more questions?
I think we can stop because otherwise other
No,
speaker
yeah.
is waiting.
Okay, then thank you again.
Thank you.
And I think you will.
So,
Uh-huh.
there is one question asked online. What is that?
Deal with separately.
Where Sudoku number is used? Sudoku number is useful. This is the question asked online.
Okay, that's what I told you. For a scheduling problem, we need actually the coloring of the graph. Just the knowledge of the chromatic number alone is not enough. We need an actual coloring of the graph. Then Sudoku number gives you a tool to get a coloring of a given graph. Okay, it gives
Thank
a
you, sir.
tool to get the coloring.
Thank you so much, sir.
Yeah.
Whenever we have a session by Professor Arugma, we have plenty of questions online and offline we have seen. So he made us to think and ask the question. Thank you, sir. Thank you so much, sir, for a wonderful session. Now, I would like to request Professor Katona to facilitate Professor Arumgam with the token of memento, please, sir. This way, sir. Thank you so much, sir. Thank you. So now we have a tea break, so we can proceed. And after
And so it's my pleasure to introduce the next speaker, Professor Chikova. Some of you might know her under a different name, Samanichova. The confusion is due to she married Fenyovchikov, and this changed her name. She studied at Shafarik University, and she finished her master degree. She got her master degree in 2002, so only 20 years ago. And the title of her thesis was Magické graphy. I don't think I have to translate it, although it is in Slovak language. And in 2006, she got the PhD degree. And she had really magic activity since then. I not anti-magic, although there are some papers under this title, magic and anti-magic graphs, and really very large number of papers for her age. It's about 130 papers, so it's really very large number, and the number of citations is above 1,000. So it's really remarkable. I think this is enough for the beginning. So, Professor Fenyovchikova, please.
Good morning. So good morning to everybody. I will try to be quick because I see that all of you are looking forward to have a tea. So I will try to be very quick. First of all, I would like to thank the organizers for inviting me here. I'm very happy to be here. This is my first visit to Delhi, and I enjoy my stay. During my talk, I would like to tell you something about some variation of anti-magic graphs. This is a common work with my co-authors, Mohamed Ali Ahmed, my colleague and friend Martin Bacha from Technical University in Košice, Bhaskar Babuji, Loganathan Shobana, and Peter and Teresa Kovažovci from Czech Republic. Today, I would like to tell you something, as I told, about anti-magic graphs. And when we speak about anti-magic graphs, then there is one very famous conjecture by Hartsfeld and Ringel, and they conjecture that every connected graph other than K2 is anti-magic. And another very famous conjecture in theory in label graph is a conjecture by Ringel and Kotzig, and they conjecture that every tree is graceful. During my talk, in the first part, I will try to show you some connection between these two concepts of anti-magic and graceful graphs. We will start with the definition of anti-magic labeling. Let me explain the definition on some small example. So what we have a graph, and we will assign numbers to the edges of these graphs. We will assign numbers from distinct numbers from 1 up to the number of edges. Like for this graph, it has 8 edges, so we will assign numbers from 1 up to 8 of these edges. For example, like that. I don't know whether you can see it, maybe it's too small. And now we will check the weight of the vertices. For example, for this vertex, its weight is equals to the sum of the labels of edges assigned to incident to this vertex. For example, this 11 we can get as the sum of number 2, number 8, and 1. Okay, so the weight, for example, for this vertex is a sum of numbers 8 plus 5 plus 6 plus 7, and we get 26. And what we require, we tried to find such an distribution of numbers to the edges of this graph that all the vertex weights are distinct. This definition was given by Hartzell and Ringel in 1990, and they also proved that some standard graphs like cycles, passes, stars, complete graphs, wheels, and complete bipartite graphs K2M are anti-magic. And you can find many results about this type of labeling proved by many different authors. A lot of results are known for regular graphs, and now it seems that every month you can find some new nice results about this topic. It's very, very popular. Hartzell and Ringel, they conjecture that every connected graph other than K2 is anti-magic. Trivially, K2 cannot be anti-magic because we have just one edge. We have to assign number 1 to this edge, and then the vertex weights of the ends, they must be 1. So we cannot distinguish these two vertices. But they conjecture that every graph except K2 is anti-magic. This conjecture is still open, and also open is the weaker conjecture that every tree except K2 is anti-magic. This conjecture was proved, it's proved for graphs with sufficiently large minimum degree. It was proved by Alon Kaplan and the other authors. But what is very interesting situation for when we study anti-magic graph is that if you will have a graph and you will try to find such an anti-magic assignment, then you will find such an assignment very quickly. So for a given graph, the problem of finding anti-magic labeling is not very complicated. If you compare your solution with your friends, you can find non-isomorphic labelings. So it seems that for a given graph to find a solution is very simple, but to prove it in general, it's very, very complicated. And we can find many different non-isomorphic labelings with this property. And this inspired other authors to find some, or to study some variations of such labelings. For example, when we not require just that the weights of the vertices are distinct, but we give additional property that the weights must, for the set of vertex weights must form some arithmetic sequence. Or another is way how we can extend this topic is that we will not label only the edges of a graph, but we will label also vertices and edges of a graph, or just vertices of a graph, or we can label, if we have a plane graph, also faces. And then another extension is that we will not check only the weights of the vertices, but we can check the weights of edges, faces, and variations of this one. So you can see that we have many, many different ways how we can extend this one. And in the last years, it's very popular also the local version of anti-magic labeling. And the problem of finding the corresponding local anti-magic chromatic index. Okay, so I will show you one extension or one variation of this anti-magic labeling. It's called vertex anti-magic total labeling. And what is the definition? So everything is hidden in the name. Vertex anti-magic total labeling is mean. Total means that we label, assign numbers to the vertices and edges of a graph. Yes, we have a cycle, we assign numbers to the vertices and edges of a graph. Vertex anti-magic. Vertex means that we will check the weights of vertices. Anti-magic means that all the weights must be distinct. And now, what is the weight of the vertex? For example, we have this vertex. So the weight of this vertex is the sum of the label assigned to this vertex plus the labels of the incident edges. So like for this vertex, it is 1 plus 14 plus 10, it's 25. I'm not sure that you can see it because the picture is too small. And then you will see all these vertices have distinct weights. You can see that not just that the set of vertex weights consists of form some arithmetic sequence. So we have some additional property, but in general, we just require that the weights are distinct. And we have a very nice result proved by Mirka Miller, Rudan Panalassi, and Joe Ryan, and they proved that every graph is vertex anti-magic total. they describe a very nice algorithm how to find such an assignment. And what is very beautiful on this algorithm is that it is possible to extend this algorithm also for another types of labelings. For example, when we have edge anti-magic total labeling. So what we do? We assign number to the edges and vertices of a graph. It means that we have a total labeling, and we will check the weights of the edges. And these weights must be distinct. Like for this one, yeah, weight of this edge is 8 because it is the sum of the labels assigned to the ends of this, yeah, edge 1 plus 10 to the ends of this, yeah, edge 1 plus 2 plus the label of the edge itself. And we require that these weights must be distinct. So in the original paper, Mirka Miller, Joe, and Udan, they prove that every graph is edge anti-magic total. Another way how we can extend the algorithm is, for example, for plane graphs. Here is one example. We assign numbers to the vertices of a graph and to the faces of this graph, and we will check the weights of the faces, and we can prove that we can find such an assignment always, just by modification of this algorithm. And it can be also applied for finding anti-magic labeling of digraphs. When I will have time at the end of my talk, I will also deal with digraphs. So here we just have a small example. So what we have, like we will check the weights for the vertices, like how we will get this weight 8 for this vertex. So it is the sum of the label assigned to the vertex plus the label assigned to the ingoing edge. So 7 plus 1 is 8. And such labeling is obtained just using modification of this algorithm. It's really, really nice algorithm, and we use it many times. Okay, and now I will tell you something about graceful labeling. So graceful labeling was defined by Alex Rosa, under the name beta valuation. So what we have in this case, we will assign numbers to the vertices of a graph. We assign numbers from 0 up to the number of edges, and we will check the induced labels for the edges, or we can say induced weights for the edges. These weights are defined as absolute value of difference of the end vertex labels. And what we require that every edge has distinct weight. Yeah. Alex Rosa, as I told, called this labeling or assignment as a beta valuation, and later it was renamed by Golom as a graceful labeling. And Alex Rosa, he proved that existence of graceful labeling of a given graph with skew edges is isomorphic to the cyclic decomposition of a complete graph with 2q plus 1 vertices. Cyclic decomposition of this graph into subgraphs isomorphic to the given graph G. Yes, so we have a practical application of this one. And let's check several properties of this graph, and let me explain this labeling on some example. So it is trivial that the induced edge labels must be numbers from 1 up to the number of edges, because as we assign numbers from 0 up to number of edges to the vertices, the maximal difference trivially is number of edges. So we have that the edge labels must be from 1 up to the number of edges. Here we have a small example. This graph has 8 edges, so we assign some numbers from 0 to 8 to the vertices. For example, when we will do it in this way, we can check the weights of the induced labels for the edges. For example, for this edge, 6 we get as a difference 8 minus 2. Or for this edge, 2 minus 0 is 2. So that's why this edge will have number 2. Yeah, so this labeling is a graceful labeling. And as I already told, Gerhard Rinkel and Alex Rosa, they conjectured that every tree is graceful. When I would like to tell you something about the connection between anti-magic and graceful labeling, there is already known some connection. But I have to introduce one special type of graceful labeling called alpha labeling. So alpha labeling is a special graceful labeling having some additional property. And this property is the following. There must exist some integers, say lambda. We call this integer as boundary value of the labeling, such that for every edge, the labels of the end vertices of this edge have such property that this number lambda is a number between these two labels. So what are the properties of alpha graphs? Trivially, alpha graph must be bipartite. And when we consider the edge that has induced label 1, then the number lambda, must be the smaller of the vertex labels that yields to this number 1. For example, here we have a graph with graceful labeling, but this labeling is not alpha labeling. Because, for example, check this edge. Here we have a number 1. Yeah, induced edge label is 1. So according to this property, boundary value must be free, but just check the second edge, this one. 3 is not number between 4 and 7. So this is not alpha labeling. But for this graph, for example, this labeling is alpha labeling. And now I will show you some connection between what is known about graceful labeling and anti-magic labeling. Martin Bacha and Christian Barrientos, they proved the following. If you have a tree with at least 3 vertices, and this tree admits alpha labeling, then this tree also admits such labeling that we assign numbers to the vertices of the graph, and we check the weights of the edges, and then the weights of the edges form arithmetic sequence with different one. So we can get from graceful labeling some edge anti-magic vertex labeling. And using a connection between edge anti-magic vertex labeling with difference one, we can obtain also some total labeling with difference according to this proposition with differences 0 and 2. So there exists a connection. And we also concentrated on another problem, whether there is some connection between these two types of labelings, and we asked for the following. Is it possible to find such anti-magic labeling of a graph that is induced by some graceful labeling? Okay, so we defined the concept of graceful anti-magic labeling. So let me recall the definition, what we really require. So our goal is to assign numbers from 0 to the number of edges to a graph, to the vertices of a graph. We require that this assignment is graceful labeling, and then we will check the properties of induced edge labeling, and this must be anti-magic. Yeah? So let me explain it with some example. We have this graph, we already know it. It is easy to see that this graph is graceful. Okay, so for gracefulness of this labeling, we have to check the differences of the absolute value of the end vertex labels. We see that the edges are, the induced edge labels consist of distinct numbers. So this labeling is graceful. And now we will check what are the induced vertex weights by this labeling, edge labeling. And like, yes, this 11 we will get as a sum 6 plus 2 plus 3. And we see that for this labeling, there are 2 vertices that have the same vertex weight. So this labeling is graceful, but not graceful anti-magic. But it is quite easy to find graceful anti-magic labeling. For example, this one, we prove that it is graceful, and then we will check the vertex weights, and we can see that this labeling is graceful anti-magic. Okay, and now what we get, some results for some standard graphs. So first I will tell you something about passes. Trivially, every graceful anti-magic graph must be graceful and must be anti-magic. And it was proved by Alex Rossa that every path with at least 2 vertices is graceful. And Hartzell and Rinkel proved that every path with at least 3 vertices is anti-magic. And what we have, we proved that every path with odd number of vertices is graceful anti-magic. So we have partial results for passes with odd number of vertices. And now what we have for even number of vertices in this path with even number of vertices. So it is easy to prove that if the number of vertices in a path is 2, 4, and 6, such labeling does not exist. For n equal to from 8, 10, 12, 14, and 16, we can find such graceful anti-magic labeling, but in general, for even n, we cannot find such an assignment. But we believe that such assignment exists, and we believe it because of the following result. Albrecht, Shiran, and Shiran proved that the number of alpha labelings of passes, this is just this special type of labeling, we have even more graceful labeling of passes, asymptotically grows at least as fast as 5 by 3 powered by n. So we have a lot of graceful labelings, and we believe that at least one of such labelings is also graceful anti-magic. So we have this conjecture. We were studied also we obtained results for stars. We proved that every star is graceful anti-magic. And we have result also for double stars. There is only one double star that is isomorphic to pass on 4 vertices that is not graceful anti-magic. Here we have one example of such a star. And we were also dealing with trees in general. So here you can see, in this table, you can see how many non-isomorphic trees on n vertices we have. So plenty of them. The question is how we can prove that all of them have such a labeling. And what we did, we proved that for trees up to 8 vertices, all but these 5 trees have such labeling. So the exceptions are isolated vertex, isolated edge, pass on 4 vertices, pass on 6 vertices, and this graph, this we call 3 on 6, but T6. Yeah, and we believe that there are no more exceptions. Yes, so we believe that all other trees have such a property. And again, here you can find such these labelings of the corresponding graphs. And what somehow supports our conjecture. Well, it is known result by Alfred and McKay that the number of graceful labeling on trees on n vertices grows very quickly with n. And it seems all our research indicates that at least one of them has the required property. So we have this conjecture that all trees except K1, K2, P4, P6, and T6 are graceful anti-magic. So you remember we have 2 conjectures. Every tree is anti-magic except K2, and every tree is graceful. Yeah, and we believe that there holds something more stronger, that except these 5 graphs, all graphs are graceful anti-magic. Yeah? So somehow I don't believe that this will be proved, because immediately if you will be able to prove this one, we will immediately obtain that every tree is graceful and every tree except K2 is anti-magic. But maybe, and sometimes a new point of view can help us to solve some old problems. Okay, we obtained also some results for cycles. we know it was proved by Alex Rosa that cycle is graceful if and only if the number of vertices is either divisible by 4 or is congruent 3 modulo 4. And Hartzels and Winkel, they proved that every cycle is anti-magic. We have partial answer for this problem for graceful anti-magic graphs. We proved that if the number of vertices is divisible, is congruent 3 modulo 4, then the graceful anti-magic labeling exists. And in the case when n is divisible by 4, we have positive results just for some small cases, but we again believe that it is possible to find such a labeling for any even cycle, not even yet, n divisible by 4, but we are not able to find some generalization for this labeling. Okay. Now I will tell you some results for, previous results were about sparse graphs, and now we will speak about dense graphs. So what we can say about complete graphs, the situation is very simple because what we know, complete graph is graceful if and only if number of vertices is at most 4, is anti-magic if n is at least 3, so we have only 2 candidates. Yes, so the situation was very simple, and we proved that complete graph is graceful anti-magic if and only if it is graph K-free. And then we were dealing also, we characterized the situation when we have a graph, complete graph, and we delete either 1 edge, 2 edges, or 3 edges. So we have a characterization of this problem, and what we get. So every graph, the complete graph Kn without 1 edge is graceful anti-magic if and only if n is 3, 4, and 5. If we delete 2 edges, okay, so what we can either delete 2 K2s, or we can delete edges that form a pass. And in all cases, when n is 4, 5, and 6, we find a positive result. So this is again if and only if. And here we have a situation when when we delete 3 edges. Again, what we can do, if we delete a star, then we have that is if and only if n is 4, 5, and 6. If we delete 3 isolated edges, then n can be only 6. When we delete a triangle, then n must be 4 or 6. When we delete a pass on 4 vertices, n is either 5 or 6. And when we delete the isolated edge and pass on 3 vertices, then n can be only 5 or 6. So yeah, you can find here all these results. We have also some results, not characterization for complete bipartite graphs. We solved the case when the cardinalities are the same, and we have some partial results for the case when the partite sides, the cardinality, one is even and the second one is congruent to modulo 4. And now I would like to present some open problems. So what we know, as I told you, we found 6 connected graphs with at least 2 vertices. They are K2, pass on 4 vertices, K4, K5 minus triangle, pass on 6 vertices, and 3 that we call or denote as T6. These graphs are graceful, but not graceful anti-magic. And the question is, are there other graphs that have this property? We don't know. Yeah. Another question is the following. Yeah, we know that these 6 graphs, they are not graceful. Yeah, so when graceful anti-magic. So, but we can ask for a local version of this problem. So we will not require that all vertices will have distinct weights, but we just require that the adjacent vertices will have distinct weights. And this leads to the concept of local graceful local anti-magic labeling, and we have these exceptions here. So for these graphs, we cannot find graceful local antimagic labeling only for K2 and K4. K2 is trivial because K2 is neither local antimagic, and K4. And for the other graphs, we can find graceful local antimagic labeling. And the correct question is, are there some other graphs, or K2 and K4 are the only exceptions? We don't know. And of course, then we can ask, because every local antimagic labeling is inducing a proper coloring, proper vertex coloring. So we can ask for the corresponding graph invariant called local antimagic chromatic number. Yeah, what is this parameter? So we have this problem. Okay, I'm checking the time. I don't know whether I have time, or if you would like, I can finish. I prepared something for diagrams, but if you would like to have a tea break, so I can finish. So yeah, shall I continue, or okay? So now I would like to tell you something about antimagic labeling of digraphs. I will start with some definitions about antimagic labeling. So first definition is by Hefes, Mütze, and Schwarz. And what we have. So according to their definition of antimagic labeling of a digraph, what we will do? We will assign numbers to the arcs of a graph, numbers from 1 up to the number of arcs. For example, we will do it in this way. Yeah, and now we will check the weights of the vertices. We again have to define what is the weight of the vertex. So for example, for this vertex, the weight is defined as the label of the ingoing edge, 6, minus the label of the outgoing edge. So 6 minus 1 is 5. Yeah, for this vertex, yeah, we have 1 ingoing edge, so it will be +1, and 2 outgoing edge, +1, -2, -4. So for this edge, vertex, sorry, it is -5. For the other vertex, 4 ingoing edge, -3 outgoing edge, so it is 1. And so on. We will check the weights of all vertices. And if the vertex weights are all distinct, then according to their definition, we have antimagic labeling of the digraph. And what they prove, okay, so they call that the digraph is antimagic if it admits an antimagic labeling. And they say that an orientation D of a graph G is an antimagic orientation if the digraph D is antimagic. And what they prove that every graph whose underlying undirected graph is dense is antimagic. And they also prove that almost every undirected D-regular graph admits an orientation which is antimagic. Yeah, so we have one definition for antimagic evaluation of digraphs. But we can find also another definition of antimagic labeling. This one is given by Marimuthu Rajadurga and Durga Devi. And they define a concept of vertex in antimagic total labeling. So again, what we have here, total means that we assign numbers to the vertices and arcs of this graph, for example, like that one. And we will here in antimagic means or vertex and in antimagic vertex means that we will check the weights of the vertices, and in antimagic means that we will check how it is. This explains how the weight of a vertex is defined. In antimagic means that, for example, for this vertex, its weight will be the label of the vertex itself plus the label of ingoing edge. So this is 7 because we have 1 plus 6 is 7. For this vertex, yeah, we have only one ingoing edge. So 7 plus 2 will be 9. And also for the other vertices, one ingoing edge, 9 plus vertex level 3 is 12, and so on. And if we have, yeah, if all vertices have distinct weights, then such labeling is called vertex in anti-magic total labeling. Analogously, we can define vertex out anti-magic labeling total. It was proved by Dalibor Fronček, Petr Kovář, and Tereza Kovářová that all digraphs allow vertex in anti-magic total labeling and also vertex out anti-magic total labeling, with also this additional property that super, it means that we use the smallest numbers for labeling of vertices. And their proof is based on the algorithm of Mirka Miller, Joe Ryan, and Woodham Panalasi. Let me very briefly explain you how this algorithm works, because it's very nice. So consider that we have a digraph. I will show you how this algorithm works for in anti-magic, vertex in anti-magic case. So for this case, we do not care about the structure. What is for us only important is if we have a set of vertices, which arcs are going to the vertex. It is not important what is going out, because we don't need to care. If you would like to have a super case, so we will keep the numbers, smallest numbers from 1 up to 4 for later for labeling vertices. We will start with labeling of arcs. And the first step is distribute the next consecutive number starting from 5 arbitrarily to the arcs, as you like. And we will check the partial weights of the vertices. Like for this one, for example, it is 5 plus 6 is 11. Yeah, this one is 7, 8 plus 11 is 19, and also for this vertex is 19. It doesn't matter that we have some vertices that have partial weights the same. And now the trick is, it's very simple. It's really nice. What we will do, now we will assign numbers to the vertices. It's easy, yeah? Look, it's very tricky. The smallest vertex label we assign to the vertex with the smallest partial weight. Then the total weight will be 7 plus 1, 8. Then the next smallest unused vertex label we assign to the vertex with the second smallest partial weight. So we have total weight will be 2 plus 11 is 13. And then the next smallest vertex label 3, we will assign to the next smallest partial, the vertex with the next smallest partial weight. And here we have two options. Yeah, so you can decide. So for example, we will assign number 3 here. The total weight of this vertex will be 22, and we will continue. Very, very nice algorithm. Yeah, it's exactly just modification of the algorithm proved by Mirka Miller. We have this result. Of course, for out vertex out anti-magicness, we will do the same. Just we will check we will just control the out partial weights. Okay, and we have graph. They proved that all graphs are vertex in anti-magic total. All graphs are vertex out anti-magic total. And now we can ask whether there exists a labeling such that it is at the same time vertex in anti-magic and vertex out anti-magic. So again, we have a concept of labeling that has some like more properties, like graceful anti-magic. It was graceful and also anti-magic. Here we have this topic. I like labeling having more like properties. So such a labeling we call vertex in out anti-magic total labeling. And we were dealing with this concept with Martin Bacha, Petr Kovář, and Tereza Kovářová. So let me recall or explain you the definition. I will also show you the example. So what we will do, we will assign numbers to the vertices and arcs of a digraph from 1 up to the number of vertices plus number of arcs. And we require that the vertex in weights and vertex out weights must be distinct. Yeah, so, and if you use the smallest possible numbers for labeling vertices, then such labeling is called super. So let me show you an example. Finally, we have a bigger example, so maybe you will see it more clearly. Consider such distribution of numbers, and we will check first in weights. For example, for this vertex, the in weight is 3 plus the label of the in weight edge, so 10. And for this vertex, it's 5 plus 8, so together 13. And we can do it step by step, and we will check that all vertex invades are distinct. And now we will check whether this labeling also has a property that all outweights are distinct. So, for example, for this vertex, what is its not nice, not good color for this projector. So it's 11 because it is free, plus the label of outgoing edge is 8. Yeah, and we can check all the outweights. Yeah, so we see that invades are all distinct, outweights are all distinct. Of course, it can happen that some invades and outweights are the same. For example, here we have 13 and also 13, but it's not a problem. It could be interesting also to ask whether we can find such assignment that all these sites are distinct. Yeah, but at the beginning, we just solved with this problem. And here are few observations for this type of labeling. So what is like trivial observation? The sum of all vertex invades must be the same as the sum of all vertex outweights. Why? Because every arc it contributes once to every in vertex weight and out vertex weight, and the same is for the vertex label. As I told, in general, the sets consisting of invades and outweights, they can intersect. Yeah, and what we find is that it seems that there are only two digraphs. The first one is a digraph consisting of two vertices and opposite arcs, joining by opposite arcs. And the second digraph is the digraph on three vertices. So we have two vertices joined by opposite arcs and one vertex joined by a slope. It seems that there are only these two graphs that do not have super vertex in-out anti-magic vertex labeling, but these two graphs have non-super case. And so here is the labeling. Okay, so here you can also see the invades and outweights. And what we, according to this observation and our results, what we have, what we conjecture that all digraphs allow vertex in-out anti-magic total labeling. And for the super case, we believe that only these two small cases are the exceptions, that also for the other cases we can find such an assignment. And what we proved, we have some results for dense digraphs. So we proved that if the minimum degree is the maximum of the smallest in degree and smallest out degree of the digraph. So if the minimum minimum degree of the digraph is sufficiently large, then D is super vertex in-out anti-magic total. We have also some results for sparse graphs. I will be very quickly because I see that everybody would like to have a T. And we have also some results for regular graphs, and we have some results when we add one vertex to this graph. But I think that I will finish my talk now. Thank you for your attention.
Thank you for the interesting talk. Questions? Oh. Wait for the microphone.
There was a characterization for graceful anti-magic.
Just for dense graphs.
Sorry, ma'am.
For dense graphs, not for all of them.
Yes, for particular graphs you have mentioned. So is there any characterization for anti-magic graphs like that?
There is conjecture, yeah, like conjecture by Hartzell and Riegel, but every graph it's at K2 is anti-magic. When you will prove it, you will be very famous.
At least for particular graph, is there, does that exist, ma'am? Like a graph is
Yes,
anti-magic if and only if so and so?
Yeah.
Does it exist?
There are, you know, there are proofs that all regular graphs are anti-magic. Yeah, you can find such results.
Okay, ma'am. Is there any real life application for this graceful anti-magic?
For what?
Is there any applications?
No, just the beauty of the, as you told yesterday. I was accepting the same question. Thank you for your answer yesterday.
Yeah, hello. So I have a question, something which is related to this. So there is something called edge weight induced vertex coloring. They have. So here you have a bijection to the. So instead of bijection, if we allow repeated labels, then I think the number of labels becomes much lesser, right?
Yes.
It's even if so even if you impose the condition that the resulting coloring must be proper, so they have some results like that. Luigi Adario Berri.
Maybe yes, I don't know. Yeah.
Okay. But it's very interesting that you have to. The number of colors get much that I think they have for 16 and 5. So instead of bijection, if you just allow for repeated labelings, the number of colors becomes much less. So I'm just seeing like if there is any connection or like what is the reason behind that kind of thing. It'd be very interesting to.
More questions? Hold on, I think you will get a momentum.
Thank you. Thank you very much.
I thank Chairperson Katona sir, invited speaker Arumugam sir, and invited talk speaker Andrea ma'am for their knowledgeable talk. Now we'll have a 15 minutes short break. Please be here in another 15 minutes. That will be 12:15. So we'll start the next session soon after the break.
Hello.
Completed his MSc in 1920 from University of Kashmir, and he went on to do his MPhil and PhD from Aligarh Muslim University. He was also appointed as the professor in Department of Mathematics, University of Kashmir. His research interests are combinatorics, graph theory, theoretical computer science, and algebra. He has won Young Scientist Award 2002-2003, Department of Science and Technology, J&K Government of India. He is the head of Department of Mathematics, University of Kashmir from April 1, 2021 to present. He was the Dean of Schools of Physical and Mathematical Sciences from November 2017 to 2020. He was also the head of the Department of Mathematics from August 2014 to 2017. We welcome you, sir.
Thank you, Dipashi. Good afternoon, everyone. So we have this second session of invited talks, and the first speaker for this session is Iva Sbarka. She completed his master's from Szeged, Hungary, and then went on to US, University of Caroline, for her PhD. And after completing her PhD, she has worked at various places on various positions. And finally, in 2018, she is the full professor of mathematics at University of Caroline. She has a very good list of publications, more than 15 number in quality journals. And there is an honor for her, and the award is from American Mathematical Society, which is AMS representation to the Delbert Ray Hulkerson Prize Selection Committee for 2020 to 2023. She was nominated for the Mungo Graduate Teaching Award. So ma'am, please, on the maximum tangle graph crossing number.
Thank you. So this is joint work with Laszlo and the PhD students at our department in Reach and Liu. So I have to start with some definitions. Rooted binary tree, probably everybody knows, but there are different variations of this. So let's just be sure. A rooted binary tree is a tree that has a special vertex, which we call the root. And each vertex has either 2 children or no children. Vertices with no children are leaves, and vertices with 2 children are internal vertices. So this means that I consider a single vertex tree as a rooted binary tree, and that vertex is a root and a leaf at the same time because it has no children. And if the tree has more than 1 vertices, then it has at least 2 leaves of degree 1 and then -1 vertices, where n is the number of leaves here. The root has degree 2 and all other internal vertices have degree 3. So some examples. Right. The 1 vertex rooted binary tree, the 2 vertex rooted binary tree, there is only 1 of these. And you can always obtain the next one by looking at a leaf in one smaller vertex tree and add 2 children. This is the 3 vertex binary tree, and there is only 1 up to isomorphism. Now for 4 vertices, you already have 2 choices because if you insert two children here, then you get this tree, and if you insert 2 children either here or here, you get this tree. So some special trees, I call the rooted caterpillar this sort of structure. So basically you have if you have n leaves, you have 1 leaf at distance 1, 1 leaf at distance 2, 1 leaf at distance 3, and so on, and 2 leaves at distance n-1 from the root. And the rooted completely binary tree of height k has 2 to the k leaves. I think everybody knows this one. If you select 2 leaves, the last common ancestor of the 2 leaves is the vertex that is closest to the root on the path containing them. So for example, if I select those 2 leaves, that's going to be their last common ancestor, because if you look at the path containing these 2, connecting these 2 leaves, this is the vertex that's closest to the original root. So tanglegram, because that's what I promised to talk about. A tanglegram is a pair of 2 rooted binary trees with the same number of leaves and a perfect matching between the leaves. So we consider 2 tanglegrams the same if one can be obtained from the other by a root switching graph isomorphism. So as graphs, they are isomorphic to each other, and the graph isomorphism assigns the left root to the left root and the right root to the right root. And every such graph isomorphism can be obtained by a sequence of switching subtrees rooted at an internal vertex. So a tanglegram layout is a straight line drawing. I'm drawing the left tree with straight lines without crossing edges, the right tree with straight lines without crossing edges, in such a way that the leaf sets are on 2 parallel lines and the matching edges are drawn in between. And that means if there is any crossing in my drawing, it will happen between 2 matching edges. So these 2 drawings, these 2 layouts, I should say, are actually layouts of the same tanglegram. And I have made the coloring so it's easy to check. For example, the left tree is a rooted binary tree of height 2, where one of these pairs of vertices I'm going to call a cherry. A cherry is 2 leaves that are attached to the same neighbor. Oops. Okay, sorry. So this cherry is red and orange. This cherry is blue and red. Similarly here, so the coloring is there. This is a rooted caterpillar. Distance 1 vertex is red, distance 2 vertex is blue, and the cherry is orange and green. Distance 1 vertex is red, distance 2 vertex is blue, the cherry is orange green, so the coloring is matching. The truth is, and the matching is between same colored edges. So you can see that these are the same binary trees. But I can also show you the switches. Switching means that you take an internal vertex and exchange the order of the subtrees. So these are the two trees. I switch on that vertex, then I obtain the layout that you see. Next, I switch on that vertex. That's my new layout. Then I switch on that vertex. And finally, when I switch on that vertex, I get to the other guy. So a sequence of switches gets one into the other. So how do switches change crossings in the layout? Because we have seen that the crossing change. If I have two matching edges E and F in a tangogram, they have a last common ancestor in the left tree and the last common ancestor in the right tree. Last common ancestor is the left tree, is the two last common ancestor of the two leaves they are matched on the left tree, and similarly on the right tree. So for example, in this tangogram, if I select the edge E and select the edge F, in the left tree, these two leaves, if you look at them, the connecting path goes through the root. So the root is the last common ancestor. These two leaves, this is the connecting path, this is the common ancestor. So, given a layout of the tangogram and two matching edges, if we switch at the internal vertex of one of the trees, it will change the crossing status of E and F. So they become uncrossing if they were crossing, and they become crossing if they were uncrossing, precisely when we switched at one of the last common ancestor, either on the left side or on the right side. So let's look at now just the internal vertices of the right tree. I have X, Y, and the last common ancestor of E and F. If I switch on X, E and F still remain uncrossed as before. If I switch on Y, E and F still remain uncrossed as before. And if I switch on their last common ancestor in the right tree, then E and F became crossing and they were uncrossed before. So this is an illustration of what I claimed. So what is the tangogram crossing number? We are finally getting to the concept that I promised to talk about in my title. The tangogram crossing number of a layout of a tangogram is simply the number of crossing of unordered edge pairs. If you take an edge pair that's crossing, because it's a straight line drawing, they only cross once. So I just have to count how many of these edge pairs I have that they're crossing. That's my crossing number. This is important to state this way because you might have three edges in your drawing that crosses at the same point. That's three crossings because you have three different pairs of edges there that cross each other. So from what I said earlier, two edges can only cross if you selected two different matching edges. I have n matching edges. That's my size now. So the crossing number is at most the crossing number of any layout is at most n choose 2. The tangogram crossing number of any tangogram is the minimum crossing number over all of its layouts. There are quite a few. So one way of going through it, though it's not a very efficient one, is to look at all the layouts, count the crossing number of every layout, and find the minimum one. But the tangogram crossing number is also at most n choose 2, since any layout has no more than n choose 2 crossings. It is known, people who have found it are listed here, if that finding the tangogram crossing number is an NP-hard problem. So it's believed to be very hard. It's believed to be that there is no polynomial time algorithm that can find it for you. But it is fixed parameter tractable, which means that if I fix any number k, say 5, deciding whether the tangogram crossing number of your tangogram is at most 5 can be done in polynomial time. But this polynomial depends on the number that you fix. So if you want to find the actual tangogram crossing number, it's still NP-hard. So with Stefan Wagner and Laszlo, we have determined that there is a positive constant C such that if you select the size and the entanglogram randomly uniformly amongst all the size entanglogram, then the expected tangle crossing number of this tanglogram is at least constant times n squared. So in order as large as possible, because the tangle crossing number is at most constant times n squared. Just the two constants differ. So how do tanglograms look like? Some small tanglograms. This is an obvious one, size 1 tanglogram. You have one vertex here, there's just one matching. Size 2 tanglogram, there is a unique tree on both sides that you can put there, and it doesn't matter how you match, you end up with this up to isomorphism. So there's still one tanglogram. Size 3 tangograms, there's a unique tree to select from both the left and the right side, but there are two different ways you can match them. Those are those two. And these are all the size 4 tanglogram. You can have two trees. You have seen those before, the height 2 binary tree and the 4-leaf caterpillar. And there are 7 different ways you can select them. And these are actually drawn in the best possible way with respect to the crossings. So with the least number of crossings, with the crossing number. And you might notice that all of them here are planar. They can be drawn without crossing, except number 6 here and number 13 here that have one crossing. So why do we even talk about tangograms? Who came up with this concept? Tangograms are used in several models of coevolution in biology. For example, parasites and hosts, and the matching represents which parasites dwells on which host. There are some multi-gene coevolution models in which tangograms are used, and a lot of other things. And tangogram crossing number is believed to correlate well with biologically important quantities corresponding to this model, such that number of times parasites switch host, the number of horizontal gene transfers, which I don't want to get into because this is not a biology lecture. But this is something that biologists actually do care about a lot. So correspondingly, there are several results besides the one that I mentioned. For example, Billy, Konvalenko, and Madsen provided exact and asymptotic enumeration of the tangograms. And asymptotically, their number is 2 to the n minus 3/2 times n to the n minus 5/2 divided by square root of pi times e to the n minus 1/8, which is a mysterious number. If you think about it, it involves pi and e, despite of the fact that we are talking about integers numbers. So Ravello, Manana, and Wagner have given the same result with respect to planar tangograms. They enumerated them exactly and asymptotically. And it's essentially a constant times another constant to the n divided by n cubed, but those constants are weird. So with Wagner, the same Wagner who had enumerated the tangogram, and Laszlo, they gave a Kuratov-Stein theorem characterizing planar tangograms. If you recall, the Kuratov-Stein theorem says that a graph is planar precisely when it doesn't contain a subdivision of K5 or K33. We have a similar thing here. A tangogram is planar if it doesn't have those two pesky tangograms that had crossing number 1 in the previous lecture, number 3 and number 6. So those are the ones responsible for a tangogram not being planar, but the containment is the induced subtangogram relation, which is somewhat natural because if you think of a tangogram that I built the phylogenetic tree of the host and the parasites, and the matching is who is dwelling on whom, an induced subtangogram would be I'm selecting a subset of the hosts and the subset of the parasites who actually are matched to them, and build a smaller phylogenetic tree on the two sides. It can be described mathematically what exactly is going on, but I'm not going to bother with that because I'm not going to talk about that today. And with our PhD student, Stephen Smith, very recently, we actually provided an infinite anti-chain in the tangogram poset where the tangograms are ordered by this subtangogram relation. And more surprisingly, that every member of that infinite empty chain is a planar tangogram, which is sort of a bummer because this cut off a very natural way to actually provide, actually not provide, but know that similar characterization like this Kuratowski type theorem exists for very many interesting questions about crossing numbers of tangograms. So those are harder than one might hope for. And there are countless algorithmic results on drawing tangograms, obviously because it's an MP-hard problem, we can't be sure to draw them perfectly, but there are these algorithms that apply reasonable ideas trying to draw them with small crossing number, hopefully close to the actual one. So largest tangogram crossing number. At a mathematical research communities workshop organized by the AMS with this group of people, we started to work on this problem. So I'm going to denote the largest tangogram crossing number of a size n tangogram by Mn. And what we have managed to show that Mn is strictly less than 1/2 n choose 2. Remember, n choose 2 was the very trivial upper bound, so it's not more than half of that. And it's bigger than 1/2 n choose 2 minus a term that's of order of n 3/2, when n is a square number. And actually, in general, it's still bigger than 1/2 n choose 2 minus a term that's of order n to the 3/2. And this means, since 1/2 n choose 2 is of order n squared, that if you divide Mn with 1/2 n choose 2, in the limit as n goes to infinity, this goes to 1. So we actually know the order of Mn. It's about 1/4 n squared plus the term that's little o n squared. So how you can see that Mn is less than 1/2 n choose 2, this is actually fairly simple. If n is at most 3, the tangogram is planar. I have shown you all sides 3 tangograms, they were planar. So we can start, and 0 is less than 1/2 n choose 2 with for those numbers. So that's fine. So we can consider any tangogram of size at least 4, because those are the ones that we have something to prove for. And size at least 4 means that both the left and the right tree will have a cherry, a pair of leaves that are adjacent to the same neighbor, which I'm going to use later. So what I'm going to do, say I'm selecting the left tree from your side, it's this side. So I'm selecting the left tree and I switch at every internal vertex. That means that I changed the crossing number of every, the crossing status of every pair of edges in the layout. So if it was uncrossed, it becomes crossed, and if it was crossed, it becomes uncrossed. So if I started with a layout which has crossing number k, after the switches, everybody switch status, so the new layout has crossing number n choose 2 minus k. And that means that the tangogram crossing number is at most the smaller of these two. And at first, it can be 1/2 n choose 2. I'm almost there, except that this is less than or equal to, and I claim strictly less than. So if 1/2 n choose 2 is an even number, equality is still possible. So I have a little more to work. So what can happen? If equality holds here, so minimum k and n choose 2 minus k equals to 1/2 n choose 2, then both k and n choose 2 minus k is 1/2 n choose 2. In fact, for every layout of the tangogram crossing number has to be that same number. But that is impossible, because now I can take any of my layouts and switch a cherry at the right tree. So that means I change the crossing status of exactly one pair of edges. So I got a new layout that has a different crossing number. So it cannot be equal to 1/2 n choose 2, it's less than. Well, that was easy, I think. So how do we do the other reaction? So before I do that, in order to do that, so I have to give you a tangogram that has crossing number bigger than that. Okay, so giving the tangogram means I give you the left tree, I give you the right tree, I give you the matching, and I argue that it has large enough crossing number. I'm going to do that first with when n equals to k squared. So I'm going to create a left tree with k-square leaves as follows. I'm going to have k plus 1 trees with exactly k leaves, L0, L1, Lk, and I'm going to do it in following way that my root is going to be the root of L0, and I'm going to append the roots of L1, Lk to the k leaves of L0. This is going to be a tree with k-square leaves, k times k is k-square. And I'm going to label the leaves V11, V12, V13, and so on. So Vij will be the jth leaf of the tree Li. So far, so good. I'm going to do the same thing for the right tree, except so to know which one is which, I'm going to label the leaves Wij's, not Vij's. And the matching is going to be the following. Uij is going to match to Vji. So far, so good. Why is it good? That means that the first tree has an edge going to the first tree on the right side, the second tree, the third tree, and the kth tree. Similarly, the second tree, the third tree, and so on the kth tree. So every tree Li is matched to all of the trees R1, R2, Rk on the right side. And that means, since no matter how I'm drawing these, the leaves of L1 are going to be next to each other consecutively, the leaves of L2 are going to be next to each other consecutively, I can view it kind of going out and into the distance that I have these color dots, K dots exactly on the left and the right side, and everybody is connected to everybody else with a straight line. So the crossings I see in this drawing will be seen here too, and maybe some more, because if the edges of coming out from L1 have to intersect between each other, I'm not seeing those anymore. So how many crossings will I have in this thing? I have to select 2 vertices on the right side, 2 vertices on the left side. There are 4 edges going between them. I better do it. So 2 edges on the 2 vertices on the left side, 2 vertices on the right side. There are 4 edges going between them like this, and 1 pair of them is crossing. So there are k choose 2 vertices selecting from the left, k choose 2 ways to select 2 vertices from the right. So k choose 2 square ways of selecting these 4 edges, and each of these corresponds to 1 crossing. That means that the maximum tangle crossing number on k square points is at least k choose 2 squared. So what if n is not k squared? Well, I will draw this tree for the largest k that n is at least k squared. And I just insert a few leaves here and there with an edge and connect them any which way I want. So that means that mn is at least square root of n floor, that's my largest k, choose 2 squared, and the bit of algebra gives you what I claim. That's all. So we are going to be interested now, because we are interested in the largest tangle crossing number. How big is it exactly, or at least approximately? What's the exact separation between mn and 1/2 n choose 2? And what I have just shown you show that mn is less than 1/2 n choose 2, but bigger than this quantity. So what we have managed to do is improve upon these bounds. We improve the upper bound is to 1/2 n choose 2 minus n over 8. And we kind of improve the lower bound, because I don't have it for every n, just for n equals to 2 to the k, to 1/2 n choose 2 minus n log n over 4. Log is now base 2. So I'm going to show you how. So how do we do this? I'm going to have a tanglegram with 2 to the k leaves, tau k with 2 to the k leaves, and tangle crossing number this quantity, which is exactly this quantity when n equals to 2 to the k. How? I'm going to describe a tangogram with its layout first. Okay. So what I'm going to do is I always have to turn around to know this. The left tree is the complete binary tree of height k. The right tree is also a complete binary tree of height k. And I'm going to label the leaves from 0 to 2 to the k minus 1 with their binary representation in order. So those are going to be the strings, 0, 1 strings of length k, all of them in this order. And I'm going to put an edge between two leaves in the left and the right if the label of one is the reverse order of the label of the other. So 0, 0, 0 is connected with 0, 0, 0, 0, 0, 1 is connected with 1, 0, 0, and so on. Okay. So this is my tangogram for every k. It's an easy exercise to show that the layout that I described, so if I draw it exactly this way, has exactly as many crossings as I claim the tangle crossing number is. That's all nice, but how do I know that there is not a layout with smaller number of crossings? Well, now come the colors that I put here. One of the things that happens, if you look at what I'm going to call the reddish colors, the red and the orange, this is going to be, if this is a complete binary tree of height k, this is a complete binary tree of height k minus 1 in this side. And if you look at what they in use, it's actually tau k minus 1, the edges. And similarly, the bluish colors. So I have two disjoint layouts of tau k minus 1 with any layout of tau k. And that actually gives me at least twice the crossing number of tau k minus 1, many crossings in this layout. In addition, if you look at the reddish edges, now I need the red and the orange. On this half, the red edges go to this subtree, the orange edges go to this subtree. The blue edges go to the first subtree here, and the green edges go to the second subtree. The important part is that half the edges coming out from there go to the first, and half the edge go to the second little subtree over there, no matter how you lay this out. And that means that half the edges from here and half the edges from here always cross. And that means that in any layout of tau k, there are at least 2 to the 2 times k minus 2 crossings between the edges of those two little subtrees. And that gives me that 2 times the crossing number of tau k minus 1 plus 2 to the 2 times k minus 2 is a lower bound of the crossing number of tau k. And this quantity is the upper bound. And now to say that this is equal to this is equal to this is a simple induction argument, okay? So what about the lower bound? I'm going to first tell you about the Berlekamp switching scheme. This is a quote from Alan Spencer's book, Probabilistic Method. You have an n by n array of lights to be given. Each light is either on or off, denoted by +1 and -1. And in each row and each column, there's a switch. If you pull the switch, that changes the lights in the row. Whatever was on becomes off, and whatever was off becomes on. Then for any initial configuration, so any settings of the lights, it is possible to perform switches so that the number of lights on minus the number of lights off is at least square root 2 over pi plus little o 1 times n to the 3/2. Okay, this actually exists. This is a picture of Berlekamp switching game. This is a 10 by 10 array of lights. So the result that I mentioned, which was proved by Komos and Shoyok and Brown and Spencer, can be described this way. You are given an array of plus or minus 1 numbers aij. Then there exists constant there exists xi and yj, both of them set with plus or minus 1, such that the double sum xi, yj, aij is bigger than or equal to 2 square root 2 over 5 plus little o1 n to the 3 half. Which, by the way, means that there exists a selection of xi and yj such that the double sum is less than or equal to minus the same quantity. For example, you can switch the choice of every xi in the previous case, whatever when xi was plus 1, select minus 1 and vice versa. It is known that these bounds are best possible up to a constant number. So this sum can be as big as n to the 3 half, maybe not square root 2 over 5, but some bigger constant. And I want you to know that if you look at xi and yj as independently selected random variables, the expectation of this quantity is 0. So the question is how far away we can push this sum from the expectation. All very nice, but what does it have to do with tangogram? So take a tangogram, any two matching edges EF, take your favorite layout D. I'm going to say that chi of the EF is 1 if E and F crosses in this layout D and minus 1 otherwise. So this is actually same as the crossings, the number of crossings. The crossing number of E and F in the layout D is 1 or 0, depending upon whether it's crossing or not. And that can be actually this quantity, 1 plus the chi value divided by 2. Crosses 1 plus 1 over 2 is 2 plus 2, which is 1. Doesn't cross 1 minus 1 over 2 is 0 over 2, which is 0. So I just shifted the crossing. Fix your favorite layout epsilon. This is going to be called standard layout by now. Look at the internal vertices of the left tree and the right tree. And I'm going to have a pair of functions alpha and beta on the internal vertices of the left and the right tree, which have values plus or minus 1. Plus 1 means that starting from my standard layout, I keep the two subtrees in that internal vertex. Minus 1 means that I switch. So this pair of vertices will give me a new layout. And in fact, every layout can be obtained this way. And if you look at the chi value of E and F in the layout D, because it only changes, the crossing status only changes when you switch on the vertex of the last common ancestor, that can be computed as the alpha value in the left common ancestor of EF times the beta value on the right common ancestor of EF times the chi value in the standard layout. Which means that the crossing number of a layout is the number of crossing of unordered edge pairs, and the number of crossings can be computed as sum over all matching edge pairs, 1 plus the chi value on DEF divided by 2. And because of that observation, this quantity can be replaced with this. This looks more complicated. How does it help? Well, a little bit of manipulation will get you this to 1/2 n choose 2 plus 1/2 times sum over the internal vertices of the left and the right tree, the alpha value, alpha and beta values, product of the alpha and beta values times sum over matching edges where the left common ancestor is X, the right common ancestor is U, the chi value in the standard layout. Yeah. This gives you that from random values of alpha and beta, the expected crossing number is 1/2 n choose 2. This red quantity can be viewed as the difference, as the gap from 1/2 n choose 2 of the layout. And the issue is, how small can we make this? That's going to be my maximum crossing number. If for any tangogram I can make it small enough, that means that the tangogram crossing number is 1/2 n choose 2 minus this quantity. So this is the goal. Using appropriate plus or minus values for alpha and beta, we want to push down this value. Now I'm going to denote this quantity because this is now constant. This only depends on my standard layouts and choice of tangogram of AXU. And this is sum of alpha x beta u AXU, which can be written as sum of AX times this green quantity. And This red sum now looks exactly like the Berlekamp switching game, the xi, the yj, and the aij, except the xi's, the alpha x are plus or minus 1, the yj's, the beta u's are plus or minus 1, the axu's, which was the xij's, are not plus or minus 1 now. They can be larger, smaller, and unfortunately, they can be 0. So it's an analogous situation, slightly extended thing. What can we do with this? So I'm going to say that given a root in binary tree, not a tanglegram binary tree now, an internal vertex is special if it has a leaf neighbor and even number of leaf descendants. So this is now a tanglegram picture, but this X is supposed to be special here. It has a leaf neighbor and some other leaf descendants, but the total number of leaf descendants, including this guy, is even. So I have a special vertex in the left tree. I'm going to denote the leaf neighbor by V0 and the adjacent matching edge by E. The other leaf descendants, V1, V2, K minus 1, the total number of leaf descendants is even, so the other ones are odd. And the matching edge is F1, F2, F2K minus 1. And UI is going to be the last common ancestor in the right field, E and Fi. So I have a bunch of UIs over there. If you take two matching edges, such that, sorry, not such that. If you take two matching edges, if their left common ancestor is X, that means precisely that one of these edges is E, the other one is the Fi. The only way to get this to be the left common ancestor, if one of the edges is E, the other one comes here. So pick your favorite special vertex in L, and I want to compute this quantity. The first step was to write in what the AXU was. Now, what happens here is that I summed over all the internal vertices of the right EU and summed over all the matching edge pairs whose left ancestor is X and right ancestor is U. Well, the left ancestor X is fixed and the right ancestor goes over all possibilities. So this is essentially sum over all matching edges whose left ancestor is X, this quantity. Well, but we know that if the left ancestor is X, then one of them is E, one of the edges is E, the other one is one of their Fi's. So I have a sum that has odd number of terms, and the terms are all products of two quantities plus or minus 1. So it's a sum of an odd number of plus or minus 1, which is odd. Most importantly, odd means not 0. So how do we finish this proof? We can show that any rooted binary tree with at least two leaves has at least floor of n over 4 plus 1 special vertices. This is an easy induction proof, and the easy induction proof actually gives you that this theorem is sharp. Now, this is a corollary. In any size n tanglegram, there are at least floor of n over 4 plus 1, which is bigger than n over 4 vertices, internal vertices of the right tree, that, such that for no matter, for any choice of beta u, so no matter what the layout is, this quantity is at least 1. Now I took the absolute value, so that's at least 1, because it's not 0. Now pick alpha x for every x, negative of the sign of this sum. So if the sum is positive, alpha x is negative 1. If the sum is negative, alpha x is positive 1. And that means that now this quantity that we cared about becomes sum over the internal vertices of the left tree, the absolute value of this. And since there are at least n over 4 vertices for which this absolute value is 1, and I have a minus 1 here, this is less than minus n over 4. Remember, in that red quantity that I cared about, there was a 1/2 in the front. Therefore, I have that the maximum tangle crossing number is less than 1/2 n choose 2 minus n over 8. So what I want to add is that I kind of believe that the n log n over for lower band actually extends. But we know that that's not the best drawing that exists. We just don't have any sort of proof or idea how we can push it further. So it's a question whether the true answer is between n, order n, or order n log n. But that's all what I wanted to say. Thank you very much. Are there any questions? And I hope I got a little bit of extra time for you guys.
Are there any questions or comments? Any questions or comments? Yes. Any comment?
Yes.
Why do you consider the order tag e comma s instead of just
Use the
Oh, sorry. Yeah. Why do you consider it as the order of n squared as a crossing number instead of choosing just because there'll be only n edges, right? Like, why do you?
There are n edges, but if you select any two, they might cross.
Oh, I see.
So
you look
n
at.
choose two,
Okay.
means you can select any two, so it's order n squared, at most order n squared. And we have actually managed to prove that in expectation, it's order n squared.
I see. Okay.
Which is actually good news for the biologists because they believe that the trees they build have some sort of relationship status.
Okay.
And the fact that they have low crossing numbers, so the crossing number is not order n squared, is sort of a proof of that they are not just randomly selected, but there is something going on there.
I see. And how does this the rooted binary tree structure affect the result? Can we have some other?
So the rooted binary trees come from the fact that these are supposedly come from phylogenetic trees.
Okay.
And phylogenetic trees are rooted binary trees, ideally. And if they are not rooted binary trees, because if you want to build a tree, then sometimes there are issues. Then they are low degree trees. So there are actually extensions of this idea to trees that are not rooted binary trees.
Okay.
Or phylogenetic networks, which is like kind of a more complicated thing, and also to things where there is not a matching, but a many-to-many relationship.
Okay.
In some cases. So there are other ideas going on, and some of them actually have been enumerated. So if you look at some papers of Billy and Komvalenka, you can find extensions of these ideas.
I will check. Okay, thank you. Okay, thanks.
Any more questions? So if there are no more questions, let's thank the speaker again. And
thank you.
so our next speaker for this session is Professor Suresh M. Hegde. He's professor in National Institute of Technology, Sudoku in Karnataka. Suresh did his PhD from University of Delhi with Professor B.D. Acharya and Arn Cole. He is also the Dean of Students Welfare there, has guided several students and has produced many good research papers. Professor Suresh has also actively worked at different positions in National Institute of Technology, like he has been the coordinator for continuing education, then worked as warden and other things. He has a vast teaching experience of 25 years. So now I request Professor Suresh to share his research.
for your kind words. First and foremost, I'd like to thank the organizers of this conference, and a special thanks are due to Dr. Rajesh Singh. Before going into the graph labeling problems, I'd like to tell you something which only mathematicians can do. Can anybody from the audience recognize at least one person from that photograph? Who is that? Okay. So this is the photograph of the 4 field medalists in the year 2014. The ICM was held in Korea, and they are Arthur Avila. So he is Arthur Avila, then Martin Herer, then she is Mariam Mirzakhani, and of course, I suppose many of you know Manjul Bhargav. Okay. Yes, Mariam Mirzakhani. Let me tell you something about her. Mirzakhani is the first woman to get the Fields Medal after a long years. And the citation for her award was outstanding contributions to the dynamics and geometry of Riemannian surfaces and their moduli spaces. Born on May 12, 1977 in Tehran, Iran, but unfortunately died on 14th July 2017. And you know, the field medals are given to the mathematicians below the age of 40. She born in 77, died in 17. 40 years she lived. And she did her BSc from Sharif University of Technology, Tehran, and PhD from Harvard University. After BSc, she straight away went to Harvard and did her PhD. Why I took this is, can anyone have infinite wealth or infinite number of dollars or rupees, whatever you say? Can anyone? No? Okay, let us see. She worked, sorry, this her supervisor was Macmillan from Harvard. Okay. See, I told you, and yesterday Professor Pijada sir said, mathematics is the king of, not queen. Definitely, you know, kings are controlled by queens. Why? Because of the power of mathematics, because of the number of tools exist in mathematics to solve the problems. You know how many branches are there in mathematics? These many branches are not there in any science. So that is the beauty. So as I asked you, can one make infinite wealth? You said no. Okay. But I told you only mathematicians can do that. Neither Tatas, Birlas, Ambanis or anybody, Musk or like that. But there is a possibility for mathematicians to do that. Okay. Given a complete tripartite graph, is it possible to partition its edges into collection of 5 cycles? This is the problem. Okay. Some complete tripartite graphs can be decomposed into cycles, 5 cycles, and others cannot. E.S. Mahmoodian from Sharif University, and he was the mentor for Mariam Mirzakhani when she was doing her BSc. And what he did, he set up a contest which offered $1 for every new example that a contestant could find. What he wanted? The decomposition of the complete tripartite graph into 5 cycles. Okay, this is one example. This is state 333, and these are the possible types of decomposition into 5 cycles. Okay, so this is one time, that means taking 2 points here, 2 points here, 1 point here. So like this, which is the method of decomposing. Interesting thing is, she found a countably infinite classes of such graphs. That means she got infinite dollars. She got infinite dollars. This is possible only with a mathematician. I don't think anybody else can have infinite dollars. See, this shows her level. She did this in her BSc. Okay, and she got the gold medals in mathematical Olympiads, getting 100 out of 100. So I brought this because to tell that mathematicians can do wonders. Nobody else can do. Okay, now let me come to the graph decomposition. In fact, that was also a decomposition. The study of decomposition of graphs and hypergraphs almost. It's a very long, it has a very long history going back to 200 years to the work of Euler on Latin squares. So you know what is a Latin square. And in 1872, Euler asked for which values of n there is a Latin square which can be decomposed into transversals. What is a transversal? A transversal is a collection of cells of this Latin square which do not share the same row, column, or the symbol. Okay. This problem has many equivalent forms. One equivalent form is graph decomposition. Look at this Latin square. This is 4 by 4, and this is one transversal, and this is another transversal. This is the third one, and this is the fourth one. These are the 4 transversals of this. Okay. We say that a graph G has a decomposition into another graph H if the edge set can be decomposed into this into the graphs H. This is called graph decomposition. So we are only decomposing the edges. You know, if the graph is Eulerian, the edge set can be decomposed into disjoint cycles. So like that, here we are decomposing the graph into given graph, say H. Euler's problem is equivalent to asking for which values of n the balanced complete 4-partite graph. So here he has used the word balance as the regular. Okay. four-parted graph K, N, 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 N have a decomposition into copies of the complete graph on 4 vertices. Okay. In 1963, Ringel, in the proceedings of some conference, made a very appealing conjecture on decomposition of complete graphs into edge disjoint copies of a tree with roughly half the size of the complete graph. Ringel's conjecture says the complete graph with 2n plus 1 vertices can be decomposed into n trees, copies of the tree with, n edges. Okay. This is the decomposition problem. Okay. But as we know, to solve some problem, many concepts in mathematics were introduced. Okay. To solve 4-color problem, the chromatic polynomial was introduced. They wanted to approach this 4th-color problem using the approach of chromatic polynomials. So like that, to solve the decomposition problem, Rosa has introduced the graph labelings. See, we are calling here the labelings. Much before 1963, you can find the graphs having labels on the edges. They were called weighted graphs, not the labeling. Here, we are defining this as the labeling because we have the relation between the values of the edges as well as the vertices. But there only they were giving weights to the edges. Okay. The definition, what we say, graph labelings, where we assign the vertices and edges to the given graph. Sometimes we assign real numbers. Sometimes we assign pluses, minuses. Sometimes we assign the subsets of the sets. Okay. And with certain conditions, we are studying, or people have introduced the different types of labelings. What are, see, some of the labelings were motivated by their utility to use in solving the real life problems or applied fields, and their intrinsic interest or mathematical interest, we call it a logico-mathematical. See, as discussed in every conference or every meeting of mathematicians, people are asking for applications. Of course, if a person who is really interested to know about the applications, we can to some extent tell him, but it is very difficult if a person just want to ask for the sake of asking. There are people simply just trouble you, they will ask, what is the use? Tell me. But for that also we can snub them, because we have bombastic words in mathematics also. We can tell them that this is used in this one, this one, this one. He doesn't understand that. That's why. Okay. But at the same time, it is always better to know some applications which we can convince. Simple applications. Okay, this is what. See, today mathematics is used throughout in so many fields, but mathematicians also engage in pure mathematics. This we are mathematicians. We are preparing the tools. We are preparing the tools, but it's used by somebody. We should not bother about the use of the tools. We are having the different tools of different sizes, shapes, and all. I'm not bothered while preparing the tools. Is it not? So we should not bother in applications until and unless whatever we do are logico-mathematical. We are bothered about that. We are bothered about the subject, development of the subject, not about the applications. Okay, but of course, need of Java is also there, that is application, but fine, we have to have. You must know some applications. Fine. Okay, as told, it was introduced in 60s and till now the number of papers are getting increased, and for example, for about 3,000 papers can be seen using the Galleon survey. This is a formal definition of the graph labeling. We are taking the set R, we are taking the vertex set, edge set, and then using a binary operation. What is the graph labeling? Graph labeling is a binary operation star from R cross R to R, where every vertex function F from VG to A, we are taking subset A of R, induces an edge function F star from EG to R, such that we have defined the edge value as star of F of U equal to F of U star F of V. Normally we take the integers. Okay. Now, important thing is one is interested in determining the vertex functions having the specified property P such that the induced edge function has some specified property Q, but P and Q need not necessarily be distinct. And in literature, one can see many binary operations, that is addition, multiplication, modular addition, absolute difference, modulo subtraction, and if you are using, then it is symmetric difference, etc. So these are different kinds of graph labeling exists in nature. So this is the labeling introduced by Rosa. The vertex values vary from 1 to n. The edge values will be from 1 to n. And as shown by the earlier speaker, after giving the label, you can partition the vertex set into two sets such that all the numbers in one set are less than the numbers in the other set. Okay. So these are the three conditions, and we define, or Rosa defined, alpha labeling if the function satisfies ABC, and beta labeling AB. But as told by the earlier speakers, presently the beta labeling is popularly known as graceful labeling. Okay, these are some of the examples for the sake of completeness. A lot of work on Ringel's conjecture has used graceful labeling approach to solve some decomposition problems. Okay. Rosa has proved the following theorem. This is regarding the decomposition of complete graph with K2n plus 1. He has proved if a graph has an alpha labeling, then there exists a decomposition of the complete graph K2n plus 1 into copies of G for all K. This he has used using the alpha labeling. And he has used one more type of label. This is the decomposition, how the complete graph K5 is decomposed into trees. 2n plus 1 is 5, n is 2. The tree is having two edges and it is decomposed into 5 trees. And he has also introduced another type of labeling called row labelings. So here he allows the vertex numbers to go from 1 to 2 times number of edges, whereas the edge numbers will be from 1 to 2 the number of edges. So he has defined the labeling as if f of u, so if f of u minus f of v less than or equal to the number of edges, then the labels on the edges retained like this. If not, then it is obtained like 2m plus 1 minus the value. For example, consider the complete graph. We have 10 edges, m is 10 here, and the vertex values can go from 0 to 20, and these are the vertex numbers. And if you take the take this edge, then 15 minus absolute difference of 15 minus 13 is 2. It is retained here. Otherwise, see here, 0 minus 15 is 15, but it's more than 10. It's more than 10. That's why the 15 is not retained here. But here, the value is 6. So like this, if you are able to give the labeling, then this graph is called row labeled graph. As you introduce this again to solve the Ringel's conjecture, and he has proved if G is a graph with 2m plus 1 with m edges, sorry, there is some problem. If G admits row labeling, then the complete graph k 2m plus 1 can be decomposed into 2m plus 1 copies of the graph. These are some labelings defined by Rosa. There are some other types of labeling exist in nature. Let me tell you some application of labeled graphs, and then if time permits, we will discuss some applications in detail. So the qualitative labelings, as I told you, in literature you can find some labelings where the plus and minus or minus 1 and plus 1 are used to label the points, and you get similar things on the edges. These are called, when we use this, the qualitative labelings. And qualitative labelings can be seen in conflict resolution of social psychology, electrical circuit theory, energy crisis, etc. Whereas the quantitative labelings, where we use the numbers, has a lot of applications, such as coding theory, ambiguities in X-ray crystallographic analysis, design of communication network addressing systems, in determining optimal circuit layouts, construction of polygons with same internal angle but distinct sides, solution of linear congruence equations. We can solve some linear congruence equations using graph labeling problems, radio astronomy, etc. There are many. Okay. So what happens in this X-ray crystallography problem? Okay, I will write input, then processing, and then output. This is what we talk about nowadays. But earlier this input output was not there. Okay, now here the input is a crystal. Processing is X-ray diffractometer. Kindly excuse me for my good handwriting, because I cannot read my own handwriting sometimes. There's a problem. Then this is X-ray diffraction. Okay, and this is a crystal, and when the crystal is put in this X-ray diffractometer, it will give you X-ray diffraction pattern. Actually, this is a set of numbers. This is the crystal, and what this X-ray diffractometer does is it fixes the atomic positions and measures the interatomic distances between every pair of atoms. So when we see the word distance, it's a number. So output is set of numbers. This is the physical problem. Mathematically, in this one, what we do, this is set of numbers. Our processing is absolute difference between the numbers. Once we take the absolute difference, what is the output? Set of numbers. Set or maybe multiset. Set or multiset, because there may be repetition of numbers depending upon. This is the problem. But what happens, what is the ambiguity in the X-ray crystallography is that the X-ray crystallographers had believed if the numbers in this set output are all distinct, then their conclusion is it cannot be crystal 1, crystal 2, cannot be from two different crystals, it is from a unique crystal. Okay, their conclusion was that if all the numbers are distinct, then this pattern is for a unique crystal. But it was disproved that it is possible that two different crystals can give you the same X-ray diffraction pattern. And this was proved by mathematicians. Okay. A combinatorial problem of antennas in radio astronomy. The antennas are to be arranged. Few antennas, some of them being movable, are required to be located in several successive array configurations to measure various spatial frequencies relative to some area of the sky. What they want, they don't want the repetition of the same spacing as well as whole. In a sense, no number should miss. The condition is you have to arrange the antennas in such a way that the distance between the antennas are some multiples of some number d, where there should not be any repetition, there should not be any missing number. This can be solved using labeling problems. Now let us come to magic graphs. Sorry. A graph is said to be edge magic. Then if it is possible to assign the numbers to the points as well as edges from the set 1, 2 to p plus q, such that you take any edge, the value assigned to the edge as well as the end point should be the same. It's a constant. A magic graph is said to be super edge magic if in this assignment the vertices or points receive only the values from 1 to 2 number of points, and edges will receive from p plus 1 to p plus q. In the magic graph, it is not necessary, it can be anything. But if a magic graph satisfies this condition, that magic graph is called super edge magic. And one can see a property in a super edge magic graph, the sum of the vertex value into degree plus sum of the edge values is equal to q times cf, where cf is called the magic constant. Okay. Sorry, yeah, maybe I'm poor in preparing. First, that should have come. So the theorem has come after that. Fine. We are using this magic labelings to solve a linear congruence equation. In fact, in a paper published by G. Adams and Vadim, distinct solution to linear congruence in the journal called Involve. It's a very good journal, but only condition is that if you want to publish in this journal, guide and student must be there. One of the author must be a student, and you have to send the proof also. Okay. So in this journal, it was conjectured that for k less than n and the GCD of A1, A2, AK belongs to Zn star, then there exist distinct solutions for the congruence equation A1x1 plus A2x2 etc. AKxk, which is congruent to 1 in Zn. Okay. Now we have solved partially this conjecture using the concept of magic labelings. How we did it, this paper was published in National Academy of Science Letters. What we have proved that if k is less than or equal to n minus 1 and A1 plus A2 etc. AK is equal to n minus 1, then there exist distinct solutions xi satisfying this equation. Okay. What we do, consider this equation, that is 4x1 plus 3x2 plus 2x3 plus x4 plus x5 is congruent to 1 in Z12. So for us, k is 5, n is 12, and we use this one, n plus 1 minus k equal to 12. Okay. Consider a sequence that is A1, A2 to AK and introduce this many zeros. From this, we see that the A1 is 4, A2 is 3, 2, 1, 1, and these many zeros are introduced. Then we have added 1 to all these numbers. We got 5, 4, 3, 2, 2, 1, 1, 1, 1, etc. Now what we do, we construct the caterpillar of order 3 and size 12 using this sequence. Yes, this is how we have constructed a caterpillar. So look at these V1, V2, V3, V4, V5. These are representing the 5 coefficients. Okay. Then after adding so many zeros and then adding 1, these points represent those 0 and 1s. This is how we construct a caterpillar. Now, this is how we have constructed. Now, we have labeled, because that labeling was different, and now we have labeled in a different way this caterpillar, and we have given a super edge magic labeling for this caterpillar. You can see the value of V1 is 1, V2 is 10, V3 is 4, and V4 is 12, and V5 is 5. The original V1, V2 to V5. Now we have changed. Okay, and 5 plus 13, 18. So 1, 2, 2. Okay, then we have labeled 1, 2, 3, 4, 5 to these vertices. Then 6, 7, 8, 9, 10, 11, 12, 13 to these vertices. Okay, then 1 plus 6 is 7 plus 14. Then 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, we want to make this graph super edge magic labeling. Now I am asking the audience, if you want to make this graph super edge magic, And you have used from 1 to 2 number of vertices here. You have to use 14, 15, etc. Where this 14 can be given, here or here? Hmm? 14, suppose you give 14 plus 13, 27 plus 5, 32. Okay, let us say 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So this is how you can give the labels. Then you take any edge, the number is 32. So this is a super edge magic labeling. Now, as I told you, if the graph is super edge magic, then the summation of edge values plus summation of the vertex values multiplied by the degree is q times the constant. Okay, q times the constant. Now we have seen that the vertex values of this super edge magic graph is in the set 1 to n. Okay, and they are distinct in Zn, because now we are considering Z12. Okay, and you can see that summation of ai into f of ai will be congruent to n minus 1 in Zn. This we have proved. Now, yeah, how we solve this equation? Now we substitute xi equal to n minus f of vi. Remember, vi's were the original vertices, and we have seen, and using this one, you can prove that ai into n minus xi is congruent to n minus 1 in Zn. Hence, sum of the ai xi for this value satisfies the equation. That means these are the solutions for the given equation. Yeah, consider. So our x1 was n minus f of v1. F of v1 was 1, 11. Then x2 is 12 minus 10, it's 2. x3 is 12 minus 4, it is 8. x4 is 0, x5 is 7. These are all distinct. And this, see, 4 into 11 plus 3 into 2 plus 2 into 8 plus 1 into 0 plus it is 73, which is congruent to 1 mod 2. So this is how we use graph labeling problem to solve the equation. Okay. Now we have another application. This was published in the discrete mathematics. I will just illustrate. Indexable graphs means or indexable labeling means we are taking the vertex values from 0, 1 to 2, p minus 1, and edge labels from 1 to 2, q. Then the edge values obtained by using the binary operation plus. Okay, I will tell you a small. Okay, let it be there. I will just. Next. Yes. So what we do, you take a triangle with one unit, then give 0, 1, 2. This is 1, this is 2, this is 3. So this is one indexable. Okay. Then what we do, add 1. So this becomes 1, 2, 3. Then we take the addition, 1 plus 2, it is 3. This is 4 and this is 5. What we do now, here k is 1 and what we do, we consider a cycle C2n plus 1. So this is a cycle when n equal to 1. So we have k equal to 1, n equal to 1, and this becomes 9. Okay. Now what we do, we divide this edge into 9 parts. All these edges into 9 parts. Okay. Now this is C2n plus 1, a cycle. And we do this one. Then this number is 1. We consider a point which has got distance 1, both sides. Then we join. And here we consider the point which is at distance 2, join. Here we consider the point at which distance 3 and join. Now from C2n plus 1, we got P 4n plus 2. Okay. So we got a polygon with 4n plus 2 sides. Now we are saying that this triangle has, this polygon. Now you can say A, B, C, D, okay, E, F. This is a polygon with 6 sides. Okay. Once we construct like this, then we have to find the internal angle is 2n by 2n plus 1 pi. Okay. So here n is 1. This is 2 by 3 pi. I think it is 60. Fine. So internal angle is done. It's the same. Now we have to calculate the sides. Fine. This side is 4k plus 4n plus 4 minus I plus j. That means this plus this. So this we have divided this into 9. And the length of this side, that is AF, is 9 minus 1 plus 2, it is 3. This is 6. Okay. Now here 9 minus 5, it is 4. Here 9 minus 5. Sorry, 9 minus, this is 5. This is 4. So we have calculated these sides. Fine. Now we have to calculate these 3 sides. For that, you can see the formula is square root of 2i square minus just उसको बढ़ा देना. Sorry. Okay, just okay, 2i square minus 2 times 1 minus cos 2n minus 1 by 2n plus 1 pi. Yes, fine. Or I times whatever is this one. Now let us take this same example. So here it is I times 1 minus, what is this? Cos 60. Okay. Sorry, 2 times cos 60. So that's equal to I times 1 minus 1 minus, what is that? I 1 minus 1. No, it can't be 0. What is that? No, just 2 times It's 1. I think I've done some mistake in the formula. Actually, here it becomes 1. Sorry, root, this is 2 into. Is it not? This is 2 into. 2 into I goes out. Then 2 into 1 minus 2 cos this one. That is 2 minus 1. That is 1 by 2 into 2. It's 1. Yes, fine. It will be I. In this case, it is I. Okay. So that means these sides are IT. I into T. So T is 1 in this case. So I is 1. So that means the distance of this side is 1. This is 2 and this is 3. So we have constructed using the labeling a polygon with different sides and internal angle. Because I'll just show the one example. This is what we have discussed. Yeah, this is another one. You can see that it is not T is not 1. T here is 1.6180, etc. So that is why the sides are, these sides you can calculate using that number. This is 10, 9, 8, 6. But whereas these are 1T, 2T, 3T, 4T and 5T, where T is this. Okay, this is what we have done. And why I have taken these two applications is that I think it can be easily understood, the construction. And we all of us know that graph theory is such a wonderful subject. If you are asked to prove something, it looks very difficult. But once it is done, it can be easily understood. That is the beauty of this subject. With this, thank you one and all.
Have any time for questions? So if there are any, we can discuss during the lunch break. So please, for the moment.
इनको फोटो चाहिए, इनको फोटो चाहिए. Thank you, sir. Thank you.
So now we have lunch break, and I invite you can.
Yes.
Cover है ना उधर, cover उधर. No problem.
So with this, we end the session 2 of day 2. Thank you, P. Sadar sir, for chairing the session. I also thank our speakers, Eva ma'am and Suresh sir. Now we'll proceed for lunch, but guests can proceed to lunch, please. And for the students, for the participants who want to go on excursion, you are requested, if you want to make the payment, please make the payment at the reception. So there is a counter over there. You can pay. The trip will be on 13th. Thank you. The paper presentations will be announced after the 2 lectures. Okay. So the room numbers will be announced later on. Good afternoon, everyone. Welcome to the session 3 of day 2. Today we have 3 lectures in this session. The first will be by Professor B.S. Panda, followed by Professor Shivraj Kumar, and then in the end, Professor Mukti Acharya, which will be an online session. To chair the session, we have Professor Kiki. Professor Kiki is Associate Professor in Department of Mathematics, Faculty of Mathematics and Natural Sciences, University of Indonesia. In the starting 2013, Professor Kiki served as chair of MKA until 2017. Professor Kiki is still an active member of MKA Association and doing a lot of research in graph theory. She has published over 155 publications and has been a speaker in many of the conferences. Her area of research is matrix dimension of graphs, graphs labeling, magical labeling, and rainbow connections. I hand over the session to you, ma'am.
Thank you very much for the introduction. So good afternoon, everyone. I'm an honor for me to be the chair of this session. So we have 3 invited speakers of this session. The first speaker will be Dr. Bawani Sankar Panda. He has got his PhD from Department of Mathematics, IIT Kanpur in 1994 in algorithmic graph theory. And he has many experience. So he's visiting scientist at ISI Calcutta, and he also a lecturer and became an assistant professor in computer science department at BITS Pilani. He then served as the reader in the Department on Computer Information Science in University of Hyderabad. And he is also in Department of Computer Science and Engineering, University of Texas at Arlington, USA as a visiting researcher. He joined the Department of Mathematics, IIT Delhi as an assistant professor from 2002 and became the associate professor in October 2006. And since 13 April 2011, he became a professor. He was also the head of the Department of Mathematics until 2014. And then he also professor online from IIT Delhi, in IIT Kharagpur, sorry. And he was also GitJam Vice Chairman, IIT Delhi for GitJam 2018, 2019, and 2020. And he was part of Git 2020 organizing team as a vice chairman. His area of interest is graph theory, algorithmic graph theory, combinatorial optimization, parallel computing algorithms. His work already published in 50 research publication in journal and more than 35 research publication in conference and 3 edited volumes. And he also success as a PC co-chair on the 4th International Conference on Algorithm and Discrete Applied Mathematics, CALDAM in 2018. He also successful PC co-chair in the 11, 13, 14, 16 International Conference on Information Technology from 2008 to 2017. So today he will give the talk as a first invited talk in this session. So Professor Panda, please.
Thank you for your kind introduction. So I'll be talking about one important problem called matching problem, and that too stable matching. This is, yeah, you'll see in few slides that this is one of the very important problem, and every graph theorist should know what this problem is. Okay, so this is the graph theory audience, so I don't want to take what is a graph. So if you see this graph theory, which is, so, yeah, in the last 2-3 lectures, people are asking what are the applications and other things. And this is one topic which is full of applications. right? So you'll see where exactly these are used. And graph theory is not only by mathematicians. You must have seen the history of graph theory. It has been now developed by several people from chemistry. Then electrical engineering network theory was, network analysis was based on graphs, like Kirchhoff's theorems you must have seen. Similarly, operations research is one such field. Computer science is the major field where they develop this graph theory properly. So when you talk about applications, so in fact, I did my PhD from IIT Kanpur. And as Professor Suresh Hegde told, we have some like overlapping period. So people were asking what are the applications of this. So we'll see today in this talk one of the very important applications of graph theory. So if you see in the computer science, the Ari Tarjan is one important person, Hopcroft and Tarjan. So they got the highest award in computer science called Turing Award in 1986. And these are basically graph algorithms. So a lot of problems are there. You must have seen this leveling. Now the question is how to produce a leveling efficiently, magic leveling, anti-magic leveling. So these are the kind of problems the computer scientists they deal with. And once you have a leveling, you can look for possible applications where you can use it, right? So this person was the main person who developed a lot of theory in graphs for graph algorithm. And for example, a planarity testing, given a graph, you know what is a planar graph? But now how do you test or get a planar embedding? So that is an important problem. And it has got a lot of applications. So if you see if you are using the computer, if you open the motherboard, backside you will see which is a planar graph. So the transistors will be there, and transistor to another transistor, there will be a wire going without crossing. These wire do not cross, where these are naked wires where electricity flows. So there should not be any short circuit. So how to design this thing? So this is the important applications like VLSI design, very large scale integration where more than 10⁻³ transistor has to be put in 1 mm silicon chip. So you have to get the planar embedding. So this planarity testing is basically one of the important contribution for which we got the ACM Turing Award. And then this ICM 2010, it happened in Hyderabad. And there is a person called Daniel Spielman. He got the Nobel Prize for his contribution of application of graph theory to computer science. So you'll find numerous applications, but I'll talk about some applications also, today's talk also. So these are in computer science domain, but mathematics domain, one of this Fields medal has the age limit, but there is an important prize called Abel Prize where there is no age limit, and best contribution they get the Abel Prize. So if you see these two persons, Andre Jamaredi, he has got in 2012, he got the Abel Prize, and some of his theorems are so basic that they are in the textbook level, for regarding infinite graphs. So he got for discrete mathematics and theoretical computer science, and discrete mathematics is major part is graph theory basically. Then this is the recent one, 2021. This is the Wigderson and Lovage. Lovage's theorem you must have seen, perfect graphs. This is the problem where I worked basically for my PhD thesis. This Lovage has contributed a lot to graph theory, and Wigderson has contributed to complexity theory. And their combination of these two things, developing complexity theory and graph theory, and the interplay between these two things, for that they got the Abel Prize in 2021. So in mathematics domain as well as computer science domain, this is one of the recognized field. But is there any Nobel Prize in mathematics? Yes? Yes or no? No. So we'll see a Nobel Prize in graph theory, essentially graph theory. That is what the topic of the talk today. See, for example, 2012 Nobel Prize in economics was given to Roth and Shapley. So Gale and Shapley is the person who developed this table matching in 1962. And after that, the other authors, this is the Shapley, he developed many of the theoretical things in graph theoretic setting only. But then Roth is the person, the economist, who joined with Shapley, and they developed a lot of applications of this Gale-Shapley algorithm, stable matching algorithm, and applied to numerous situations. And for that development only, they got the Nobel Prize in 2012. So this is the prize in economic science, and this is for theory of stable allocation and practice of market design. So these are basically bipartite graphs where one side demand and suppliers are there, and they have to match it properly to all those things. So you will see some of the applications of the basic algorithm of stable matching. So see, this is a mathematician and this is an economist, and there's two whether they got Nobel Prize, and this is the area of graph theory. So if you see the applications in the economics side, most of the economics theory journal, if you see, you'll find those are basically graph theory. So if you want to, this is one area, one way to work in graph theory, that look for the work of this computer scientist and the economist who has developed the model. Then you have a graph theoretic question. You can bring that, and then you can now study and get the theoretical properties. So always you can say that, okay, this is the application and this is the theory you are going to develop. So that is the role of mathematician, that you develop the theory, the basic applications and other things, let other people are there. And if you see, like it is a collaborative work. It is not the single person who develops. So many people that do, like Shapley contributed on the theoretical aspect of that. And then the Roth and all his other students and collaborators, they developed the application part, right? And that's what they got it. So this is the article which summarizes the work of the Nobel Prize thing. So you know what is a bipartite graph? So the vertex set can be decomposed into two sets, that every edge has one end in one part and the other edge in other part. In other words, these two sets are independent sets. So we are interested in complete bipartite graph, where there is an edge between every vertex in first part to every vertex in the second part. And this models a lot of things. So what is a matching? A subset of independent edges. That means a subset of edges, no two edges have an endpoint in common. So they are not adjacent edges. So such an edge set is called a matching. And the endpoint of the matched edge, for example, this is one matching 1, 2, and 3, 4. And these points are called matched vertices, 1, 2, 3, 4. And these two edges matched every vertices. So such a matching is called perfect matching, a matching which saturates every vertex. That is possible only when the number of vertices is even. And now number of the edges in the matching will be n by 2, right? So this matching also can be described like this thing. So you have set M1, M2, Mn. These are the men's, and W1, W2, Wn. You have the women. Complete bipartite graph with equal partite sets. And matching is a subset of, this is A cross B. We are talking about A is the men, B the women. And this M of Wj is less than equal to 1. That means every man is matched with at most one woman, and every woman is matched with at most one man. So that is basically the matching. For example, matching in bipartite graph. So these are the A and this is B. So you can see M1, W2, M2, W3. This is a matching. So you have several other matchings are there. So if you take a single edge, that also is a matching. So now the question is to find out the maximum matching in graph theoretic setting. But here the problem will be slightly different. Now you have two sets. One set is men, another set is women. and each man has the preferences for the women. Every woman has a preferences for the men. So this is called matching with preferences. So preference list is given. For example, you have 2 men and 2 women. This man's preference is W1 and W2. This M2's preference is W2 and W1. So now, so this is the case, right? So in this case, we are interested in the stable matching. Stable matching is, now you have to find out an allocation. Every man should go to exactly 1 woman and the vice versa. Second thing is that, so here M1's first preference is W1 and M2's first preference is W2. Suppose M1 W2 and M2 W1 also is a matching. This is a complete bipartite graph. M1 goes to W2 and M2 goes to M1 goes to W2 and M2 goes to W1. That is also a preference. So that is a matching, but that will not be a stable matching because the preference of M1 is W1 and now W1 also prefers, M1 prefers W1 and M2 prefers W2. So if you do the other thing, so they together they will collaborate and now they will change their partners. So the matching or the marriage will not be stable. So the will formally define what is a meaning of stability. But this problem has several applications. You know, allocation of junior resident to hospitals. So after doing the MBBS, now so they are assigned to the hospitals for residentship, and there is a program in the US. You know, through that they allocate, and it was now using the Gale-Shapley algorithm. These 2 people improved that allocation scheme, and which is being used in the US, and that is one of the important contribution for which they got the Nobel Prize. Many other things we'll see. Allocation of school leaving students to colleges, allocation of students to hostels, allocation of kidney transplant patient to donors, and many more. So these are basically the market scenario. One set, there is a demand, there is a supply. You have to do it. You have to assign such a way that it is stable. Stable in the sense that they together do not go. For example, a doctor is assigned to one hospital and and another student is assigned to another hospital, but the hospital prefers this student and this student prefers the other hospital. They together will go outside the system. They will keep on exchanging, and whatever the initial allocation is there, that will collapse. So you have to do in such a way that, so this has to be a stable one. So later on they cannot go and exchange, right? So if the person wants, then the hospital will not want. So that is the case. Otherwise, everybody does like this thing, then it will collapse. The program allocation will collapse. So that is the main complaint or was there, and we'll see what that application is. So this is National Residence Matching Program. So this is one of the important program which federal government uses to allocate the doctors to residents to the different hospitals. So you can see the details. So now it was a very old data, but currently now so many more hospitals are there, doctors are there. So market operations as a central clearing house. Students apply and interview at hospital in the fall. In February, students and hospitals state their preferences. Each student submit rank order list of hospitals. So these are the students, these are the hospitals, number of seats they have. And this is basically a bipartite graph, complete bipartite graph. And after that, you have to find a matching which is stable. So let me define what is it. So this is one such important applications. Then the kidney exchange part also is being used. Right, this is the data of the US where they have used this, they have developed the software for this particular application as well, using stable matching. So the problem is what? Everyone has a preference over the possible outcomes. The goal is to find a matching and allocation of the candidates to one another, which is optimal in some sense for these preferences. So optimality can be defined in several ways. But at the moment, we will talk about stability is one of the first criteria. Later on, we'll see some other criteria. So this matching problem with preferences was first introduced by Gale and Shapley in 1962. And they introduced the stable marriage problem formally, which involves finding man-woman pair so that no individual wants to change his or allocated partner. The marriage will be stable. Do you know? That is what it claims. In the stable marriage problem, every person is matched with exactly one person of opposite sex. So this is basically 1962 papers, and that now was developed by Shapley and Roth further, and they really developed and showed that this performance of the new software is much better than the previous one, and because of this thing they got the Nobel Prize. So these are basically Roth, and this is the Shapley. Okay. So now bipartite matching with one-side preferences. So here you have two sets, two disjoint set of candidates. Each member of only one of the two sets provides a list known as the preference list. For example, say allocation of student to hostels. So the student gives the choices. So the one-side preferences. They will give which hostel they will go or which room they will go. Complete list will be given. So this is 1, 2, 3, 4. So ABCD in the other side, 1, 2, 3, 4 in the first side. And for each one in the first set, you have the complete list of preferences. This is one side preference list. Now you have two sides. Now not only this side gives the preference, the other side also gives the preferences. So this is both side preferences list. Here the previous one was bipartite setting, and many other applications are there which is can be modeled with non-bipartite or general graph, where you have single set of candidates. Each candidate provides its preference list with contains other members of the set. For example, stable roommate problem in the hostels. More than one candidate can go to the same room. So this is a roommate allocation problem, which is widely studied also. So this is 1, 2, 3, 4. If you see that they have given from this set only, right? Only one set. Okay. So we'll define what is a stable matching. And prior to that, let us see what is a blocking pair. So blocking pair with respect to a matching M. M is a matching. So this MW, M, W, this men, women. This pair is a blocking pair. So they are not matched. Currently, they are not matched to each other. And M prefers W. M would have been assigned to some W1, but W is in preference list, the higher priority than W1. So that man is not happy, right? So man prefers W over M of W, M of M, that means whatever has been assigned, or M is unmatched, or you have not given the matching. That means he has not got the partner. And W prefers M. Not only this M prefers W, W has higher priority to another man, then he cannot do anything, right? So, but in this case, W also prefers M. And if you are not assigning these pairs, and if you are assigning to other partners, this marriage will collapse, right? So this is a blocking pair. Such a thing is called blocking pair. So, for example, this particular setup, 1 is assigned to B, 2 is assigned to A, 3 is assigned to D, and A, B, C, D, and 4 is assigned to C. A goes to 2, B goes to 1, C goes to 4. So 4C is assigned D. So in this particular setup, can you see that this allocation is a good allocation, or some pair is still unhappy? One has go to B because it has got the highest priority. So you cannot do, and B, but B's case, if you see, it has gone to the last preference, right? So if you see, let's see, this is 4A is a blocking pair, where this is 4 is assigned to C, but 4 prefers A. A is in the higher priority for 4. And if you go to the A, now A has been assigned to 2, but 4 is in higher priority. So they together they will collaborate and they will dismantle this assignment, right? So 4A is a blocking pair. So a matching which is doesn't have any blocking pair is called a stable matching. So a matching M is said to be stable if it has no blocking pair. So now the question is, given this complete bipartite graph, that means every man has preference list, complete preference list, every woman has complete preference list, whether such a matching, stable matching exists or not. It exists means everybody will be happy. Outside the system, they cannot now dismantle it, right? So that is the main thing. And now the question is, if so, then how do we find? Gale-Shapley showed that, yes, it is possible always. And they gave an algorithm construction that this is the way it is the case. So these days, if you ask any of the young men, boys and girls, whatever they will do naturally, that is what Gale-Shapley has done. Nothing more than that. So we'll see, I'll illustrate that one. But now this is the scenario. I'll come back to this stable matching algorithm I'll explain. But now what are the other things in applications or maybe in real world is that this is too much to ask that every person has to give the complete list of preferences. For example, our JE or the counseling that takes place in IT admission, every student now is presented with the available colleges and seats, and they give the preferences, but they are not supposed to give the complete preference. Maybe 20, 30 they give and other things they stop it, right? So the preference list may be incomplete. And I do not, it doesn't matter if I get A or B, one of them is okay for me and I have the same priority. So then ties are also there. So there's the real world situation. So stable matching and their preferences. This is a complete one. Let's see. Okay, so we'll see these different variations which are studied in the literature and which is of practical importance. So different variations of the stable matching will be there. But prior to that, let me see. Okay, so what this n men's and women's are there, complete preference list is there. We find a stable matching in this instance, and existence of the stable matching in SM is implied by the classical Gale-Shapley algorithm. They gave an algorithm, always it produces a stable matching, so existence is guaranteed. So let me, and this appeared in this journal. So okay, I'll come back to this algorithm, but let me explain this algorithm. This is very easy one. So now you start with men's part, and now the men and women are ordered. M1, M2, Mn, W1, W2, Wn. You start with M1. M1 is going to propose to a girl, and girl may accept or reject. If when it is going to, suppose nobody has matched, the girl has not got any matched one, then it is going to accept it temporarily. But girls are also smart. The moment they get a better person, immediately they'll reject, right? They accept the new one and reject this person. This person has to, once again, you have to start proposing it. So that is the idea. So what it does, WB, M's most preferred woman to whom M has not proposed yet. So M proposes to W. If W is free, that means it has not got the partner, then M is matched to W temporarily. Else, suppose W is already matched to somebody Now W prefers M to her current partner M dash. If that is the case, then M is matched to W and M dash becomes free. So it's that it go. So this is my higher priority, right? Else W rejects it. Suppose W has got the highest priority 1 and some low priority person proposes, so that reject it. And yes. This, yeah, of course we can do all those things also. But Indian scenario, it will not work because people are confused. Today you are assigned, tomorrow you say, no, I didn't give the preferences correctly. That's the problem, right? So here you have to give the preferences. So let me see, okay, I'll come back to this one, theory. So let's see the example. So if I iterate from the, this is men dominated, so men side only it is the case, but I'll come back to the women side later. So here we start. One is preference is BC, BACD. So once is starting, so whom it is going to propose? B. So one proposes B. B has not got any partner. So what is going to do? It is going to accept it. So B accepts. Temporarily it is, of course. Okay. And but B's case, there is a chance that B's last priority is 1. Right. So there is a chance that it may say no, reject, and the latter point of. Now then 2 will propose to A. Right. A has not got the partner, so A accepts. Right. Up to this point is fine. So this green color you can see. Then 3, he proposes D. 3 proposes D, and D has not been assigned to anybody, so D also accepts it. Right. Then when it comes to 4 proposes A. A has got whom? 2. A has temporarily got assigned to 2, but now A's list, if you see, 2 is the last one and 4 is slightly higher priority. So he'll say that no, I'll accept 4, right? So A accepts and men 2 becomes free, right? The boy is free now. Then he'll come again, you start with the higher to lower. So 2, so A is gone. So next person is C. It's going to propose C. 2 proposes C, but what about C? C has not been assigned to anybody, right? So C accepts, right? So now all the people have been now, they got the partner. And there is no boy is now proposing because they have got their highest preferred partner. So now you stop. That is a stable matching. And that is what it happens in practice. If you ask the boys and girls of these days, like school mates, they will solve it. And this is what they did it. And eventually it got the Nobel Prize. It's and its variations, basically. Its applications, you know. But now, who will be happy in this algorithm? Men will be happy because we have not started with women. So if you wish, you can start with this side, right? Depending on what is the priority, right? So these are representative only boy and girl, but actually these are items, demand, supply, and other thing. Which is more important, you can start from that side. But still, this is you can satisfy one set of people, not the both sides. That is the problem with this. So what will be the natural question a mathematician will ask? Popular matching, right? Which will, you have to define what is your loss function or optimizing function. So find a matching which maximizes this function, right? Happiness of many people, it's now maximizes, or maximum number of people are happy. Then this is called popular matching. And this is the current area of research. And these problems turn out to be very hard, whereas stable matching is a slightly easier problem, right? So this is basically stable matching. You will find in a graph theory book, also it is there. If it's a DBS book, also it is written, because this is one of the very important problem. And this is what graph theorists should be proud of, saying that, okay, not like this has led to a Nobel Prize, right? But now this is a big field of research as well. I'll indicate some of the problem. So what happens? Ties are there. So for example, in this case, B and C are irrelevant. Order is irrelevant. You get B or C. Similarly, here A, B, C with the same priority. This is the case. So in presence of ties, the stability criteria that we are dealing with is called weakly stability in the literature. And this was introduced by Irving in 1994, discrete applied mathematics. So this is stable matching with ties. Now, what happens? The list is incomplete. Complete preference list is not there. So this is basically stable matching with ties as well as the list is incomplete. So under what condition it will happen? So one may propose A, but A's preference, okay, one A and is acceptable if A is present in one list and vice versa. For example, one A is there, for example, two C, two proposes to C, C also is there, two proposes to A, three proposes to B also is there. Okay. So if the other side, this preference is not there, this will not be acceptable. This is only one-sided, right? Both sides mutual agreement should be there. Then only you can take this as a matching edge. So that is the difficulty. So if the moment you put it, and the preference list which are consecutive. So you have an ordering of the man, you have an ordering of the woman. So this preference list, so M W2 to W5. That means in between you cannot leave anything. All your preference will be consecutive, right? So have you heard of something, this kind of thing in graph theory? There is something called convex bipartite graph, right? So if you see, most of the problem, even domination problem is NP hard for bipartite graph. So you need graph classes where you can solve these problems efficiently. And one of the important class of graph is called convex bipartite graph, where you can order the vertices of X part, Y part, so that the neighbor of every element in X is consecutive. Similarly, neighbor of, this is one side convex, biconvex, this is convex. Biconvex means you can order X and Y both sides. So the neighbor of each vertex in X is consecutive in Y, and every vertex in Y also is consecutive in X with respect to that ordering. So this is called biconvex graph. The moment you restrict graph to biconvex graph, most of the problem also can be solved in polynomial time. So these are basically widely studied subclasses of bipartite graphs. So this is the consecutive ordering. Another is inclusion, right? So in the society there is hierarchy. So if this person, man, wants these two women, then this is a higher, maybe influential person. Not only he will, his preference lists are this, maybe slightly more, right? So one is a subset of this. So this preference list of M1 is a subset of preference list of M2, is subset of preference list of Mn, and women also preference list of W1 is a superset of preference list of this, and this is one instance. So these are the things which appears in the real life applications. That's why these problems have been studied in the literature. So with this particular stating, and then state this preference list of MI is equal to all Wj, j less than equal to I. So W1, W2, W2. So preference list of M1 will be only W1, M2 it will be W1, W2, M3 it is W1, W2, W3, Mn is equal to this thing. So if you see the only preference list, if you take and draw a graph, so this graph is becoming a something called chain graph, which is a bipartite graph, right? So okay. Okay, before going to this thing, okay, let me see this one, the stable matching, where it works well. I have illustrated it, but this is the theorem. Okay, so this proposal, this complexity of this stable matching algorithm is order of n square. So how it is the case? At most n square iteration of the outer loop. For example, each iteration a man proposes to someone to whom he has never proposed before. So how many women are there? At most n women are there. So it can, in one iteration, it can go first, second, third, and other thing. It can propose just this n step. And then each iteration, and then how many iterations are there? N iterations. Because once you reject, some are accepted, and this person is now initially it is assigned. For example, if you take a man 1, will be temporarily will get a partner. Man 2, if it is rejected, then now man 1 will be free. So next time you start with man 1. So next iteration he'll get it. So how many times it can be rejected? N minus 1 times, right? So another time he is going to get a partner because n women are there, right? So in n square proposal, the algorithm will terminate, and there is no blocking pair for this particular matching. So you have to prove the correctness as well, right? So assume that MW is a blocking pair. M never proposed to W. This is the first case. Second case is M has proposed to W. Because this MW is a blocking pair, that means M has not got W, right? W has not been assigned to M. So M either has proposed and W has rejected, or M has not proposed. There are two cases. So first case, M never proposed to W. So M cannot be unmatched. Because the algorithm, as long as somebody is not, some girl is not proposed by a man, the algorithm will keep on running. So in that case, M must be matched with something W1. So as algorithm would not terminate, so men propose in the order of preference, hence M must be matched with a woman. He prefers to W. So MW is not a blocking pair because M prefers W than the other. So in that case, M has not proposed to W. That means he has been assigned W1, so which is of higher priority because in priority wise he is going to propose. So he has got a person, woman of higher priority. So the MW cannot be a blocking pair in this particular case. M has already proposed to W. So W is highest priority, higher priority, but whatever has been assigned to him is W1, which is lower priority. So W must have rejected M at some point. Women only reject to get better partners. So W must be matched at the end with partner she prefers to M. So MW is not a blocking pair because M would have got some W1, but see, W doesn't prefer M. W has been assigned. If W has not been assigned, then the man would have whenever he proposed, the woman would have accepted it. But now W would have got some M1, which is a higher priority. So MW cannot be a blocking pair. Right? So this is the correctness of the algorithm. Okay, now I'll go back to the variations. Okay. This SMTI, that means stable matching tie and incomplete list. So in this particular case, so in that case, it may contain stable matching of different sizes. The question is how to get the maximum cardinality or minimum cardinality. One can ask these questions for this particular thing. And given an integer k, it decide whether there exists a stable matching of cardinality at least k, that means greater than or equal to k. So this is the decision function. And the decide mean SMTI is you have to find out, given a k, whether there is a stable matching of cardinality at most k in this particular setup, where incomplete and ties are there. So this is SM problem, stable matching with tie also can be solved in order of n square. Complete list, but ties are there. So in that case, you can break the tie in some particular order, and now you use the stable matching algorithm, Gale-Shapley, that can be shown that solves this particular problem, and hence order of n square. But the stable matching tie and incomplete list, then this is a difficult scenario. So in that case, the problem becomes NP complete to check whether this instance admits a stable matching of cardinality greater than or equal to K, whether at least K pair can be assigned. That is difficult to decide. So that becomes an NP complete problem. So one can look for special cases where you can solve it, or you can look for approximation algorithm of the optimization problem. Many other variations are also there. And tomorrow, if you find out some applications where certain kind of ordering or certain restrictions on the men and women are first set to second set, some restrictions are there, then you have a new variations of stable matching. You can study the existence, uniqueness, then find out the optimal solutions and look for solving that application. So you have got another set of applications of this. Okay, so you can see this Irving, this is the B, this part has been solved by this Irving. Menlove and others have shown that this problem is NP complete, this and the other things, right? So this complete SMTI, that means stable matching, ties are there, list is incomplete, ties, incomplete list, and step is also there. That means less than equal to I. So in that case, okay, so if this is the case, if you see this one, the step is not there. So this part is not there. Com SMTI is NP complete. So you cannot solve this problem unless P is equal to NP. So you put restriction that, okay, what happens if the step is included over there? So you restrict the preference list that less than equal to I only for MI, at the most M1, W1, W2, WI. Beyond that is not allowed. So if that is the case, also this problem, now this problem can be solved in order of n squared time, quadratic time. And this is what we solve. This Sachin is one my PhD student, and this is a joint work, right? And yeah, this result now appeared in this lecture note in computer science, and then it has been submitted for a journal publication. And then if you see that SMTI with C is consecutive. So the man wants WI and least is WI and maximum is WJ. In between everything, the man should be there in the preference list. So consecutive. So if that is the case, even if you add this extra condition, this problem remains NP complete, right? So still difficult. So the clue is that you can put some natural conditions using which you can solve the problem, or you look for some approximate solution. Okay, how much time I have? 5 minutes. Okay. So the objective of this talk is to introduce the problem and create some interest. This lecture is there, and you can find out on the online these papers. If you want to study further, you can study it, but little bit maybe give the idea, proof idea of this thing. So what happens? Okay, see, for example, any good problem with good applications in graph theory, you will find those problems are hard problems, right? So there is a book, Gary and Johnson, The Theory of NP Completeness, right? So this computer interactability and the theory of NP completeness. The book is PDF copy is available. So several now today, if you see thousands of graph theoretic problems are NP complete. So the Johnson maintains a website where it lists out only graph theory problem you can see. You can now study those things in different setup. So there is something called exact maximal matching, where preference list is not there. So you have a bipartite graph, and K is an integer, and you ask whether there is a matching, maximal matching of cardinality exactly K. Maximal means you cannot add one more edge. to make it a matching. So this problem is a hard problem. The minimization of matching problem is a hard problem. Minimal maximal matching, maximum maximal matching is easily solvable. So there are a lot of beautiful theories there of matching problem. If you look at any graph theory book, undergraduate book, like D.B. West book, there is a important chapter called matching. You'll find very, very celebrated theorems regarding matching, like Borg's theorem, right? Okay. So now this problem is already known to be NP complete. So what I mean to say is that if you are doing in graph theory also, pure graph theory, you must understand what is the meaning of NP complete. What is the consequence of this? The moment the problem is shown to be NP complete, then you don't expect a good characterization. It is not, unless otherwise P is equal to NP, which is not going to happen possibly. So you will not find a good characterization. For example, see Hamiltonian graph, Eulerian graph, you have a good characterization. A graph is connected, graph is Eulerian, you can only degree of each vertex is even, and you can find a Eulerian circuit also. But Hamiltonian graph, you have lot of sufficient condition, not of necessary condition, but good like non-trivial characterization you do not have. So for that, what do? You look for some parameters, longest cycle is n, then it is Hamiltonian. So you find out, maximize the cycle length, or can get some bounds. So the bounds, you find graph theoretic paper, so many bounds people have obtained. So why do you look for bounds? Why do you look for bounds? Yes? Other people are finding bounds, that's why you find bounds, right? No, why do you estimate that? Right. Okay, 1 minute. Okay, I don't have much time, but I'll tell you. This is important. Mathematicians don't do like this, you should understand, the beginners. So it has got good implication. If you design good approximation algorithm, then you need to use those bounds. We have designed a lot of approximation algorithm, and in Indian graph theorist who are there, Sampath Kumar, has initially paper, he has given a lot of bounds. We have used those bounds to design good approximation algorithm, right? So that is the motivation why one should design this thing. So you should know how to do this particular thing. That okay, and this reduction is easy for a mathematician. It is very easy to understand what is NP complete. Nothing great. So what you do, given an instance, given a graph and an integer k, from this setup you have to construct another graph in such a way that this graph has a maximal matching of cardinality exactly k, if and only this problem is an yes instance, means this admits a solution. So those necessary and sufficient conditions you would have done in many of the thing, right? Characterization. This is very easy. Only thing that you have to understand this thing, and then you can do some meaningful research which has got applications. People are asking about applications. So I think my time is up, but there is a book. I think it's not going. You go to the last one. Last one, references I will show you. Okay, I think it's going right. Or you have to do. Okay. So these are basically little bit technical thing, but it is not difficult to understand. But let me see the. Okay, so for example, so this is what basically 3x2 approximation algorithm that we have done, and let me see. Oh, I don't have this thing. I don't see, there is an important book matching with preferences that you can see. I think soft copy is available in the net, right, web. So you can download, and if you are interested, you can see lot many variations, but you can now study the graph theoretic aspect of that, right? Then you can. Okay, thank you. If you have any question, then you can enter.
It's a really nice talk. Thank you very much. But I'm sorry we run out the time. So if you have question or a remark for Professor Panda, you can like ask by yourself at the break time.
Yeah. So you can see, I'm in IIT Delhi. So you can see my numbers or email from my website. If you have any queries, of course, in IIT Delhi, there is a summer research faculty fellowship program. So in summer, you can visit for 2 months. IIT will give all the supports. So this is open for lecturers basically, or assistant professor who are in job. You can apply, and if you are interested, then you can come and work with us. Thank you.
We continue for the next session. So the next speaker will be Dr. Sivaraj Kumar. Okay, so I will read his CV while he's preparing. So he was completed his Bachelor of Science in Physics, Mathematics, and Computer Science from Yuva Raja College, Missouri in 2005.
Please, participants, don't leave, as the presentations will start later on after this lecture. So all are requested to be seated here. So sorry, ma'am, for just disturbing, because everyone was leaving. So I just wanted to make this announcement.
Okay. It's okay? Yeah. So Dr. Sivaraj Kumar have his PhD from Department of Mathematics and IT Suratkal in 2012 with supervision of Professor Hegde, and his PhD thesis mainly dealt with the proof of tree conjecture on graceful digraph. And he was a postdoctoral fellow in IISc Bengaluru, and during his stay in IISc, he worked on the distribution of quadratic residues modulo prime P with Professor Sunir Chandran and Dr. Siddharth Barman. Currently, he is an associate professor in Department of Mathematics at the National Institute of Engineering in Mysuru, and also he worked as associate professor at GSSSIETW, and also he worked as assistant professor at MIT Manipal from September 2016 to December 2016, also in Falachil, Mangalore, and also in SD MIT Ujire. He is a life member in Indian Society for Technical Education and Academy of Discrete Mathematics and Application. His research is combinatoric. He has several publications in international journal, and he has got several awards. So he was honored with the best paper, for the best paper award during the National Meet of Research Scholar in Mathematical Sciences in 2010 at IIT Madras. And also he awarded the NBHM and the Dr. D.S. Kotari postdoctoral fellowship. So Dr. Sivaraj Kumar, please.
Am I audible? Oh. Thank you, madam. First of all, my belated New Year wishes to all of you. And in the morning, Professor Hegde have already given a very nice introduction about graph labelings and its applications. And also Professor Andrea discussed about the magic labeling for digraphs. So in this talk, I will discuss about graceful labeling of digraphs. In particular, I discuss about proof of tree conjectures in the theory of graceful digraphs. So how do I move it? Now it works.
For pointer, for forward, for backward, for pointer.
Not working. Ah, it's working now. Okay, so in the year 1985, Bloom and Su have extended the idea of graceful labeling of undirected graph to a directed graph in the following way. So here, suppose D is a digraph with Q number of edges or Q number of directed edges. Now assign to each vertex a different number from the set 0 to Q. I mean, essentially, we expect a one-to-one mapping from the vertex set to the set 0 to Q. And the label on the edge, I mean, here it is a directed edge. The arc UV indicates U is directed to V. And the label on the edge is given by, directed edge is given by G of V minus G of U, modulo Q plus 1. If all arc values are distinct, then we say that it is graceful. Essentially here, when it comes to the directed edge, we expect both one-to-one and onto mapping. So then we say that it is graceful. For example, if we consider the unidirectional cycle, unidirectional cycle means the in degree and out degree of each vertex is 1. So here there are 6 edges. Therefore, we use Z7 to label the vertices. Here all vertices are distinct, 0, the labels 0, 6, 1, 4, 2, and 3. And the directed edge labels are defined like this: 6 minus 0, because arc UV. So G of V minus G of U, therefore 6 minus 0 is 6. And then 1 minus 6 is minus 5. So minus 5 under modulo 7 is 2, and so on. So it is graceful. Here, since we are using the set ZQ to label the vertices and edges of the directed graph, and ZQ is a cyclic group. Hence, we can expect some nice algebraic characterizations of graceful digraphs. And in a way, Bloom and Su are very successful to come up with some nice algebraic characterizations. To name a few, one such characterization is this. The unidirectional path, I mean the path where all internal vertices have in degree and out degree 1. The unidirectional path is graceful if and only if Zn is sequentiable. The group Zn is sequentiable. So in general, suppose G is a finite group of order n under the binary operation star. Now G is said to be sequentiable if I am able to arrange the elements of the group in this form. So I will fix S0 to be identity element of the group G, and S1, S2, Sn minus 1, I will put it in this way. So D0 is S0, and D1 should be S0 star S1. I mean, I consider the product of those sequence, S0, S1 to Sn minus 1, then I should end up with D1, D2, etc., Dn minus 1. All of them should be distinct. Then we can call it the group is sequentiable. And basically, if the group Zn is sequentiable, then we end up with the graceful labeling for the unidirectional path. So here is the example. Suppose I fix S0 to be identity element, and S1, S2, S8 are the numbers. It follows this sequence 1, 6, 3, 4, etc., 7. And I put it on the edges. And consequently, I end up with the labeling on the vertices as well. Here, 1 is basically sum of 1 plus 0. Similarly, 7 is sum of 6 plus 1. Similarly, 2 is sum of 6 plus 3 plus 1, and so on. So I basically end up with a graceful labeling for the unidirectional path if it is sequentiable. And another important characterization is this. If suppose we have a disjoint union of unicycles, say there are S number of unicycles, maybe I will put it on the board. Suppose I have so S number of so on. So these are It's better, yeah, I will use hands. Even it's not working. Okay, so etc. I have S number of disjoint cycles, in fact, unidirectional cycles. This has length, say K1. I mean, then there are K number of edges. This has K2, etc. Ks, number of edges. Now, in order to say that it is graceful, I mean, assume that the total number of edges in this diagram have, say, some E. Then I should use, the group ZE plus 1 to label the vertices. And now, in order to say that it is graceful, I should be able to partition the set into disjoint subsets, S number of disjoint subsets, so that I should be put it in the cyclic sequences. And if I consider the differences, then again I should end up with the non-identity elements of the group. Say, suppose this is G11, this is G12, G13, etc. Similarly, this is G21, G22, G23, etc. And similarly, here it is GK1, GK2, etc. If I consider all these cyclic sequences, G11, G12, G1K, K1, in fact, and here G21, G22, etc., G2K2, etc., GK1, GK2, etc., GKS. So these are basically the non-identity elements of the group, and they are distinct. These are cyclic sequences. And if I consider the difference, then I should end up with the labels on the directed edges. And again, if these differences are the non-identity elements of the group, then I can call it is graceful. And in fact, it is called K,1 complete mapping of the group G. So that is how it is defined. Maybe again, it is not working. Next one. No, next one, not the previous. Yeah. So K,1 complete mapping is this. Basically, we have to partition the set, the group, non-identity element of the group G into S cyclic sequences and their difference. Their differences should comprise the non-identity element of the group G again. And if the group G is, Z, I mean, ZE plus 1, then we say that it is graceful. And also Bloom and Su have made another, this is the example. Here we have two disjoint copies of unidirectional cycles, and there are basically 8 in total, 8 directed edges. Therefore, we should use Z9 to label the vertices. And here is the cyclic sequences. No. So 184 is one sequence having length 3. I put it in the vertices of the first cycle. And the second sequence 2, 3, 6, 5, 7, I put it in the second unidirectional vertices of the second unicycle. And if you consider the differences, again I end up with the non-identity elements of the group Z9. So yeah, that proves that it is graceful. And Bloom and Su also have made another important characterization. We all know the graph WN, the wheel, have n plus 1 vertices and 2n number of edges. I mean, n plus 1 vertices means the central vertex, and there are n vertices on the rim of the cycle. Since it has 2n edges, we have to label the vertices of the graph by using Z2n plus 1. And if 2n plus 1 is a prime, then we end up with ZP, and ZP have quadratic residues. Therefore, yeah, Bloom and Su have used the quadratic residues to label the vertices of the directed wheel, and somehow they find the labels on the edges and they are distinct. Hence, it proves that the WP, I mean W2n plus 1, where 2n plus 1 is a prime P, then it is graceful. But still, they are unable to find the graceful labeling for Wn when n equal to 6 and 10. Though it is a very small class of graph, they are not able to find it. Then later in 2006, Alison Marr have, or she was able to find the graceful labeling for n equal to 6, but unable to find the graceful labeling for n equal to 10. And Bloom and Su have made the following conjecture, that is all unicyclic wheels are graceful. And also, yeah, in this theory of graceful digraphs, we have some more nice conjectures. This is by Zhao Lingiki in 2008. So he conjectured that, if n is even and if m is greater than 14, then the digraph n dash cm is graceful. Maybe I will define the structure of the graph soon. And similarly, in the year 1994, Du and Son conjectured that for any n even and any integer m, the digraph n dot cm is graceful. We have proved all these three conjectures when I was a PhD student under the guidance of Professor Egde. So our first impression on this problem is the following. So normally in labeling problem, they try to label the vertices first. They try to fix the labels on the vertices, and then they fix the labels on the edges. But here we did the other way around. So here we try to fix the label on the edges first, and then the vertex labels are automatic. So the problem of finding the graceful labeling of digraph hence boils down to just fix the labels on the edges according to the structure of the digraph. That is what we did. So by using this idea, our first result on this problem, the theory of graceful digraphs, is this. A balanced digraph. I mean, the balanced digraph means it is a digraph where the in degree and out degree of each vertex is same. Then we say that it is balanced. And if a digraph is balanced and it is graceful, then the number of arcs in the digraph should be even. So that is our first result on the theory of graceful digraphs. The idea is this. To prove this, let me consider the following example. Maybe, yeah, this looks better. If we consider a unidirectional cycle, I mean, the number of, the in degree and out degree of each vertex is same. It is balanced digraph. If you consider this unidirectional cycle and assume this unidirectional cycle is graceful. If it is graceful, then A2 minus A1, all elements are from Zn plus 1, essentially. A2 minus A1 should be congruent to B1, modulo n plus 1. Similarly, A3 minus A2 should be congruent to B2, modulo n plus 1, and so on. So essentially, we end up with this system of simultaneous congruences. Therefore, the problem of finding graceful labeling boils down to solve this system of simultaneous congruences, essentially. Now, if you look at this, if you look at the left-hand side of this, if you look at the left-hand side of the simultaneous congruences, if we add them, we end up with 0. Why? Because in degree, out degree are same. Therefore, everything gets cancels, and we end up with 0. And now, if we want a solution for this system of simultaneous congruences, then the right-hand side also should add up to 0. I mean, the sum of the edge labels. So that is, B1, sum of B1, B2, B3, etc., Bn minus 1, all should add up to 0, modulo n plus 1. Then only we can expect a solution for this system of simultaneous congruences. Hence, from this system of simultaneous congruences, we can easily say that the cycle Cn is graceful only if the number of edges is even, otherwise not, right? Why? Because the right-hand side should add up to 0. It happens only if n plus 1 is odd. If n plus 1 is odd, every number will have an additive inverse. They add up to 0. If n plus 1 is even, then we have a mid element n plus 1 by 2. It is not having an additive inverse. Therefore, we end up with non-zero number on the right-hand side. Hence, it is not 0. Therefore, if you want a graceful labeling for a balanced digraph, then the number of arcs should be even. So that is our first result on the theory of graceful digraphs. Now using this idea, let us discuss about proof of these three conjectures. the unicyclic wheels N-CM and N.CM. So here, yeah, let me define the structure of this directed wheel first. So directed wheel is said to be outspoken if, yeah, all edges point out from the hub towards the rim, the central vertex. And we say that it is inspoken if all the direction should towards the hub from the rim. And if the rim has a unidirectional cycle, then we say that it is unidirectional outspoken or unidirectional inspoken wheels. And here, to prove this conjecture, again consider the system of simultaneous congruences governed by this directed wheel. For that, let me consider the following example. So W6, it is outspoken unicyclic wheels. Here, assume that this digraph is graceful. Then A0, A1, etc., A6 are vertex labels, and B1, B2, etc., B6 are the labels on the spokes, and B7, etc., B12 are the labels on the rim of the cycle, unidirectional cycle. Now, this is the corresponding system of simultaneous congruences. Now, here we have already seen that this unicycle, if you add the labels on the edges of the unicycle, then it should add up to 0. That we have already seen. But this is just a necessary condition. Now, what is sufficient? So then another interesting fact is this. The sum of the labels on the edges of the unicycle is 0. And the sum of the labels on the edges of the spokes is also 0. Why? Because Z2n plus 1 in general is an odd number. It adds up to 0 because we have 2n number of edges in the wheel. If you add all the edge values, it adds up to 0 basically. And already we have seen that the labels on the unicycle is 0. Hence, the sum of the labels on the edges of the spokes is also 0. If you look at this system of simultaneous congruences, it is more evident. Here A2 get cancels, A3 cancels, and A1 get cancelled, since B7 plus B8 up to B12, they are the labels on the spokes, it adds up to 0. Similarly, since B1 to B12, if you add them, it is 0. Therefore, B1 plus B2 up to B6 also should add up to 0. This is the first necessary condition. But it is not sufficient. It is just says that, yeah, the number of edges should be even. But now, in the second stage, the arrangement coming to picture. So now the question is how to arrange these numbers from 1 to 12 so that we should end up with a graceful labeling for W6. Right? If you look at this system of simultaneous congruences very closely, if you look at this, if I subtract these two expressions, I mean I subtract A2 minus A0 from A1 minus A0. If I subtract it, A0 get cancels. I end up with A2 minus A1. And I already have A2 minus A1 here. So this A2 minus A1 should be, I mean B7 should be equal to B2 minus B1. Therefore here B2 minus B1 should be equal to B7. Then only, similarly, if I subtract, so B3 minus B2, if I consider, then I should end up with B8. Similarly, B4 minus B3 should be equal to B9. Similarly, B5 minus B4 equal to B10 and so on. So if I am able to arrange those numbers, essentially what I do is I partition the set Z2n plus 1. So I have a set Z2n plus 1. So this is my set. I consider, in fact, the non-zero elements of Z2n plus 1. I partition this set into two disjoint subsets, correct? And the first subset actually occupies the labels on the spokes. Their sum should add up to 0. Similarly, since the sum of the labels on this spokes is 0, the sum of the labels on the unidirectional cycle is also 0. Basically, if I am able to partition the set into two disjoint subsets, they are 0. And then I should arrange, suppose these two numbers, if I consider these differences, then the differences should fall in this set. Similarly, if I consider the differences of these two numbers, the difference should fall in this set. If I am able to find such a partition, then I end up with a graceful labeling for Wn. That's the whole idea. So for that, we have divided the proof into 4 different cases. In the first case, yeah, this is what I was saying. Yeah, this is the graceful labeling for W6. Using that idea, we are able to prove that W6 is graceful. Here we can look at this 5 minus 1 is 4. Similarly, 3 minus 5 is 11. 10 minus 3 is 7. And 12 minus 10 is 2, and so on. So this is the graceful labeling for W6. And here I am not bothered about the vertex labels, because once I am able to fix the labels on the edges, directed edges, vertex labels are automatic. We don't need to worry about it. So, and this is the graceful labeling for W10. So here also, yeah, 9 minus 1 is 8. 3 minus 9 is minus 6. Under 21, it should be 15, and so on. So here, if you look at this digraph, here this is the idea. See, my goal is to partition the whole set into 2 disjoint subsets where the sum should be 0. For that, what I do is, anyway, if n is even, if the Wn n is even, I can, so each subset should contain n number of elements, and n is even. Okay. So basically, what I have Z2n plus 1, this minus 0. I can partition this set into 2 disjoint subsets, as I have already mentioned, and I have elements here. Their sum is 0, and here these are the labels on these ports. If I consider this difference, these 2 numbers, I should end up with a number in this set. Consider the difference of these 2 numbers, I should end up with the next number, and so on. This is the necessary and sufficient condition. But suppose if n is even, anyway, this sum should add up to 0. To find, a subset where sum is 0, what I do is I just consider odd numbers. First odd numbers, I mean 1, 3, 5, 7, etc. n by 2, the floor or seal, whatever. And then I consider their additive inverses. Then I end up with 0 essentially. Similarly, here I consider another second half of odd numbers and their additive inverses. I end up with 0. So that is how we partition the set into 2 disjoint subsets. Maybe in this diagram we can check it out. Here in the first half, the spokes 1, then 3, and then 5. I just give a break and put as a start, give the numbers, and then I will come back and assign 7 and 9. Similarly, here from this side, I will start the even numbers, their additive inverses, 12, and I will give a break, and then 14, and then I will give a break, and 16. And the remaining even integers, I will arrange 18 and 20. And if I consider the differences, I will end up with the graceful labeling for W10. That's the whole idea. That is what we did for all 4 different cases. So this is how we partition, and this is the algorithm to label the vertices of the unidirectional wheel. And once the outspoken wheel is graceful, the inspoken is also graceful. Just interchange the roles of the direction. That gives us the graceful labeling for inspoken unicyclic wheel as well. Now let us move on to the next conjecture. This is all about the digraph n-cm. Here n is even, and first let me define what is this n-cm. So basically we have n copies of cycles with one common arc. For example, here there are 3 copies of unidirectional cycles of length 7 with one common arc. So they asked us to prove this conjecture. If n is even and if m is greater than 14, is the digraph is graceful. For till m14, they have proved it. I forgot to mention those results. But Zhao Lingiki have a very nice necessary condition for this problem. If you want to have a graceful labeling for the digraph n-cm, then n into m should be a multiple of 2. Then only we can end up with a graceful labeling for this digraph. Otherwise, one cannot. So these are the existing results. And to prove this, what we do is essentially, again, one has to partition the whole set into disjoint subsets. That's the whole point. Maybe we have, say, this is the common edge, and these are my cycles. the unidirectional cycles. Maybe I will put similarly, I have another copy. Yes. Yes. Maybe here I have so many edges, but their length should be same. That's the whole idea. I have so many copies. Again, here, if we consider the corresponding system of simultaneous congruences, first let us fix the number of edges, and then we can see how what is the equation we end up with. Here, essentially, what we have is there are n. This is n dash cm basically. In each cycle we have m number of edges, but we have a common arc. Therefore, the set. So can you guess what is the set we are going to use to label the vertices of this diagram? What is the number here? What is the total number of vertices of the, what is the total number of edges of this diagram? Any idea? Here there are how many? So there are n copies of Cm. Therefore, this is m minus m minus 1. Each time I should use this. That's the problem. So there are m minus 1. M minus 1 refers to this unidirectional path. This unidirectional path is having the length m minus 1 with one common arc. I will consider it later. How many copies are there? There are n copies, and plus this one common edge and plus 1. So essentially we should consider this set Zm minus 1 into n plus 2 to label the vertices of the diagram. Right now, if I want to prove that it is graceful, one should partition this set, this whole set, because I should not consider 0 to label the edges. I should be able to partition this set into m number of disjoint subsets, basically, right? So m number of disjoint subsets, and each set should have m minus 1 number of elements. Why? Because I have to label the edges of this unidirectional path. If I forget, suppose for a moment, if you forget this common edge, I end up with a unidirectional path here, and this unidirectional path is having a length m minus 1. Therefore, if I am able to partition the whole set into n number of disjoint subsets, each set will having m minus 1 elements, right? And this sum, the sum plus the label on this common arc should add up to 0, because it altogether forms a unidirectional cycle, and hence the sum should be congruent to 0. Similarly, if I consider the sum of the labels on the edges of this unidirectional path plus this common arc, that also should add up to 0, because it forms a unidirectional cycle. It is a unidirectional cycle, hence in degree out degree is same, and it add up to 0 basically. Therefore, the sum of the labels on the edges should add up to 0. Similarly, with all these n copies, I should be able to partition the set into disjoint subsets, and the moment I add this with label on this common arc, it should add up to 0. This is the whole idea. This is the necessary condition to say that whether this digraph is graceful or not. But if I write a system of simultaneous congruence governed by this digraph, I end up with this equation. So this maybe this 2m here, 2m refers to, I just divide the proof into two different cases. One is m is even and the other one is m is odd. So for the sake of simplification, I just, instead of m, I am using 2m. So if I add, the system of simultaneous congruences, everything everything add up to 0, because the in degree and out degree here, it is same everywhere. The in degree and out degree in this unidirectional path is same, therefore it boils down to 0. Only thing, yeah, here the in degree and out degree is quite different. That is why we end up with this simultaneous congruences. Now, my goal is to first fix the label on this edge, this common arc, right? So to fix this, I have to solve this simultaneous congruence. So here, n minus 1 into a1 minus a2m, that is a1 refers to the label on this vertex. This is a1 and this is a2m, right? So now if I want to solve it, anyway, we know that n is even. Therefore, this n into this number will be congruent to 0. It absorbed by this 2m minus 1 into n plus 2. Hence, we end up with minus of a1 minus a2m is congruent to this number. And we have already seen 2m minus 1 into n plus 2 is an even number. If you add all those edge labels, we end up with only the middle element because the middle element will not be having the additive inverse. Therefore, we end up with this number 2m minus 1 into n plus 2 by 2. And if I solve this congruence, I end up with the same number basically. I end up with a2m minus a1 minus a2m should be equal to 2m minus 1 into n plus 2. What I mean to say is I will fix the label on this common arc to be 2m minus 1 into n plus 2 divided by 2. This is the label on the common arc. Now, what is my next goal? Now, since the label on the common arc is fixed, now I treat this as a unidirectional path. I treat all this as a unidirectional path. Now, if I consider the sum of the labels on this unidirectional path plus this number should be congruent to 0. Why it forms a unicycle? Similarly, I should consider this unidirectional path, and if I add this number, I should end up with 0. Therefore, my next target will be this. So suppose we have numbers from 1, 2, etc. Let me call that number as 2m minus 1 into n plus 2 by 2 as p. P minus 1, and I just skip p because already it is fixed. I have taken out from the set till 2m minus 1 into n plus 1. I have this set. Now my goal is to partition this set into how many disjoint subsets? N disjoint subsets, and each will have m minus 1 elements basically, because m minus 1 elements will occupy the labels, on the unidirectional path, and those numbers add up with this p, and it congruents to 0. So that is my next target. So to do this, I fix this. So the n copies here, n refers to the number of copies, and each copy, the unidirectional path, if I add the labels on the unidirectional path, I end up with this number 4mn into m minus 1 plus 4m plus n minus 2 divided by 2. And if I add this number 4mn into m minus 1 plus 4m plus n minus 2 by 2 with this number, then essentially it is congruent to 0 modulo 2m minus 1 into n plus 2. And it is true with every n copies. So essentially I end up with the labels for the directed edges of n dash cm, right? So yeah, this is what we have proved. So in this lemma, I just discuss about the proof when the case for m equal to even. When m is odd, it is quite different. I will skip the details. So if m is even and n is anyway it is fixed, it is even, then in this lemma we have proved that we can partition the set into disjoint subsets whose cardinality is 2m minus 1, and the sum of the elements is add up to this number, right? To prove this, we use the generating function technique. So this is the idea. So I put all the numbers from 1 to 2m minus 2 into n plus n minus 1 in this matrix form, and I consider one number from each column. This is the equation. Maybe now it is very evident. So x1, my x1 belongs to the first column. I pick the number from the first column as x1. I pick the second element for x2 in the second column and so on. I pick one element from each column, and that sum should add up to 4mn into m minus 1 plus 4m plus n minus 2 by 2. If that is the case, I end up with the labeling on the unidirectional path. So that's the idea. For this, we use generating function technique, and this is the corresponding generating function. Using this idea, we have proved that there exists at least one solution. At least n is the, I will set the minimum number of solutions to be n, and this n is positive, and therefore I end up with a graceful labeling for the digraph n-cm where n is even, right? And this is the idea. Maybe I will skip all the details. Maybe I can illustrate this. Let me consider 4 minus C4. Here both n and m are even. Essentially, I will fix the head label to be 7. 2m minus n, 1 into n plus 2 by 2 is 7. And I just skip the element 7 from this set. And now I partition this set into 4 disjoint subsets so that the sum should be equal to 14, right? So this is the partition. So this is the equation, x1 plus x2 plus x3 should be add up to 21. And this 21 with 7 is 28. And 28 is basically congruent to 14, mod 14. Hence the labels on the sum of the labels on the unicycle add up to 0. And these are the solutions. And the minimum of n comes to be 2. Hence there are 2 solutions for this problem. And I just rearrange it and I end up with graceful labeling for n dash, 4 dash C4. So these are the 2 labelings. And also they have proposed this problem. So if n is even, we are sure it is graceful. If n is odd and n is greater than 14, but anyway, the product n into m should be a multiple of 2. Is it graceful? The only problem with n is odd, we cannot fix the label on the common arc. It behaves quite randomly because of this congruence, because the total sum on the right hand side add up to 0. But somehow we are able to give one example at least, though we are not able to prove with this idea. Even this idea has some limitations, but still we are able to give one example, counter example to ensure that there exists a graceful labeling for the digraph n-cm where n is odd. So this is the sequence we generated. If we put it on the edges, we end up with the graceful labeling for the digraph. And this is the third conjecture. Here, Du and Son conjecture that for again n even and any integer m is the digraph n.cm is graceful. In fact, we have proved much more than this conjecture. We have defined a larger class of digraph out of this. Instead of considering n copies of basically n.cm refers to this. So we have one common arc and there are many cycles. So these are unidirectional cycles, not overlapping, of course. So with one common arc, this is n.cm. They expect all cycles to be having same number of edges, but we in fact consider this general digraph. Here the digraph, this digraph refers to there are n1 unicycles of n1 copies of cm1, n2 copies of cm2 and so on. So it is a much general graph. And luckily, anyway, if you want to prove this digraph is graceful, we know that this digraph is balanced digraph because in degree and out degree of each vertex is same. Hence, it is a balanced digraph. Hence, the number of edges should be even. Then only we can say that it is graceful. And these are the existing results. And this is what the idea. So basically, if we want to prove that it is graceful, again partition is coming into picture. We have to partition the whole set into disjoint subsets where the sum of each subset should be congruent to 0. Then only we can say that it is graceful. So that is what we have done. To prove that, we rely on the Friedlander result. He has already proved it. One can partition the whole set into disjoint subsets where the sum of the elements in each subset is 0. It is already proved. So using that result, we are able to prove this conjecture. So this is the whole idea. So I will skip the details. And yeah, this is the example. And if I put it, we end up with a graceful labeling for this diagram. So, and this is our conjecture. So far, yeah, we know that. So in the very beginning, we have seen that the digraph, balanced digraph is graceful, then the total number of directed edges should be even. But we still don't know whether there exists a digraph with even number of edges, whether it is graceful or not. But we strongly believe that all degree balanced digraph with even number of edges is graceful. This is one interesting problem we are looking at it now. So that's all from my end. So yeah, thank you. Any questions or suggestions? Yeah, suggestions are welcome.
Please.
Sir, so what about the gracefulness of digraphs which is not unidirectional?
Yeah, again, the system of simultaneous congruences is totally different. So again, it boils down to solve the system of simultaneous congruences, and it need not be 0 because the left-hand side is not 0 anymore, right? So even we end up with a graceful labeling for odd number of edges as well. In that case, if you reverse the directions, you may end up with graceful labeling for even Cn where n is odd.
Thank you, sir.
Okay, so thank you. So let's give a thanks for the speaker. It's a very nice result. Give the session for the next one is okay. So I give the session to you.
So I take this opportunity to thank our chair, Professor Kiki, and I would like to thank our speakers, B.S. Panda, Professor B.S. Panda and Professor Shivraj Kumar. Now we'll be proceeding for the online session, and all those who are having their presentations can go to their respective rooms. I'll just announce the room numbers. So in room number 103, we have S. Karthike, Anthony, Amalia, Nivedha, Shruti, Arun, Kshitij, Ninu Susan, Sridhar, and Shri Priya. This is in room number 103. Then we have Shivani Rai, Anup Kumar, Mohammad Azmi, Manas Singh, Jyoti, Kevin, and Gurumurgan Ganesh in room number 203. All these names in room number 203. Then in 207, Nirakar, Tajinder, Sumanta, Shashira, Shivani Goyal, Margarita, Dr. Ashish, Dr. Jitendra, Mr. Albin. All these are in room number 207. Then we have Mr. Praveen, Mr. Bipachi, Dr. Anand, Dr. Karuna, Dr. Anuj, Ms. Shobha, Mr. Rahul in room number 208. I repeat, these are the names in 208. Then we have V. Kamala, Grace, Murugan, Dr. V. Murugan, Miss Priyanka, Miss Binki, Dr. Soumya, Mr. Sandeep, and D. Lavanya. They are in room number 308. I repeat, these are the names in 308. After that, we have got Mr. Deepak, Mr. Jabir Hussain, Ranbir Singh, Dr. Raibanak Sen Gupta, Radha Madhavi, Dr. S. Devi, Dr. Lalita. All these in room number TIC room, which is just above this floor. So TIC room is above this floor. Thank you so much for attending the session. All the dignitaries are requested to be present here to move to the tea break. All the guests.
Start grade 103. I was present yesterday itself.
Hello. Good afternoon, ma'am. Ma'am, can you hear us? Can you hear us?
Okay, Dipakshi.
Hello, ma'am. Good afternoon.
Good afternoon. Happy to see you. Make me to share the screen so that time we don't take much time.
Sorry, ma'am, didn't get you.
You make me to share the screen. Share the screen, no?
Acha.
Allow me to share the screen so that time we don't make take much time.
You can share, please, ma'am, if you want.
See, I want to know whether I can share or not.
Start sharing. You are co-host now, so you can start sharing. And once we will start the session, then you can start presenting also.
That's what, just to allow me, see what happens, let me, okay.
Ma'am, click on share screen. Click
No,
on
no,
share.
no problem, no problem, I'm doing it now. So I'm seeing this one, then I open my, this one, PPTs, okay.
Presentation on there.
Are you able to see my PPTs? No.
Ma'am, you have to click on share screen, and after that you have to.
See, I have opened my PPTs, but thing is that I put it, no problem, just 1 minute. See what I do, just 1 minute.
Okay.
No. That's 1 minute.
Ma'am, open your PPT, then minimize that screen. Then
Okay, just one. Okay, I got it. That's one happens, no. Oh, it has become big, no. Desktop.
Ma'am, you have to open your PPT. After that, you have to minimize that PPT, and you have to click on. You have to open this Zoom meeting. Zoom meeting window.
Zoom meeting is open, no? Zoom meeting is open only.
You will see the share screen button, ma'am. Click on
No,
share.
just one. Let me just delete which are unnecessarily plates which have come unnecessarily, because I will just 1 minute. See now I'm going to open PPTs. Okay. After sharing, I'm getting your full view, and then I open my PPTs. Okay. I go to the Finder and I open my PPTs. Okay. So once the PPT is open, I have to just 1 minute.
Again, you have to go to the Zoom, ma'am. Again, you have to
No,
go.
just 1 minute. Then just 1 minute. Just 1 minute. But thing is that the screen becomes becomes shorter. It becomes big. Just give me time, okay? No problem.
Sure, ma'am. No issues. We have a break of 5 minutes, so we can do
No,
it next time.
I should be able to see my PPTs being open now. Okay, that's what I'm not able to do it. Sometime it happens, no. Okay, what happens? I click the share screen on this one, okay.
And share the full system. You will get the option of sharing the window or share the screen. Share the screen, complete screen, ma'am. Then everything.
Entire screen, no.
Entire
It is entire screen only.
Yes, ma'am. You just share the entire screen first, ma'am.
Eh?
You will have to click OK also at the bottom. You will see OK. All. After selecting click and share entire screen, you will have to click on.
Just 1 minute. Now I'm back to this one. Now I'm back to a full screen. I share the screen first, okay?
Yes, ma'am. Click on share screen, ma'am.
वो ऑटोमेटिक शेयर हो जाता है. Okay, share the screen. Okay.
Option to share entire screen.
Entire, it is.
Now we can see your screen. Now we can see your screen. Now, अच्छा हमारी है. Okay. Click on share screen, ma'am.
I have shared the screen, but I'm seeing what happens. No, what choose to this one window Chrome tab. See, after I see the blue button below, I share this one. Okay, then I see your screen. Okay.
You have to click on, ma'am, and share entire screen, and then you have to select at the bottom OK.
See, entire the scale is already, entire screen is not coming, na.
Okay, what are the options that you are getting, ma'am? Please.
See, choose what to share. Entire screen, window or Chrome tab.
Choose ma'am entire screen. Click on entire screen. And then at the bottom you will get share.
I'm not getting entire screen is not getting now.
What are the other options, ma'am?
Now it has come. Now I share. But I have to, before that I have to open my window.
No need to do that. No need to do
No,
that.
before that I have to open my PPTs now.
Do that, ma'am. When you are sharing entire screen, then there is no need to do that.
But then my PPTs are not available.
You will open it afterwards, ma'am. First share your entire screen, ma'am. You can share it.
The entire screen I should share, is it?
Yes, ma'am.
Okay, I share it. Okay, now I open my this one. Just 1 minute.
Yeah, we can see your now. Now we use
Just one minute. Just 1 minute. Because what is coming? It is not getting opened.
first click on some other icon, ma'am, and then come back to this because now you have. Yes, now come back again. Come back. Only one click, ma'am. Or
I put one click.
double click, ma'am. Double click.
Now I put double click.
Ma'am, click on another icon and then come click on your PDF icon.
See, I'm coming to my PDF. Okay, you must be seeing now.
And you're clicking on the name. Instead of that, you click on the icon of the presentation. Double click on that, yes, ma'am. Double click.
Now I have to double click on this one now. On my name.
What you are doing? What you are doing? Okay, fine.
Fine. I know the problem is because it is MacBook sometimes figure इधर उधर हो जाती है, ठीक है ना? Okay, thank you. क्या के? Okay, thank you. Rajesh for teaching me. Okay.
Yes, ma'am.
Okay. Okay. So time we utilize. Okay.
Hello, Prof. Akarya. So I will be.
Hello, Kitty. How are you?
I will be the chair of your session. So.
Oh, I'm very happy to know that one. Anyway, even seeing all of you, I'm very happy.
So we need to wait a little bit because the participants still in the break session.
Yeah, I know. There will be very less participants at present. Many of them has gone for their presentations. No. How are you, Kiki?
Fine. I'm happy to be in India again.
Yeah, that is the last time I think you came in 2018.
So unfortunately, I cannot meet you face by face.
Yeah, that's nice. Nice. I could not come because Delhi is very cold.
So.
What is this?
Okay, so good afternoon, everyone. So it's an honor for me to be chair as in this session. So we know Dr. Mukti Akarya, I think, but I would like to give some introduction. So Dr. Mukti Akarya is working as a professor at Chris University in Bangalore, and she has completed her MSc in PFU Moscow and did the PhD program in mathematics from IIT Bombay. And she was appointed as a visiting scientist at Mehta Research Institute, and then joined in IIT Delhi as CIR pool officer, and then as a lecturer in NCERT Delhi. And then she joined Delhi College of Engineering, now Delhi Technology University, or we know it's at DTU. She's got the professorship in 2002 at DTU and headed the Department of Mathematics at the same till 2013. She currently works as an independent researcher and has several visiting faculty positions. Her specialization is graph theory, and her main contribution are in SciGraph, graph spectra, graph labeling, and PetriNet. And she has more than 60 research papers published. Today, she will give the presentation with the title Product Cordial Labeling, the New Perspective. So please, Professor Akarya.
Thank you, Professor Kiki, for your nice introduction. And I'm glad to see all of you on this platform. And first, I am very thankful to the organizers of this conference, and in particular, Dr. Rajesh Singh, who gave me an opportunity to use online platform for my talk. I feel very happy to see many non-personalities whom I have met during different conferences, workshops. So my title of my talk is Product Cordial Labeling, New Perspectives. This is not a new concept. This is a very old concept. And I have taken this concept for the motivation purposes for the research scholars, because there are many results on product cordial labeling, which we can further generalize it. That means I was always interested to find whether we can have if and only if condition for some of the graphs who have product cordial labeling. Of course, I will not speak much about labeling problems because it has been explained by many authors: graceful anti-magic labelings, alpha beta rho labeling, and then graceful labeling for digraphs. So I will skip about that one, and I straight away go to the this one. I will not explain what is a graph. Okay, so I straight go to straightway I go to the graceful cordial labeling. The concept of cordial labeling was introduced by Kahn in 1987. And where each vertex to be labeled with 0 and 1. The label of each edge is the absolute difference of the labels of its end vertices. Now afterwards, now in this one, we have labels of the vertices only, and the edge labels are nothing but the absolute difference of its end vertices, which also turned out to be 0 and 1. So further, the condition is posed that is absolute difference between the vertices with label 1 and label 0 must be less than or equal to 0. And same thing, absolute difference between the labels, between the edges with label 1 and 0 must be less than or equal to 1. So this was, and he called this is a weak version of graceful labeling. Reason, as I understand, because in graceful graph, we label the verse from 0, 1 up to Q and take the absolute difference of end verses and then see that all the edges should be from 1 to Q. But here, since 0 and 1, so later on he compares, that is the difference between edges with 0 label and 1 label should be less than is equal to 1. So this is the paper in which he has introduced his concept. 1987, it was published in Arcs Combinatorics. Now, depending on this definition of cordial labeling, many authors introduced a lot of different variants of cordial labeling. Now, it's the same concept, you label the verses with 0 and 1. In the place of absolute difference, many other operations has been tried by several authors. In one of the papers by Sundaram et al., they called it product cordial labeling. There is an absolute difference on edge for the edge values. They put it at product of f of u and f of v, which is nothing f of u and f of v, nothing but the labels to the vertices. This is a 2004 paper. So they call it product cordial. Why they are calling product cordial? Because the operation used is product on the values of the end vertices of the edge. And same thing happens when we can say such a labeling is a product cordial. The same condition, that is vertices with label 1 and 0, which are showing as this one, FV1, that is vertices with label 1 and vertices with label 0 differ by 1, and same thing with the edges. EF1 is nothing but the vertices with edges with label 1, and EF0, they should also, the absolute difference should also be 1. Now, if you want to have, because this was the first paper on product cordial labeling, you can refer to this paper. And apart from that, I will give some other few papers also, which later on they did on this one. The paper by Vaidya and Kanani, they call some cycle-related product cordial graphs, published in 2010. Then again, paper by Vaidya and Barasara, product cordial graphs in the context of some graph operation, published in 2011. And then other paper by Rockard and Garsara, related to product cordial labeling of some cycle-related graphs, which was published in 2014. Now, my main purpose of coming to new perspectives is I take the known results from these papers, maybe some other papers also, but basically I take the known results on product cordial labeling from these aforementioned papers. Okay. Now, in one of the papers by S.K. Vaidya and two papers he has, what they define, they take a graph G and take G is defined as the union of cycle Cn and K1n at one of the vertices of G. Their result is this graph is product cordial for every n. That is, if I have a cycle Cn on n vertices and at one of the vertex of the cycle we put n appendant vertices, then they claim that it is product cordial for every n. And it is true. Okay, I have shown the product cordial labeling. Give the label 1 to the vertices on the edge on the cycle and labels zeros to the pendant vertices. You see that the caudality condition for the vertices is satisfied, and caudality condition for the edges is also satisfied. And second result is 1. That is same way you take a cycle with a chord Okay, you take a cycle Cn with the chord and put K1n at one of the verses of the cycle. And then they also show that this graph is also product cordial for every n. Okay, so these are the two results which gave us thought. That is, that basically, if you look at their structures, I may call it partial corona. That is, they are putting pendant edges one of the vertex of the cycle. But instead of cycle, it can be any graph. Now I define an operation called corona operation on the graphs. I take two graphs G1 and G2. The corona operation on G1, G2 is defined by taking a copy of G1 and taking the number of verses of G1 copies of G2 and joining the ith vertex of G1 to every vertex of ith copy of G2. The graph obtained by this operation is denoted by the G1 circle G2. In this one, this is the corona of C4 and K2. So this is C4. I have taken, it has 4 number of vertices. I have taken 4 copies of K2, okay, and then join each vertex of K2 the corresponding corresponding ith vertex. This is the ith G2. So this is the corona of C4 with K2. Now, if you look at the previous theorems, okay, as I told you that I will call it a partial corona. But then again, I pointed out that I need not have a cycle. What are the other graphs? What are the other graphs for which this will hold? So I take a graph G such that number of vertices, it has n vertices and m edges. And I take a corona graph H, which is nothing but G corona with p copies of K1. That is, at each vertex, I put p copies of K1. And then actually, how many at each vertex of the cycle, we will have p pendant edges or vertices, vertices of degree 1. Now, this graph, I have this H. When I can say that such a graph is product cordial. Is product cordial if and only if G satisfies any one of the following. What is that one? That is M is equal to N, number of edges is equal to number of vertices. Second condition is number of edges is equal to one less than the number of vertices. And third condition is number of edges is one more than the number of vertices. And fourth condition is the number of edges is equal to 2 less than the number of vertices. Now look at their two examples which they have given. Okay, this one and the previous one cycle with the K pendant edges at one vertex. They are, sorry. So M is equal to N is the first example which they showed that this graph admits product cordial labeling for every N. Second one is coming for a tree. If you take a tree and put any number of pendant edges at each vertex of T, that graph is going to be product cordial. And then M is equal to N plus 1. That is, number of edges is equal to 1 more than the number of vertices. It is their example where they have taken a cycle with a chord and put, it is cycle Cn on n vertices with their chord, and at one of the vertex they have put n pendant edges. That is product cordial. And fourth one, if you see, number of edges is equal to number of vertices minus 2, that it has to be a disconnected graph. So this is the one where it need not be a cycle. It need not be a cycle. We can have a tree, we can have a graph with the M is equal to N plus 1, and then we can have a graph with N minus 2. And with that operation, all these graphs turned out to be product cordial. Now I have shown here, just because it's online presentation, I have taken C4 with the product cordial with 3 pendant vertices. It is product cordial. Labeling is very easy. So what we do, first we take label the vertices of the cycle with N, with the label 1, and then same number of vertices with 0, and remaining we divide it. Okay, so here if you see, the condition of cordiality is well defined. Then second example is for a path. Path, we have taken path on 5 vertices, and we have taken corona is 2k1. Okay. Then you take a cycle with the chord and corona with 3 copies of k1 is also product cordial labeling. You can see the quality conditions on edges is holds, and same thing the caudality condition for the words is also holds. Now you take a disconnected graph. I have a disconnected graph triangle and a pendant vertices, and you put a 3 corona with 3 copies of k1, and you can easily see the graph obtained from by this operation is product cordial. So now now I take up other one, okay, other theorem. That is, I take a graph G, which has number of vertices is n and number of vertices is m. Now earlier, the previous theorem, we have put a corona taken from the same, we have put the same number of pendant edges, which is coming to corona of some k and bar or p copies of k1. But here I just changed a little bit. What I said, we are obtaining a graph H from G by attaching P1, P2, Pn pendant vertices at U1, U2, Un vertices of G respectively. That is, at each vertex of the graph, there are some, at U1 you have P1, at U2 have P2, and so on. But I don't put any condition on PIs, whether they should be greater than or equal to 0. They may be 0 also. And one vertex may not have any pendant edges. So such a graph is product cordial if and only if G satisfies any one of the following. That is, M is equal to N, it is a cycle. Okay, you take a cycle, you put any number of pendant, you want to put some 10 pendant edges, divide into 4, divide into 3, put it one vertex and other things, okay? And then second graph is a tree. You take a tree and show that, put any number of pendant edge, pendant vertices and join them in any of the vertices. And second graph, third condition is coming as the disconnected graph. Only in condition this one is, that is, any one of these conditions should be satisfied. Along that, P1 plus P2 plus 3, the sum of PIs, which I put pendant edges on the vertices, they should be greater than or equal to n minus 1. Now, if you look at this theorem, my one graph is not coming. Basically, when we have a number of the graph, number of edges is one more than the number of vertices. But it is surprise, of course, I have not given that result. It is surprise to see that for that graph, this is not satisfied. That means for that graph, I can have a pendant edges, even 1 also, even 2 also. It need not, this condition, with this condition, that condition violated, okay? This need not be, it can be less than or equal to some k, where k is maybe 0 also. Okay. So with this one, what happens now? Let us restate their results. Okay. And then see that what is the difference which the result we obtained and they obtained. They have, as I told you, they have take a cycle Cn and put at one vertex, put K1 and that star, and they say this graph admits product cordial labeling. That is, this graph is product cordial for every n. So what we have proved, the graph G is defined as a same. I defined the same graph. Okay, the cycle in put that one. G is product cordial if and only if P less than is equal to n minus 1. Okay, is they say that is it should be n, but my condition is that P should be greater than or equal to n. So what happens for n? It will be their result follows from this one. First theorem follows from this one. Okay. Second condition, when they take a cycle with the I have a cycle with the chord. Okay, and then they prove that Cn is a cycle with the chord, and with K1 and union, they say it's product cordial. And what we have shown, that is G is product cordial if that is CK1P at one of the verses as a chord. This graph is product, but this theorem, as I have told, I forgot to delete it. It holds for NEP. It holds for NEP. Therefore, I'm leaving this theorem. I forgot to remove from this one. Okay. Now, as I noted in the first theorem, what are those graphs? Cycle, trees, then graphs with the number of edges is one more than the number of verses, then the discrete connected graph. So I need not have only CN. I can have all those four graphs, which is I have stated for in my first theorem, as far as their two results are concerned. Now, see what happens. Then they take a BN graph. BMN is a bi-star, which is obtained from an edge UV by putting M pendant edges at U and N pendant edges at V. And this graph is denoted by BMN. Their result was BNN is product cordial for every N. BNN is product cordial for every, that M is equal to N. Now, if you look at this graph, I take BMN, okay, no problem. That is BMN admits product cordial. This graph BMN admits product cordial labeling if and only if any one of the following holds. That is M is equal to N. That is in a edge, at a edge UV. One side you have M edges, they equal edges. Other side they differ by 1. Other side they differ by 1 because M is equal to N minus 1 and M is equal to N plus 1. You get the isomorphic pi stars. And other one is they differ by M is equal to N plus 2, then M is equal to N minus 2. They both also gave us the same isomorphic pi stars. So their result was only for this first one, that M is equal to N. But I can reduce the pendant edges at U. I can have the relation between pendant edges at U and V, which you are seeing from this one. Okay. It has been written M is equal to N plus 1, M is equal to N plus 2, and similarly M is equal to N minus 1, N plus 1. See, look at, if you change the role of U and V, they become isomorphic graphs. Okay. Now next, I have shown here B33 product cordial, but only that you have to see that whether the verses which are degree greater than is equal to 2, that is end verses of the edge, how they should be labeled. You cannot label with 0, 0. Okay, that you have to see. Then this is a B32, then B02. Okay, sorry, B02 class we have shown they are product cordial. That means instead of having one bi-star, okay, we have many bi-stars which turned out to be product cordial. Then they take a bi-star, okay. They take a bi-star, then they take the square of that one. So they call B square NN. But I also do the same thing. I take BMN and take the it's a square graph. That is only that. What is a square graph? You take a graph and join the vertices which are a distance 2 from each other. Okay. Now their result says that is B square N is not product cordial for any N. If at their end vertices you have the same number of pendant edges and you take a B square, you take a square graph, that is not product cordial. Okay. Now I take BMN. At one vertex I have M pendant edges, other vertex I have N pendant edges. And if you see, it is product cordial if and only if M is equal to N plus N or M is equal to N minus 1. They see M is equal to N plus 1 or M is equal to N minus 1. They are isomorphic if you interchange the role of U and V, and they turned out to be product cordial. But when M is equal to N, they have shown that that's not. They have shown the existing of labeling, showing that it's not product cordial. But here it is very well. Turns out to be product cordial. Again, here the same thing. That is the U and V should not be labeled with 0, 0. Okay. then you will not be able to get the product cordial label. Now, then they see these are the graphs which I have taken from their papers. Okay, not that I have created my own paper. They take a BNN, okay, and then take a new another vertex, and that vertex they join to U and B respectively. Okay, then they say that is graph obtained from this admits product cordial labeling for every n. So I go again same way. Okay, I take BN, BMN, take a new vertex and join that new vertex to the U and V. So that means we get a triangle in that one. At a triangle, at two of its points, we have pendant edges. Okay, and go back to the previous theorem, you will get the answer. First theorem. Now G admits product cordial labeling if and only if any one of the following holds. M is equal to N. Their result. Okay, M is equal to N plus 2. M is equal to N minus 2. They are isomorphic. Change the role of U and B. Then M is equal to N plus 3. M is equal to N plus 4. So that way we have I can say four bi-star graphs whose square graph admits product cordial label, and one of them is their result, M is equal to N. See why earlier I was never interested in this graph labeling problem. I will tell you in the end why I came to product cordial labeling. Okay, at the end we will get it. So I have shown here M is equal to N, M is equal to N plus 2, M is equal to N plus 3. And then I have shown that they are M is equal to N plus 4 and M is equal to minus 4. Okay, no problem. And shown their labeling, and that you will see. If you look into the picture, you can yourself find out that they are product cordial. Now, then one of the paper by Professor Vaidya and Kanani, they have this result. They take two cycles on same number of vertices. Okay, having an edge in common. Okay, take two cycles on the same number of vertices having an edge in common. If you look at that graph as a whole, what I will say, we have a cycle with a chord, and they say such a graph is not product cordial. And note that in this graph we will have 2n minus 2 vertices, and number of edges will be 2n minus 1. What can be said about the graph, which is the union of two cycles, Cn and Cm, having an edge in common? I change the length of the cycle. Why should I have both the cycles are the same length? They can be of different length also, but they should remain cycles. The graph, which is a union of two cycles, Cn and Cm, having an edge in common, is product cordial if and only if n is equal to m plus 1 or n is equal to m plus 2. Okay, that is now they said that's not product cordial. For every n they say it's not product cordial. Then they take cycles, two cycles are on same number of vertices, and such a graph, when they both the graphs has a edge in common, that's not product cordial. Then I do have such a operation. I do have the graphs where the length of number of vertices one more than and two more than that one, they turn out to be product cordial, because I'm not destroying their class. I'm not destroying their operation, but I'm just taking the cycles of different number of vertices. So there I have shown C6 and C5, then C4 and C6 and C4, C6 and C5, and we have shown the labeling, and which turns out to be product cordial labeling. Now you will ask the proof. See, proof is very simple. When you write the proof, we must know how many vertices are labeled with 1 and how many vertices are labeled 0. And then similarly, how many vertices are labeled with the 1 and how many edges, same thing with the edges. Then you get two Diophantine equations as far the condition of caudality is concerned with respect to vertices and with respect to edge. And you solve that one and you get this relation. Now, they take a graph, they take two copies of Cn. Okay, they take 2 copies of Cn and join a path pk. They take 2 copies of Cn, take one vertex at one cycle, other vertex at put a vertex on put a path on k vertices. But here only that I just mentioned in my next theorem, the graph obtained by joining 2 cycles Cn and Cm by a path pk is product cordial if and only if any one of the following holds. That is, m is equal to n or m is equal to n minus 1 when k is even. Okay, m is equal to n or m is equal to n plus 1 when k is odd. Therefore, they did not bother about the length of the path, which is odd number of vertices or even number of vertices. They got the result first, m is equal to n. Therefore, they say that graph obtained by joining 2 copies of Cn by a path pk is product cordial. But it depends, and they give us different structures. And m is equal to n is both. It is in both the condition when k is even and k is odd. It was interesting to solve those this one. Okay. Now in this one, what I assume that pk is a path on k vertices whose n vertices are joined by an edge to a vertex at c1 and cm respectively. Note that this will have m plus n plus k vertices and m plus n plus k plus 1 edges. Okay. But when they consider they're the vertices which are on both the Cn, that they count as a path, but I don't count that one. Okay, because I join them by bridge. Look at this one. Okay, so I have a path on 4 vertices. There are n vertices. I join to one vertex of one graph, another one to the other vertex of the cycle, and I get their graph. And which is one cycle is C5, other is C4, and it is product cordial. And similarly, I have taken with the C5 and C6 and shown you the product cordial labeling. Now, same result I wanted to extend for as follows. Okay, I'm not giving its figures. It will be easy to, you can make out for yourself. Let G1 and G2 be 2 graphs having n vertices. They have the same number of vertices, but the edge is different. They have m1 and m2 edges respectively. Then we obtain a graph H from G1 and G2 by joining a vertex of G1 and G2 by path pk. I don't take cycle. Okay, I take any graph with these conditions. Clearly, H has 2n plus k vertices and m1 plus m2 plus k plus 1 edges. H is product cordial if and only if any one of the following holds. m1 is equal to m2. Okay. Look, I will come to their theorem. Or m1 is equal to m2 plus 1 or m1 is equal to m2 plus 2 when k is even. Look at that. They said for M1, they have cycles of the same length. Okay, they say it is product cordial. Then second condition, when k is odd, m is equal to m1 or m1 is equal to m2 minus 1 or m1 is equal to m2 plus 1 when k is odd. So if I put m1 and m2 are equal to n, then you get that result. Okay. Then we remain this one. N is equal to you remain in this condition depending upon this one. So basically their result that such a graph admits product cordial labeling. See what happens. Everybody knows what is a dragon graph. It is also called a tadpole graph. It is also called a kite graph. Basically all these results which I have mentioned, they came from this result. In one of the paper, okay, paper of 2004 in which they introduced product cordial labeling, their theorem is dragon graphs are product cordial. This was their theorem, 2004 paper, and it has been referred in many papers. And now I will tell you the motive behind for this write-up which I have written. I got some continuously some 4 or 5 papers on product cordial. And every paper will have paper reference of this paper. Then I got anxiety. What is this? Let me go and find whether I'm able to get this paper. I got the, what do you call it, image copy, which was not, I took the printout and started working. Then I said, no, I'm wrong. I may be wrong. I may be wrong. I may be wrong. Okay. Then I went back to Father Joseph Varghese and I told somehow my mind is not admitting this one, that dragon graph support cordial. Then I got a very small counterexample. That counterexample is the thing. I took a triangle and put one pendant edge. That's all. So I have a cycle which is a unicyclic graph having 4 edges, 4 vertices. That's not product cordial. Then the question arises, okay, that is, can we characterize dragon graphs which are product cordial? So basically, how we define the dragon graph, we denote by D and K, where n greater than or equal to 3, K greater than or equal. They are unicyclic graphs formed by joining a cycle Cn to a path Pk by a bridge. So here Pk means is a vertices on the cycle. The one of the edge we put a bridge. So this already the paper has been submitted or accepted for this one. Now this is the characterization of dragon graphs. The dragon graph D and K of order n plus case, order will be same, number of vertices will also be same. The number of vertices as well number of edges will be same because a unicyclic graph. Where n greater than is equal to 3, k greater than is equal to 1 is product cordial if and only if n plus k is odd or k is greater than n minus 2. Or k is greater than n minus 2. Now here we have taken D6, 5. That is, I have a cycle of 6 vertices and I have a path on 5 vertices. And we have shown that it is product cordial. 6 plus 5 is 11. So it's odd. Okay. So all the vertices you label, it's need not that all the vertices will receive 1. You label all the vertices, cycle vertices on 1 and other vertices on 1. But that need not be same. But because when k is less than n, then it will not be there. So my k should be, in this case, when nk plus is not odd, my k must be greater than n minus 2. So here, here you take a graph where n plus k is even, okay, and k is less than n. So I have not shown the labeling, but see what happens, n plus k is even, but k is less than n. So once n k plus even, in order to the cordiality condition is satisfied, the vertices n plus on the vertices, I should have n plus k by 2 vertices receiving 0 as well as 1. So 1 n plus k by 2, k is less than n. So one of the vertex with label 1 will be at label 0 will be on the cycle. So due to vertex which is label 0 on the cycle, that vertex gives us two edges with label 0. So number of edges with 0 increases. That is cordiality conditions on the number of edges is not satisfied. That is, if I pick up edges with label 1 and pick up edges with label 0, their absolute difference is not less than equal to 1. Okay. So that is later on in the same paper, we took a dragon graph and took its line graph. The question was, when we can say the line graph of the dragon graph is product cordial. Okay, the line graph, you know the definition very well. I don't think I have to explain that one. This line graph of the dragon graph is product cordial if and only if n is greater than 3 or k is greater than 1. Okay, or k is greater than 1. That is there. Because if you take n is equal to 3 and k is 1, then it's not product cordial. So a line graph, with this condition it comes. The very, of course, the proof of this line graph when we prove takes a lot of sub cases to prove that the product cordial labeling does not exist, for which D, the product cordial labeling does not exist for its line graph. Now, these are my references. As I have already given you in my text also, by Kar's paper, Sundaram, then Vaidya, again Vaidya, Rokar, then our paper with Dr. Varghese, that is characterization of product cordial dragon graphs, which is to appear. And naturally, you have a survey on graph labeling, which is the best one. And recently, we introduced parity labeling in sign graphs. Okay, and, it has that is parity labeling in sign graphs. That is nothing. This concept, I think, if you read this paper, these two papers, someone who is working on graph labeling must know, will come to know from where we got this idea. And we took it to sign graphs. We took it to sign graphs. Because we wanted, because if we have a parity labeling, we wanted to have that one. And then another paper, we have this one. This paper which I gave a talk, this is not all the results are included in that one. One that has been submitted. Now, of course, when we were doing product cordial dragon graphs characterization, we had one question in our mind. So there are many varieties of unicyclic graphs. Product cordial is one. Dragon graph is one. Then any cycle with the that is any number of pendant vertices at each vertex, or CN corona with K1, corona with P copies of K1. That is also unicyclic graph. And you can create many unicyclic graphs. You take a tree and one there you put a triangle or put a cycle, that becomes the unicyclic graph. See, there is already a result that if you take a cycle with the corona with K1, it's product cordial. And also you say, if you take a cycle with the result, you know our result. Okay, you take a that is you put P1, P2, P3 up to Pn pendant edges at each vertex of P1. That also turns into product cordial. That is also unicyclic graph. Now the question comes: you have a unicyclic graph. Okay, you remove the cycle. Its components. When you remove that cycle, it becomes a disconnected graph. So far, the examples which we have, after disconnected, we have only pendant edges. Now we have only vertices. That is totally disconnected graph. Suppose it is not totally disconnected, means all not isolate vertices. So we put a condition. We tried our best during that time when we were doing characterization of dragon graphs. That is unicyclic graph. You remove its cycle. The remaining components should be a forest. Each component need not be isomorphic. Each component need not be isomorphic. But I have not included that result because I have to yet prove. So we can prove that result very well. That time we were not able to get the method, the procedure to label its vertices with 0 and 1, so that we are able to show that correlative condition is satisfied. Only 2 days back, I got that condition. That paper will be different one. So with this, I finish my talk, and my main motive has been, that is the students, the newcomers who come for the research, just they start taking some, what happens, some concept and start working. But I feel sometimes I feel little bit disturbed. Yesterday I attended one paper presentation. Okay, one of the papers was in the energy of divisor cordial graphs. Energy of divisor cordial graphs. There is nothing but a divisor cordial, that is, you label its vertices from 1 to n, where n is the order of the graph, and put 1 if f of u, f of v divides, or f of v, f of u, a is divisible by or b is divisible by. They were a and b are the labels to the vertices, and 0 otherwise. Okay. So that is they are showing finding is energy. But I don't consider this is a problem because their underlying graph will be same only. When I take any product cordial or cordial, or there are many different avtaras of cordial labeling. If somebody must be interested in cordial and go and find out. I have collected about 8 different avtaras of cordial labeling. And some of them I'm trying to take it to, what do you call it, to sign graphs. Already one is taken, that is edge product cordial. So I've taken to sign graphs. So my advice, pick up a problem. It should have some depth. It should have some depth, so that you know what is happening. Because even Suresh has told on a labeling problem, there are more than 3,000 papers. 3,000 papers. But just having a paper on cycle, having a paper on trees, having a paper on cycle with a cord, that I think we should, my colleagues and my personalities who are working in graph labeling, we should encourage students to go for the problem. And with this one, I finish my talk, and I'm grateful to the chairperson, to the organizers, and I'm happy to see all of you. Thank you very much.
Okay, thank you very much, Professor Akarya. So let's give a big applause for the nice talk.
Thank you very much, Kiki. Okay. Sorry, I could not see you in person. Okay. Next time.
Yeah. So any question or comments from audience?
Audience are there?
Yeah, we have some audience here. So any question from the online participant? Oh yeah, so there is one participant raised hands.
Yes, let me know his or her question.
Could you please open your mic and maybe you can ask directly to Professor Akarya?
I will not stop my PPTs, because if she asks, I may have to move my PPTs. Okay.
Okay.
What is the question? We must have put in the chat box. Is it there? I'm not able to see the chat box. He has to be unmuted, no?
Yeah.
He has to be unmuted.
Wait a minute. So I don't know if like
Organizers should do unmute him. Who is asking the question? He should be unmuted, or let the he should unmute all the online participants.
Yeah. Okay. So if you have questions, so could you please? It's Santi. So could you please open your mic and?
Thank you, ma'am. Good evening. This
Yes.
is Shanti from Chennai, Tamil Nadu, ma'am.
Yes.
Thank you for your and this is my question, ma'am. Actually, I have defined some new graph on commutative ring, ma'am. I'm doing my research on algebraic graph theory. So I have defined some new graph on commutative ring, ma'am. I have got some graphs which involves bistars as a subgraph, ma'am. Can I get application for such graphs in real life, ma'am?
Which graph? You want a bistar graph, or
Yes,
you
ma'am.
want applications of this cordial labeling?
No, ma'am. I'm asking about bistars, ma'am. Actually, I'm getting a graph in which bistar is a subgraph, ma'am. It's not the whole graph, but bistar is existing there inside my graph. It connects every vertex of the graph, ma'am. It's actually a connected graph, but bistar is a subgraph there.
No, I want to know your bi-star is a induced subgraph or a subgraph?
Yes, ma'am. Induced subgraph, ma'am.
Induced subgraph.
Yes, ma'am.
No, applications of induced on bi-stars. If I say if I say what happens, suppose there are two persons who are very friendly. Okay.
Okay, ma'am.
Adjacent vertices are their friends, but they themselves are not friendly. The two person you and we are there. He has some friends, and we are also have some friends. The friends are themselves are not friendly. They means they are not acquaintance. They don't have any acquaintance among themselves.
Yes, ma'am. Okay.
That is the one, because that group is actually what happens if you have you have friends, I have friends. Naturally, we should have some interaction among our friends.
Yes,
so in that case, your bi-star graph turns out to be that two persons are friendly, but they are friends. So there are no acquaintance among their friends. Okay.
Okay, ma'am.
That way you think, but it's coming that you are finding a group in your this one in your graph which you are getting where this is happening. Okay.
Yes, ma'am. Ma'am, one more question. Actually, I'm having one more graph on a special ring, ma'am, in which there is some complete bipartite graph, ma'am. Other than those vertices, the others are isolated, ma'am. So is there any application of such graph, ma'am?
You find it yourself. That means if you are getting for commutative rings, okay?
Yes, ma'am. Yes, ma'am.
Your elements are from commutative rings, and you must be having the rule how to put the edges between two vertices.
Yes, ma'am.
What
Yes,
are the
ma'am.
rules? Your operation for which they give you the edges.
Yes, ma'am.
Which binary operation you use to get edges on the commutative ring? Whose elements are the vertices of the graph? Which operation you use?
Yes, ma'am. Okay, ma'am. Okay, ma'am. Thank you, ma'am.
Depends on the operation also, na? Okay.
Yes, ma'am.
See, for the applications, for example, this cordial labeling, if you look at this one, can you give me in the present situation, can you give me this application of cordial labeling?
I'll try, ma'am.
I give you the application. I give you the application. Now the
Yes,
corona
ma'am.
is there. Corona is there. Okay. So
Okay,
you
ma'am.
take 0% label with 0 have a negative corona, and with this one you have positive. With one you have positive corona. You take a product. Okay. Naturally, positive and negative will not match. They will not be put in the same room. But positive and one they can be in the same room. Similarly, 0 and 1 cannot be in the same room. Okay.
Okay,
So that
ma'am.
way it depends the binary operation which you are doing it. Okay.
Okay, ma'am. Okay. Okay, ma'am.
This 0-1 product cordial labeling with the present situation, it has a good application.
Okay,
But
ma'am.
anyway, corona has given a worst meaning of positive.
Okay, ma'am.
Okay, thank you very much, Shanti.
Thank you, ma'am. Thank you so much, ma'am. Thank you.
Thank you very much for the question and answer. So we will close this session with the last but not least speaker, Professor Mukti Akarya. So please give a big applause again.
Thank you very much. Thank you very much. Thank you very much.
I will
I have
the session
okay.
to Dr. Deepak.
I have come to.
Hello, ma'am. Thank you so much for your speech and lecture. I also thank Professor Kiki for her patience and listening to 3 lectures on the go. Thank you so much, sir. Thank you.
Thank you, Deepakshi. Thank you very much. Enjoy it. But today I will not be joining any presentation paper because there is no session is of my interest. Okay.
Sure,
okay.
ma'am.
Thank you very much.
Thank you so much, ma'am. Thank you. Okay,
I'm
bye.
not, okay, bye. Bye. Professor Hinch, he cannot hear you. Unmute him. Okay.